Good morning. I'm delighted to see so many people here. Welcome to the Connect America Phase 2 Cost Model Workshop. Delighted to see so many of you in attendance in person today. Please make yourselves comfortable and take advantage of the coffee and food provided at the back of the room to my right. We also have folks attending this workshop virtually, and I'm thrilled about that. It's very consistent with the theme of today's workshop, which is getting to better networks to all Americans. I do regret that we're unable to provide coffee and refreshments to those attending virtually. You're on your own. Last November, the Commission directed the Wireline Competition Bureau, of which I'm the chief, Julie Beach, to develop a forward-looking cost model as part of the Phase 2 of the Connect America Fund. The purpose of the model is to set efficient amounts of support for deploying voice and broadband-capable networks to unserved areas of our nation. The Bureau has since taken a series of steps to implement the Commission's order. In December, we invited parties to submit cost models into the record. In February, U.S. Telecom and ACS responded by submitting their respective models. A number of parties have since accessed and reviewed both models. And in June, the Bureau sought comment on a variety of model design and input questions. Today, we begin a 2-day workshop to examine the record models publicly and in depth. This process will ensure that the Bureau, the Commission, and the public develop a more complete understanding of these models. It represents another step in our effort to ensure transparency in our own modeling process. As we announced yesterday, shortly following the conclusion of this workshop, we will be convening an online virtual workshop, which will continue for a period of weeks, sufficient to allow public input on all material issues. The purpose of the virtual workshop will be to provide the public with an open and accessible forum in which to discuss the numerous technical and policy questions involved in developing a model. It will foster the back-and-forth interactivity of an in-person workshop without requiring members of the public to physically attend multiple meetings. I want to thank the parties, especially that made the effort to prepare and submit models into the record. While this workshop is not an endorsement of these models, the models have contributed materially to helping us build an objective, factual basis for the technical discussions we will need to have before finalizing our own model. We are pleased to have representatives from both groups that submitted models today. CostQuest, which developed the model submitted by U.S. Telecom, is represented by Jim Stegman and Mark Goodman, while David Blessing of Paris Blessing & Associates and Karen Brinkman will talk about the model submitted by ACS. I look forward to your presentations and a productive discussion over the next 2 days. Finally, I'd like to recognize the FCC staff who organized this important event, including Susan Faizan of our Consumer and Governmental Affairs Bureau, our dedicated but often invisible audiovisual professionals, and David Zessiger and Steve Rosenberg of the Wireline Competition Bureau. With that, I'll turn things over to Steve, our Chief Data Officer, who will be moderating today's session.
Thank you, Julie. I don't have a lot to add to what Julie said beyond some logistics. As you can see from the agenda, there's a lot of ground to cover, so we do want to get moving. Speaking of the agenda, there was a mistake on the version that was published yesterday. That mistake, a 1-hour coffee break mid-morning today, has been corrected. We don't have an hour for coffee. On the version that you may have picked up on the way in the room, there will be ample breaks, but it won't be quite that long. Something to keep in mind that echoes what Julie said as we go through the day. The materials presented here today represent the views of the people presenting them. The materials are not the views or endorsed by the Commission or the Bureau. We want to make sure, as Julie said, that the Commission staff and the public have a full understanding of what's in the record so that we can move forward productively. We will be taking questions both in the room and online. There's Q&A time set up at the end of each session, so if you can hold your questions, if at all possible, that would be helpful. For those in the room today, we have a microphone that we will be handing around so everybody can hear any questions you have. For those online, you can ask questions by emailing to livequestion@fcc.gov. We have an hour for lunch today, conveniently scheduled right around lunchtime, and there's a list of restaurants on a piece of paper at the front entrance, so please consult that. I have to say there aren't a lot of choices, but it's worth checking to see what's there. And with that, let's kick things off because we do have a lot of ground to cover. Jim Stegman from CostQuest and Associates will be leading things off. Jim?
Thank you, Steve. I'm glad to see that there are some people in the crowd today. I was wondering who would show up at a cost modeling meeting. So thank you for coming. Hopefully you'll be here and through the end of the session tomorrow. I'm going to be covering a lot of material. If you've ever been to one of my presentations, my slides and my text are small. I have a lot of material to go through. I speak quickly, but I'm just trying to get out to you the kind of an understanding of kind of the issues surrounding this. I'm going to start with somewhat of a history of USF, the models, go through what CQBAT is, which is the model that we developed, compare that CQBAT to the FCC's current platform, which is the synthesis model, so you get an understanding of the differences between the two platforms. And then go into the meat, the real guts of the model so that you get an understanding of how it works, what it can do and what it cannot do. And as I go through this, as Steve said, if there are questions, please stop me and I'll try and address those as we go through. So this first session, I'm just going to go through a USF primer, overview what CQBAT is, and then once we have that overview of CQBAT, then come back and compare it to the USF models that are out there. The second session will go over an overview of the economic underpinnings of the model, so understand what really drives the development of universal service cost. From that, we can then talk about the CQBAT platform, talk about its structure, the development of the data that goes into it, the inputs, how those interact. In session 3, we'll go through middle mile. And then start on the telecom plant, so the loop network, which is really the high-cost portion of what we're looking at. With that, then I'll hand it over to the ACS presentation so that they can discuss their model. I'll come back up and talk about, again, the network, because it's a fairly detailed discussion of how the network works and how we build the network. And then tomorrow we'll go over the OpEx and how that OpEx was developed for the model so that you get an understanding of the data that was used and the process that was used to develop that OpEx. We'll finish up that discussion with kind of a review of what is online for people that have signed the second supplemental protective order to get access to the model. And then finally, as you're running for the doors, we'll talk about the current results that are coming out, show you some pretty maps, pretty bar charts, and then talk about if this platform or any platform is adopted, what are some of the key issues and some of the key data sources that need to be considered for those types of platforms going forward. So just a real quick background of who we are. CostQuest is a company that was formed in 1999 by myself and my partner Mark Gutman, who is sitting up here with me. We have worked in universal service models for 16 or 17 years now. We're still around. I was involved in the original BCPM, which was one of the models filed at the FCC for the original universal service efforts. That model was not adopted, but portions of it were the basis of some of the logic that made it into the final platform. We've also done broadband models or universal service models in Australia, New Zealand, Hong Kong, California, Texas, to name a few, and we're actually working in a couple states right now working on universal service models. So we have a fairly good sense of what universal service is and how to develop the cost of that based upon forward-looking techniques. We also wrote the FCC's broadband model for the National Broadband Plan, which was kind of the baseline from which we looked at to develop the CQBAT. It's pretty much the same concept, which was in the National Broadband Plan, what is the cost to deploy broadband throughout the country so that the FCC could put that National Broadband Plan together. Same basic concepts here. We just updated inputs into it, rewrote the logic to address some issues that we knew existed, and have come up with the CQBAT that we're going to talk about today. So I'm going to jump to the end because it's always good to understand where we're going to go with this presentation and what we're trying to understand. Basically, what we're trying to identify with a universal service cost model is the high cost portions across the country. So as you look at this map, what you see here is this was an early version of CQBAT output in which we set a benchmark of $80. That $80 was a point at which we said if you're above that, potentially it's a high-cost area that is in potential need of funding because the economics of that area may not play out going forward. As you look at this, we then thematically color-coded the cost profile so that as you look at the map, a light green is a lower cost, but still high cost because it's over $80, going up to a cost well above $1,000. There are costs when we run these models. I've seen loops that cost almost, I want to say, in excess of $1 million. And that's because, and you might guess where they might be, and I won't point to the table where they might be, but they are in remote areas where you have a lot of dedicated plant to single customers. And those routes to get out to those customers are fairly long, and there's no ability to share the plant. So you'll get very high cost areas. And that's part of the effort in CQBAT, and what's been put forth is there a cap that needs to be considered when you're looking at this? The next part of the goal was, well, let's give the model additional flexibility so that you can put on additional filters. So you may say in the final policy that we do not want to fund areas with competition. So what you see here is where the cable companies provide broadband service, and this was based upon I think release 2 of the broadband map. And the concept here is if there's competition there is no funding. So we overlay that. So anything that bleeds through the black layer of cable coverage then becomes what is considered for universal service coverage. And anything that is not cream colored, which is under $80, then becomes those areas that typically, potentially may need funding. So this is where we're going to build to, and I'll bring these slides back up at the end of the presentation. So when you see these slides again, you know we're almost done. For those in the audience who are relatively new to the telecom industry, I threw a couple slides up here just to give you a brief background of what we're talking about here. So the telco network is made up of primarily 2 parts. The first part is the local loop network. The local loop network is you, as a residential customer, pick up your phone if you have phone service. That phone is then connected by wires to a central node. We used to call them central offices where a switch was located, but in today's network, many times there is not a switch there anymore. It's just it's an aggregation point or a node in the network at which all the customers in your area home in on that point. So as we look at that, we have then the network. So you have your little house up there routes back to typically where that switch center is. That switch center then is connected to other switches, to other tandems, and to the world. That connection from the switch back to the world is typically what we call transport, interoffice, backhaul, many names for it. It's a combination of to get your traffic out to the world from your central node, we need a network to get out. So those are the 2 main components of the network that we look at. And as we develop CQBAT, we have a loop component of the network, and we have the other term I didn't mention, middle mile portion of the network, which is that inter-office backhaul conglomeration that we have pictured up there. As you get into the local loop, which is typically where the high cost differentiation is made, there are some high costs driven by the inter-office transport, but a good chunk is driven by the high cost of the loop network. So when you're in the loop network, if you start out at the customers, which if you're looking at the screen up here, you got a collection of customers out here. At the customer, you'll have a NID, which is the network demarcation point between telecom-owned plant and customer-owned plant. From that NID, you have drop. Drop connects you up to then the distribution plant. The distribution plant, typically in today's network for most providers, is copper. That copper then runs back to another aggregation point. That aggregation point, typically in the old-time networks, was a digital loop carrier system that combined, muxed or multiplexed up all the traffic from multiple customers onto a single stream and sent it back to the central office. And that transmission back to the central office, as you see up here, this is what we're talking about here. And as you can tell, I had a lot of coffee this morning. But then that goes back to the central office switch. So as we deploy CQBAT, this is the network we're trying to replicate. The technology that goes in the network is a choice of the modeler or the choice of the user to determine if we're doing a full fiber to the prem, are we doing fiber to a DSLAM and then copper out to the customer. And there's ultimately other technologies that could be used, but those are the two primary that we look at. So when we talk about universal service models, the first thing we have to think about is what are some of the policy decisions? I'm not going to talk about policy. It's just these have to be considered as you construct the model so that you can support the ability for policymakers to investigate these as they try and understand the cost of the network as they try and implement policy. So what technologies will the model assume? Will we support broadband? And at what speeds is broadband supported? And as many of you in the room know, there are some issues around the speed that is supposed to be supported, and what cost does that drive? Is the network a TDM network or an IP network? And for those not familiar with telecom, TDM is typically your voice circuit-based switched approach. It's time division multiplexing, if I remember right. And then you have IP, which is your internet protocol type network. So it's a data network in which your voice, if you're using voice, travels over as packets rather than as a circuit switch approach. We want to understand, is the network fiber to the prem or fiber to the DSLAM? And we'll talk about what these look like in later slides. Another key question is what percentage of the customers purchase the service? So it's the take rate. Back when the FCC developed the synthesis model, there was really no discussion about take rate because 95% of the population had phone service. If we look at it today, in many areas, it may be 20, 30, 40% of the population in a wire center takes phone service. So that contributes to the cost of a per subscriber end result. So then the question becomes, well, what's the divisor in coming up with the per unit cost? Is it the number of customers who take service? Is it the number of housing units? Is it the number of households, the number of locations? Whatever that may be is, again, another policy decision. Do we include polar cost? Polar cost are provider of last resort. In some states, it's called carrier of last resort. When we think about that, what it requires is the phone companies typically have to have facilities ready to serve in a number of specified days, hours, whatever it may be, dictated by the state commissions. That typically means that if a company has a 30% take rate, they have 30% of the customers in a market taking their service, the provider of last resort means I have to have facilities ready to serve each and every one of those customers. So it's not like we can shrink the network down to the customer base. We still have to have that full network out there if we're including the polar option as part of this costing exercise. We then talk about what are the geographic units of consideration. And you go, well, what does that mean? And it really comes down to averaging. We can develop cost alleys models all the way down to a customer. And we actually did that in Hong Kong. We had to come up with the cost of universal service at a customer level. If you look at the FCC's model, they looked at the average cost across the state. And it was really, is this state a high-cost state? If so, that state requires funding, and then the funds were distributed within the state based upon wire center average cost. That averaging has a fairly big impact on the total size of the fund because what the averaging does is it allows cross-subsidization within the average bucket for some customers who are low cost to cover those customers that are high cost. And then the final one, and it's really not the final one, but the final one I'll talk about is what is in the study and what is outside the study. And that really gets to the concept of where does the network start? Where does the network end? Do I go up for a broadband network? Do I include peering? Do I include the cloud? Or does it stop at some point? When I get to the customer's residence, what is included in that customer's residence? Do I need to put in a set-top box? Are we talking about video? Do I need to put in a modem because we're talking about data service? Do I need to put in a residential gateway if we're doing a CVoIP, a carrier-grade VoIP architecture? So you have to understand what's in the network, what's outside the network as we develop the cost of that network. So as we think about the FCC's model, as many of you are aware, and actually I see a lot of faces from days of yore, when the FCC developed the HCPM, or the synthesis model, it's been over 14 years, actually maybe 15 or 16. It's a long time ago. It's eons ago. But since its development and deployment, it really hasn't been updated. The platform has not been updated. Some of the data was updated. The last update, as I recall, was in 2003 when some line counts were updated in the model. But since then, the model has remained as is going forward. It was, at the time, a modern tool for calculating the cost, the telecommunication cost, for the purposes of supporting universal service. However, since 96, 97 time frame, things have changed dramatically. As I said, competition has come into the marketplace. How does competition impact the costs that need to be developed? Technologies have changed. Back when the model was developed, and I have it on the later slide, but I'll hit here, is when we talked about the network needing to support advanced services. The advanced services at that point in time was a 28.8 modem speed service. So we had to make sure that the network that was deployed could support a modem in your house to provide 28.8 speed service. Things have changed since then. If we look at the FiOS network can support well in excess of 100 megabits. If you look at the cable network, DOCSIS 3, cable speeds well in excess of 100 megabits of speed. So we've advanced from that 28.8 modem. If those of you are still around who use those, you're really grateful that we've advanced since those modems. So with the new technology and methodology, we're really poised, or at the point in time that we've got to re-look at how we develop universal service costs so that we look at what is being done today. It needs to be a forward-looking network to capture the cost as a provider would be impacted by the development or deployment of that network. I'm not going to read all this, and I'm sure you're grateful I'm not going to read all this, but I call these the golden rules. Or I used to call them the golden rules. I used to live by these. They were out of the docket, the Universal Service docket, and I think they were the first report in order. I don't know if anybody knows. Thank you. First report in order on universal service. And in that, in paragraph 250, the FCC laid down the criteria for the forward-looking economic cost determination for universal service. So part of this actually drove the development of universal service cost models, and it is still kind of in the basis of what we do when we look at developing universal service cost models. And if you look at just some of these, the first one, the technology assumed in a cost study or model must be the least cost, most efficient, and reasonable technology providing supported services that are currently being deployed. So it gives you a means to determine what technologies to include. The loop design incorporated into a forward-looking economic cost study should not impede the provision of advanced services. The question is, what is meant by advanced services here? Any network function or element must have an associated cost, out of point 2. Item 3, only long-run forward-looking economic costs may be included, and the cost must not be the embedded cost of the facilities, functions, or elements. Again, key criteria as we look at the model. We know it has to be forward-looking. We know it has to include all components of the network as we go through this. 4, an interesting point, and I'm not sure this is still true, but the rate of return is at 11.25%, which is the FCC's prescribed rate of return. 5, the economic life should fall within the prescribed FCC authorized range, and we still try and do that. 6, the cost of providing service for all businesses and households must be captured. And what that gets to is you want to make sure the network you develop is a network that is realistic to serve the customers that the companies have to serve today. You don't want to build a residential-only network because it's not really what will be built. 7, we have to include a reasonable allocation of joint and common costs. And this really gets to the whole TELRIC concept of pricing and costing, which is total element long-run incremental cost, in which you spread out the shared and common costs so that everybody gets an increment of that. 8, all underlying data should be verifiable, engineering assumptions reasonable, and outputs plausible. And I'll attest to that today, that our outputs are plausible and reasonable. So I'll just say that. 9, the cost study or model must include the capability to examine and modify critical assumptions and engineering principles. And 10, but not least, the cost study or model must de-average support. And at the point in time that the FCC released this, there was the concept of actually going down to census block level. Part of what happened is there's the thing that I mentioned, as you push the averaging down, it tends to blow up the funding requirements. When we did the original BCPM, which was being filed at the same point in time, going down to census blocks actually increased dramatically. It could have, day one, I think it was a $20 billion fund was required if you went to census blocks. Politically kind of unacceptable, so then you start looking at, well, do you want to determine funding at the census block level, or do you start to roll up? And in the end, it was determined it was at the state level, and that state level is then what is the basis for what we have today in the FCC's model.
Okay.
Yes?
Why do you think that the census block level average would go up?
What happens is when you go to consider there's two customers, say we got two customers, me and Mark. My service is cost $80, Mark's service costs $10. As you start to average, the average of our cost is $45. I may have been considered high cost in the required funding. Mark did not. When we are averaged together, we are both now not in receipt of funding. So as you push down to individual customers, the fund goes up. As you start to average, it just starts to tend to drag down. It's just the law of averaging everything. The average brings you potentially down below the benchmark. Some in the audience.
You can turn and face the screen.
Oh, thank you.
Just put it in your pocket.
Some in the audience and some of those in the proceeding may question the need for a forward-looking economic cost, which we call FLEC, cute acronym. But what are the benefits of a FLEC model? As we understand, the FCC's golden rule said forward-looking. When economists look at cost, it is really the forward view that determines what costs are. When you do valuations of property, it's what is that value going forward. We don't care about the history. So as we look at FLEX, one is it provides a clarification of concepts of the least cost provider so that we can look at, when we're talking about the distribution of public funds, we want to treat people fairly. We want to make and encourage the deployment of efficient networks, so that allows that. It normalizes participants so that we can look across everybody in a fair manner. The metrics and analytics to examine issues such as targeting reserve levels for auctions, service definitional changes, all can be done within models. I can't look at the network today and say, let's look at the fiber to the prem cost, because it doesn't exist. But in my imaginary world, in which I live, in models, I can pull a lever on a model and say, let's deploy fiber to the prem to everybody. I can quickly get that out. And quickly is, again, in my view of quickly, it may not be your view of quickly, but I can get that out to understand the concepts and the price of that network that is being deployed. It helps avoid the asymmetric embedded cost mechanisms, and I really don't want to get into that. I probably should have taken off the slide, but there are issues with embedded cost approaches, and forward-looking cost helps work around that. It is typically less onerous for policymakers and the stakeholders. As we've seen in the recent public notice where we talked about a brownfield network. The brownfield network requires a lot of information to understand that brownfield network. If I want to look at the deployment of a network, I want to know where all your nodes are in your network. So all the carriers would have to provide a list of geocoded locations of all their nodes. I also want to know which cables are 24 gauge, which are 26 gauge. I now need that database. I need your operational cost. ARMIS used to be a wonderful source of operational cost detail. Detail, again, in the eye of the beholder. But when you look at ARMIS now, it's no longer pertinent because it's not maintained at the level it used to be. So there are reasons that forward-looking economic cost help everyone because it just simplifies the exercise. And there's a clear link between the defined service and the cost of the network that is designed. So now let me kind of go into what is a universal service model. You might think it's basic, and if you've been through some of my presentations, this is old hat, but basically every universal service model is made up of actually two models. There's the cost model and then the support model. The cost model is a systemized collection of mathematical procedures that takes as inputs geographic and non-geographic data and produces an estimate of the cost. So this is the fact, and some of you may argue that it's a fact, but the cost is what it is. I may change the price of a DSLAM and get different costs, but it's not kind of a subjective art. It is, I need to run a network. What is the cost to run the network? I unitize it, but what do I unitize it to? All those decisions are made, but I get to a cost. And when you think about this cost model, as I defined it here, does not necessarily mean forward-looking. If you look at the current universal service system, the non-rural carriers are under an embedded cost architecture, but again, it's a cost model. If you look at the NECA model, it's a cost model, and it's a systematic formula. A meat grinder, you put all this stuff in, you grind that formula through, and now comes the cost per subscriber, which is then what is used for funding. On the flip side, you then have the support model, which is again, yes?
Question. I'm an economist in PPP. Can you elaborate a little bit on what you mean by a systematized collection of mathematical procedure? Are you looking at this like a carrier cost minimization problem?
Well, it depends. There's multiple ways to go about it. What we will present here over the next 2 days is more of an empirical basis of actually running a real network. There are other methods that you can use. Which is if you look at the FCC's current approach to funding on the rural side, it is a regression model. So there's multiple ways to go about it. I don't have a definition of which way, but the one I will go through is more of an empirical-based minimization of a network that needs to be deployed. And hopefully you'll get a better understanding as I go through.
But do you have a theoretical model on which the regressions are based on?
Ours is not a regression based. Ours is actually a network, and you'll see that as we go through. So if I don't answer your question by early morning tomorrow, and if you're still here, ask me again. Yes.
When you say cost, are you referring to capital expenditures or you operating?
It is both. When I talk cost model, it is typically what we refer to as kind of the monthly. The end results of the meat grinders are a monthly cost per subscriber, which includes a portion of the capitalized cost. So we've got a network that's being deployed. That network has associated with carrying costs. So you got depreciation, you've got a right or a need to provide income to the equity providers. You need to provide payment back to the debt providers, and you need to cover income taxes associated with that. So all those kind of get bundled into what I call cost. So then the support model is, again, a mathematical procedure that takes cost as an input, but it also takes into account other factors. Those other factors become subjective. Again, what is the level of averaging? Who gets to play in my playground and who does not get to play? What type of network are we going to run? What is the benchmark that we use? Or is it in ARPU? Is there a cap on this fund? There's all kinds of issues around the support, but it all is based around a cost coming out and looking at that cost. So when you talk about cost modeling issues, you've got to make the decision, is it forward-looking, is it embedded cost, or could it be a regression model? What is the modeling object? And modeling object is basically what am I looking to model? Is it a broadband network? Is it a voice-only network? We're actually in some universal service proceedings right now where we are deploying a voice network for universal service. It's the cost object. It is the object that we're trying to model. Here, the exercise is it's a broadband pipe to every home in the U.S. So again, you have to understand what that is. And what's the technology choice? As we've seen in the public notices, there's some disagreement about what the technology choice should be. Is it fiber to the prem? Is it fiber to a DSLAM and copper to the prem? And there's a multitude of choices that can be looked at. What's the source of the input data? For many of you who have been involved in this, the key driver of this is getting good quality input data. And in some areas it may fall apart because you just can't get good data. So we need to understand what that data is. The next one, accuracy of results. And part of it is, how accurate do you want me to be? If you've got a year, I can get you really good numbers. If you've got a month, I can get you so-so numbers. If you give me 4 months, I can get you, I think, reasonable numbers that can make informed decisions. Do we reflect an efficient carrier? You would think that this is a no-brainer, but it's one of those things that you've got to consider is, I can't necessarily look at the operations of any specific company. I'm looking at the operations of an efficient carrier. On the support modeling side, we've got to talk about who are the participants. How do I average those costs? What are there benchmarks for support eligibility? What is that benchmark based upon? If you look at the FCC's current model, it's a cost-based benchmark. I think it's it used to be 2 standard deviations above on the high cost side. You see nods. So it's 2 standard deviations. So if your average cost was above 2 standard deviations above the national average, that was considered a high cost area. If you look at what the coalition filed, they defined high cost as anything above $80. Different concept, but they may be grounded in the same thing. The last one that I'll hit here is just how do we apportion the state versus the federal part of that universal service. If you look at the current FCC model, they cover 76%, if I remember right, with the high cost model. The other 24% was somewhat the responsibility of the states or came back through in other mechanisms. So we have to understand that if we're developing what is the federal universal service cost model. On the cost side, let me just hit the real quick basics. It's a tutorial on one slide of how you do cost models. Yes, question in the back.
I'm happy to save these for the end. But just looking back at the point you made about the importance of the forward-looking cost model, you made a few comments about how it was necessary to exclude from that embedded or existing costs. And you sort of maybe combine that together with some comments about the greenfield approach. Could you maybe clarify how you think about forward-looking costs?
Yeah.
And why it's necessary to include, as you say, embedded costs?
Well, I would say embedded costs form a basis to understand what the forward-looking costs are. So on your operational cost side, the best source for operational costs going forward are what the operational costs that carriers are incurring today. That gives me a basis to understand how much does it cost to maintain copper? How much does it cost to maintain fiber going forward? Where it falls apart potentially is if I'm looking at a policy decision to deploy fiber to the prem. Not everybody has deployed fiber to the prem, so I can't look at the embedded books to understand the cost of fiber to the prem for that particular area because it's not being deployed. And I want that efficient provider, so I want to get operational costs that I think are reflective of an efficient provider going into that area. So that's somewhat on the operational side. Now I look at the capital side. Again, if I'm looking at a fiber to the prem deployment, costs to me are the decisions I make today going forward. So if I decide to deploy a fiber to the prem network, I look at what the costs are going forward. I don't look at what was incurred in the past because that's not really the value. If I built a house, 10 years ago, the value of that house today is not the same as what I built in the past. That's history. I'm looking at what it costs to build that house today. So when you pay your property taxes, it's the valuation of the construction of that house today or what people around you are paying. It's the same kind of basic concept here as I'm building that network going forward today. I want to understand what that cost and value of that network going forward are to understand that.
If we can hold off on questions for now, just because it's hard for people not in the room. We do have a microphone for questions, but I don't want to start passing it around in the middle of the presentation. So particularly if you have conceptual questions, if we can hold those to the end, I think a lot of the questions Jim is going to address, having had a whole 12 hours to look through the slides. I think a lot of the questions people are asking are good ones and fair ones, but the Jim has material to address them, I think, pretty quickly.
So hopefully I'll get to some of that as we go through. So from a cost model perspective, what is a cost model typically used in universal service? Well, cost, as the question was asked earlier, is you have to understand the investment, because a telecom network includes a lot of investment-related cost. Their fixed cost to deploy the service to your home. You take that investment, you multiply it by an annual charge factor. The annual charge factor includes cost of depreciation, cost of money, and taxes associated with that investment, so that you can understand. It's much like a car loan. Much like a car loan. In that car loan, you go to the bank and you have to pay back principal and interest on a monthly basis. Think of it the same way on a network. The carrier went out and borrowed money to build that network. They had to pay back principal and interest. It's a similar concept to what we're talking about here. To that, you had to add in the direct OPEX, or the direct operational costs associated with that network, which could include maintenance of the fiber, maintenance of the network. It could include customer support, because those broadband customers require support. You have to provide that. There is a direct cost associated with that. And then there are the shared and common costs, the general administrative, the carpool, whatever it may be, are included. When we look at the components of the cost, on the investment side, we're looking at loop, switching, and interoffice. And as I looked at this last night, I thought maybe that switching one is kind of I should have put quotes around it. Switching is a very touchy subject, because many carriers in the room offer circuit-based switching on their equipment. They're 5Es that have been deployed. They're DMS 100s. They're still working. They'll be working for the next 100 years. There's no reason to remove those currently, so they're still there. But when I think about a forward-looking network and what the value of those switches are, forward-looking network to me is a carrier-grade voice over internet protocol, CVoIP. So when I look to value switching, I use a CVoIP approach. Some may disagree with me, but that's how I view what the value of that switching component is, which gets to that forward-looking valuation of the assets that are provided. I'm going to focus mostly on the loop today as we go through this. I'll come back to annual charge factors and then the OPEX models, which gets to our operations as we go through. I've hit on some of these questions before, but it's as we develop these cost models, we have to go through these questions, and I've hit on what is the technologies we'll use. Should we recognize any facts about the carrier network? You'll hear over the next day and a half, Scorch Node. We usually use a Scorch Node approach on deploying of networks as we look forward on cost. Scorch Node simply means I'm going to maintain the location of the central office, so that central aggregation point. And I'm going to assume my customers are all home to the same central node. So as we go through, you'll see one of the issues, and the FCC issued a public notice on this, is we need wire center boundaries. Those wire center boundaries typically define how the customers route back to their switches, and the wire center boundaries have within them a central office or a central node. That is the extent of the network. The rest of it was destroyed through a neutron bomb that was dropped. There's no longer any copper, no longer any fiber, no longer any electronics. We are now about to enter into the new world of deploying a new network to those customers. What asset lives and depreciation and cost of money should be used? Where facilities are shared. So if you look at telephone poles or electric poles, there are many providers on those poles. There's cable providers, there are electric providers, there are phone providers. How do we capture that sharing of assets amongst alternative providers in the cost of the network? We certainly don't want to include 100% of poles if those poles are shared, but we also want to recognize that some sharing is not sharing of the asset value, it's actually a contribution of revenue. Many cable providers actually provide a payment for the use of the pole, which is then included in the operational cost, versus electric companies, which typically have joint ownership agreements. So you've got to understand kind of the nuances of the telecom network to make sure that you get the cost right. We've talked about the take rate, what percentage of customers will decline to purchase the service, and that continues to grow as I'm talking. And then the final one, what's the geographic unit of consideration? And I've hit that for the most part. On the support side, as we talk about models, I've hit most of these. We want to identify the participants of funding, the geographic basis, the services that are included, how we include the cap, what kind of caps are they, and then the state federal funding. This triangle we came up with, or a pyramid if I put it in 3 dimensions, gives you a view of this support model concept. So think of it as cost at the bottom are low, cost at the top are high. The width of the pyramid is the number of customers that fall within that cost profile. So most customers fall within the lower portion of the pyramid because they're lower in cost. You go up the pyramid, and there's a point at which you have your average revenue per user. And for carriers, they want to make sure the cost is below that average revenue per user if they want to stay in business. And it's a challenge with continuing customer loss to maintain that balance. As you go above the ARPU, it's kind of what we call the uneconomic dead zone. You really don't want to be there. And then you get into, well, now we've got to think about, if we're pushing universal service for the carriers, how do we help fund the areas that are uneconomic? In the ideal world, for the carriers, they'd like you to fund, the whole thing. In the ideal world of the public fund, they'd like to make this as small as possible. So there's a balance that has to take place. And we looked at it as 2 things. One is you can approach funding as one, everything. 2, I can go sanded ridge approach. It was just a name we came up with of consider all these high-cost customers out there. I've got limited funds. I'm going to sand the ridges down. I'm just going to push the funding down to cover as many of the high-cost customers as I can until I run out of money. So what you see here is I'm moving down, and I run out of money here. So this is the portion of unfunded, uneconomic customers that the carriers have to absorb. The other approach is the Big Bang approach. I want to get as many customers served as possible with the limited funds I have, so I fund the lower cost customers who are high cost until the point in time I run out of funding. So there's 2 approaches to funding, one top down, one bottom up. And really what we want to get to today is the point in time when this sanded ridge comes down to the Big Bang line and the Big Bang comes up to this. So really the exercise here, when we set the cap, we set a cap at $80. We set an alternative technology cap down to this level. This then becomes the amount to fund, and those are the subscribers that funded. The tip of the pyramid are those lucky customers who we assume there's an alternative technology to support them, whatever that technology may be. But it's potentially unfair in the public funding arena to give a customer $1 million when you could support 1 million customers at $1 a piece. So you've got to make a break, and that pyramid really helps, for me, solidify this whole concept of funding. So now let me go into what is CQBAT. And I'm sure you're all sitting on the edge of your seat trying to determine what CQBAT is. Well, first, it stands for the CostQuest Broadband Analysis Tool. It's a snappy acronym, CQBAT. It is a scorched node model. As I've discussed, we assume there is no existing facilities out there. We build the network as one would build it today in an optimal manner. It is forward-looking, so we are not taking into account any of the embedded decisions about how plant was deployed in the past. It is as we would build it today. It's new network built to all locations, so it accounts for the polar obligation. So we have network passing all households. We may not have all households connected up with service, but we've got that network ready to serve. It uses contemporary real-world wireline system engineering standards to do that. So when we look at a DSLAM approach, so copper to the customer to a DSLAM, the DSLAM is what provides the broadband capability, fiber on the backside of the DSLAM back to the central office. We assume, and we've talked to engineers at various phone companies to understand how that is done, and we implement that logic in the model. When we look at how to do the costing exercise, We use capacity costing techniques, which I'll talk about later on today, to estimate the economic rational investment needed in that network, and that reflects the real-world implementation of networks today. So as we do that, the network is built out from the CO to those customers who are served by that central office. We assume the current service provider will continue to provide service to that area. So when we look at a wire center, there is a defined provider of that wire center. We're still assuming it's the same provider going forward. As we look at the cost of plant, so to buy a DSLAM, we have adjustments in the model to allow for purchasing power differentials between small and large companies. But what we assumed in the model that was filed was smaller companies had the opportunity to join purchasing agreement with other small companies so they could pool together or with their trade organizations to achieve some of the same price benefits that the bigger companies get. On the coverage side, so part of the effort of CQBAT was, as I showed you in the first couple slides, the map, we wanted to identify those areas that were currently not served by broadband, specifically cable. So when we looked at coverage for cable, wireless, and telco, we went based upon the SBDD, which is now SBI, which is the National Telecom Information National Broadband Map Database. So that's where we went for the source of where is broadband today. On the network, it is an IP-based network. So I talked about a circuit switch-based network or an IP-based network. This is an IP-based network, and we're focusing on the cost of the pipe. We're putting a fat pipe to everybody's house. That's what I'm concerned about on the modeling side. I want a fat pipe to everyone's house so that they have access to a broadband network at a speed specified by the user of the model. We did not include any video gear, so this is not a video deployed network. It could support video, but we have not placed the set-top boxes in the home. We have not put the video head ends in. We have not put in programming costs, any of those costs. We are simply talking about getting the pipe to the house, and then the services that ride on that pipe are incremental and should cover the cost associated with that. What we're concerned about is the differential in getting the pipe to the house. And again, in the same vein, we did not put the voice gateway in. Voice in a broadband architecture is a service that rides the pipe. Much like video, much like your data service, they're all packets that ride the pipe. So as you get the model and you look at the results, it should help answer some questions. I hope it does. You know, what new network facilities will it need to be to provide sustainable, affordable access? So we're trying to identify the high-cost areas. What will it cost to operate those networks? Because operational cost is a big component of this network that needs to be deployed, and you need to bring that in. Where is support required to encourage this and support build-outs of broadband? And then will the resulting business opportunities make sense for the carriers as they look at this fund, as they look at the providers, as they look at the customers they have to serve? It has to make economic sense for them as well. So let me hit some of the key assumptions. So when I sat with my clients when we designed the model, I sent them a list of questions. And I said, give me feedback on these questions. And for those who have cats, you know, herding cats is sometimes difficult. I won't say my clients were cats, but, you know, getting a consensus decision on some of these was, you know, it required some discussion. So first is, what is the take rate? What do we assume is the unitization of the cost? So we're going to deploy this network. We're going to assume a 90% take rate. So as we deploy the broadband network out there, 90% of the customers will take our service. We're going to take the full cost of that network, divide by the 90% of customers to come up with the unitized cost, and that's how we go forward. How do we define cost? And this is really, for those who have been in regulatory cost proceedings, understand steady state cost and this whole levelization. For those on the financial side, you look at this with cross eyes and go, I don't know what the heck you're doing. You can actually ask Steve Rosenberg, because he looked at me cross-eyed when we did these originally, and he said, I don't know what you're doing, this makes no sense. But the whole concept is we want to bring everything to a steady state and understand what the cost is as of today, which represents a long-term planning period that is all levelized, and I'll go through that later on. We wanted to keep it simple. And for those who have looked at the model and the code, it's anything but simple, but it is simple because it could be more complex. Just think of it that way. I'll stop there. We did want to size success-based capital, so line cards and modems. So when we deploy this network, even though it's still at 90%, when you deploy a DSLAM, do you deploy the DSLAM to serve 90% or 100%? Well, you want to make sure the DSLAM frame, which costs more to install and is kind of a fixed cost, is ample enough to support potentially growth downstream. But the line cards you can install at a later date. You still want to equip it sufficiently so you still don't have to go out and visit a cabinet. So what we did is on the success-based side, so line cards, drops, NIDs, potentially were all success-based, so based upon the take rate. The cost of money that we used was 9%. That was provided by the coalition as a number to use within the model. Should capital and operational cost inputs be varied by region? And the answer was yes. Well, let's try and capture those as best we can. And what we use, and I'll show it later on, is a regional cost adjustment table. It's based upon 3-digit zip code that captures the cost, the material cost difference and labor cost differences between parts of the country. What gauge of copper? 24 gauge. How should the cost be unitized? We chose to use by active customers. So that 90% take rate gives us what we divide. So you come up with the total cost, $10 billion. What do I divide 10 billion by? I take the 90% of customers who take my service to unitize that. There are other ways to unitize cost. How do we classify companies to size? Well, one is we want to allow the control of that. And you ask why is size a factor here? Well, size impacts the operational cost. It may not impact. We provide the capability on the capital side, but on the operational side, small companies may not have the efficiency because of their scope of services and scale. So you want to factor that in. So we classify each company into a size category. How should we determine the plant mix? Plant mix has a big sway in the costs that come out of this, so buried, underground, and aerial. We ask the companies, the coalition members, to provide to us state by state the plant mix that they see, because on a forward-looking basis, we estimate or we think it'll be much the same. If you got poles there today, you're going to use those poles. If you got underground, you're probably going to use that conduit. So we don't typically adjust the plant mix on a forward-looking basis. So we want to try and get as best understanding as we can. And I'll show you that plant mix later on. Do we equip all households or only active customers with drop? Well, we ran, if I remember right, only to the working locations. I already hit on the next one on the CapEx cost for purchasing power. We have the ability in the model. We just chose to set the purchasing power for everyone at the same rate. When we size or look at the facilities coming back from these electronics, we have to understand the total bandwidth. And for that, we looked at the National Broadband Plan and some internal documents provided by the providers to come up with what we estimate the broadband demand to be on a busy hour basis. When we look at services, and specifically businesses, we want to make sure we capture what the services businesses require in the development of our network. Many businesses have dedicated fiber to their buildings because they have an OC1 in the building. We want to make sure we capture that in the cost model and the network design so that we get a proper network built. And I'll show you that service creation basis. We'll go through the copper and fiber design rules later on. What lives should be used? We chose to stay with the values that were used in the BAM model, which was our model used for the National Broadband Plan. And they are lives that fall within the FCC prescribed numbers. And where do we stop? And some of you may be saying maybe right now, but it comes down to what's in and what's outside the network. We stopped at the demarcation, from the customer demarcation point to the router that sits on the edge of the cloud. That was the cost that we came up with. So here's a picture of the kind of flow of the model. I'm not going to go through it. You'll see this again, a bigger one, a more detailed one. And for any IT people in here, you might, I threw these up. Hopefully I used the right shapes and all that. So we'll come back to this later on.
Quick note, Jim.
Yes.
So we're approaching towards the end of the first session, so just to let you know that. Also, the last slide was the first of several that are upcoming that have relatively small fonts. So there are some more printed copies on the back table, I've been told. I don't think you need to run and grab those right now, but at the next break, if you don't have a printed copy, you may want to pick one up. Thank you.
Yeah, I'm kind of known for small fonts. It's a detriment, but I've just got so much information I want to get to that I cram as much on a slide as possible. So let me give you a quick review. I've hit on some of this of the USF models that are out there, so it gives you understand what we're doing with CQBAT. Let me hit real quickly what was done in the USF models so that we can compare and contrast the approaches and see if one potentially has advanced over the others. So the FCC synthesis model was released and implemented in 1999. At that time, the BCPM and HAI, which previously was known in its former name of Hatfield, were reviewed as potential models. Both the BCPM and HAI were adopted in various states, so they are still around, I think, scratching and clawing to be used. The synthesis model contained a new loop model. One of the authors was in the room. I think he still is. Mr. Bill Sharkey is back there. He's the author of that, the model that came out on the loop side. It included the switching and transport from the HAI. And, since I wrote the BCPM, I always say it included flavors of the BCPM. There's a little spice sprinkled in there. The blending and testing were performed by the FCC staff. And in 2003, they updated and moved from Turbo Pascal to Delphi. The major inputs was customer locations, which came from PNR, provided a customer data set that could be used in the model. And I believe, if I recall right, some of that basis was actually 1990 census data. So we're in 2012, so we're 2 censuses removed from that data, but that model is still being used. So part of the reason we need to look at an update. On the line count, it includes switched, which is res and biz. It included special access, but the special access was kind of a spread on business lines. It included geographic data, soil, depth of bedrock, which current models include as well. And you bring in the soil and depth of bedrock, depth of water tables to understand construction costs. So when we dig a trench, we want to make sure that trenching cost is reflective of the cost incurred by the carrier. If you're going to dig in water, you may not want to dig in water. You might want to pull pole up. There's things that you need to know about the geographics of the area, and that was included in the FCC's model. It had cost tables to capture installation and equipment, and it had the ARMIS data for the operational cost. We no longer have ARMIS data. The service provided was from the established central office location. It was a scorched node model. It used twisted pair technology. The advanced service, as I talked about, was 28.8 modem speed service, and the length of the loop that the copper loop was set at 18 kilofeet. That 18 kilofeet was sufficient to provide that 28.8 service. The model could support DSL deployment, but it's not designed to, nor does it have all the electronics of DSL deployment. The customers were equally distributed along the roadways within the data source, and then some of the network assumptions are covered here. If you ran the HCPM at the point in time it came out, it was fun to watch it run because it was like a fireworks show. As the clusters were being formed, each of the colors would pop up, so you'd see these things being displayed. At the time, it was leading edge in how it created the clusters. So the clusters were formed based upon kind of a star design of looking at customers and their distance to a central node that did not follow the roads, and I'll talk about it in a minute. So this is the creation of the engineering areas. Once you identify the customers in an area on the far left, a grid was placed over top of that to identify then the distribution network design for that area. You had nice rectilinear routing of your distribution plan. You had nice assumptions about the distribution of customers off of pedestals or the drop terminal. This was then the distribution design. On the feeder side was again rectilinear It followed the 4 cardinal directions, north, south, east, and west, coming out of the central office. And then off of that, it had rectilinear runs out to where the clusters were. So if you looked at the cluster diagram on the first one and this, you could see where the central point of the clusters was. The distribution network was then, again, a rectilinear routing north, south, east, and west out of that central cluster point to reach the customers, and which gave you then the distribution network, and then everything was sized appropriately for the customers who were served off all components of that network. The synthesis model produced cost on a per line basis of providing universal service. It actually had additional capabilities. The results were subsequently rolled up to a statewide average, as I mentioned. And then the output provided expense detail for all the network components along with all the operational detail associated with that network. You could get density zone reports, so you could go below a wire center based upon density zones, but it really did not support developing cost below the wire center on universal service. Today, the synthesis models are still primarily used to support the cost model, and actually the synthesis model is worldwide. I actually worked with a carrier in New Zealand, or actually the government in New Zealand, who used the synthesis model as part of the basis for their universal system. It's been widely used in South America, so it's out there and being used. And it was used in some uni proceedings, which I will not go into. The BCPM, this at a point in time was my pride and joy. I'm not sure why, but actually another author is in the room with me. What we did here is this was before we had a good understanding of how we could grab roads, how we could cluster better. So we predefined clusters as grids. The grids were based upon 1/100th of a latitude and longitude, which equated to about the serving size of a carrier serving area. We then subdivide those grids down in high population areas to come up with smaller grids to try and reflect what was being done. I won't go much further into BCPM. The HAI, this is HAI cluster over there. From the cluster, they got the bounding polygon of the points that gave an area. From the area, you came up with a rectangle. From the rectangle, then you moved the customers inside the rectangle, and then you ran your nice washboard pattern of the distribution plan. And when I was on the other side, there were model wars if you weren't involved, but they were quite fun. But you always said, our network builds to the customers, their network moves the customers to the network. So, but we'll move beyond that because that was 15 years ago. So as you think about now and then, this is what was done back in the 90s. This is what we do today. We run a network that goes along the roads and mimics what an engineer would do, and that's what we'll be going through. So today's model have made major advancements in how we build these forward-looking networks. One is improved customer locations. The current model still uses census, but we can drop below that, and I'll talk about that tomorrow about how we can improve the customer locations. We do match engineering designs and constraints as they are deployed today. We have improved network routing, which I hope you understand as I go through this. We have the improved ability to vary the service delivered, so we can turn on broadband designs. We can turn on fiber to the prem. There are other network architectures we can turn on and off. In general, it's a more realistic, flexible network that reflects what a carrier would be building today. So as you saw, the nice cluster formation, and then from that cluster formation, we came up with the distribution pathing. In today's network, in our CQBAT network, what we do is we take the geocoded location of customers or the distribution of census points to the roads. From that roads, it then becomes an exercise of connect the dots. That's really what I do. So the first part of the connect the dots is we need to understand what that architecture is. If this is a DSLAM architecture where I'm going to run a DSLAM up to within 12,000 feet of the customer, some customers will be closer, but the farthest one will be 12,000 feet. I want to first come up with those engineering areas. So much like the HCPM's nice fireworks show, this goes through, and if you look up here, this is a cluster that is formed. So all customers in here are guaranteed to be within my user constraints of copper to the serving DSLAM.
along the pathing of the roads. If you look at the differential between what the FCC used was a minimum spanning tree. It was great at the point in time. We've taken it to the next step, which is minimum spanning road tree. And what that does is a minimum spanning tree uses rectilinear distances, doesn't take into account how you actually have to travel along roads, that you really can't go over that river, you can't go over that highway, you have to go around things, and that's what the minimum spanning road tree looks at, is it looks at how you actually have to route along the road paths to get to this. And what this shows is a differential between a potential cluster that is formed when you take into account the road pathing that takes place versus doing an unconstrained minimum spanning tree. When we get into the distribution and feeder design, now we're routing to those customers. As we saw earlier, this is the nice rectilinear cardinal pathing approach to that design. This is what would have happened in that same area if it were run using a minimum spanning or the road pathing to get to those points. This is in my nice pictorial. You'll see this wire center. If you've ever been to my presentations, you probably go, can't you get some new pictures? But you'll see this a lot as we go through. But the central office is down here. The blue is the feeder cabling that goes along the roads to reach those customers. The kind of the mustard color up here is then the distribution, or the copper, that goes out to serve those customers, again, along the road paths. If we compare it to some of the other approaches, this is what CQ BAT does to route the customers in an area. This is if you use the minimum spanning tree, so you're not looking at roads. And that's one of the benefits of looking at roads, is you can realistically capture the distance that's needed to connect those customers together. And then if you looked at the HAI, they overlaid a nice washboard, so you can see the differentials between the approaches. And we think this is a much better approach, and this is what we use today. Now let's look at the synthesis model broadband network design. That's it. There is none, because at the point in time it was released, we were talking about 28.8 modem service, and I'm hoping most people in here say that's not broadband. I think by FCC definitional terms it is not broadband. This is what we look at today. So we're looking at, here is the historical approach to network design. You had copper feeder cable coming out to a feeder distribution interface or a cross box, the copper distribution coming out to the NID, which provided the service to the customer. And this was for customers within about 12 to 18,000 feet of the central office. For those beyond that, you put a carrier system out there. The carrier system was fed by fiber. And again, this provided voice capability. In today's network, I'll cover both of these, but we can do a fiber out to a DSLAM, which provides broadband and voice, or fiber all the way out to the customer, and I'll talk about this. But really what's driving that need to go beyond 28.8 modem service is just the bandwidth that consumers want. The additional benefit that the models today have is the granularity to go below the wire center in cost. So this is that cost of that wire center I've showed you. Yellow is low cost around the central office. You have high density, the loops are shorter, therefore lower cost for those customers. As I move out, higher cost census blocks. These are actually census blocks. The blue dots here are then the DSLAM locations to serve that network. This is a low-cost area away from the central office, but it's because it's a high-density area. But that's what these models provide to us today, is the ability to look at cost well below the wire center and actually down to the customer location. I'm not going to go through this. But this was filed in an ex parte by me. I think Mark may have a few copies of this sitting around. But this was where I was trying to compare and contrast the differences between the synthesis model and what we're doing in CQ BAT today. And then I think the final slide before the break is issues with the FCC's synthesis model brought up by the Rural Task Force. So at the point in time, the model was released in 1996, 97, 98, 99, 99. The intent was the model was going to be used for both rural and non-rural carriers. The non-rurals which are your bigger companies. It was implemented and taken forward. Then the rural companies were given kind of a breather and said, within 5 years, we need to implement this. The Rural Task Force reviewed it and kind of came out and said, the modeled lines are different from our actual lines. You can't use the model. The modeled route miles varied significantly from actual route miles. Can't use the model. The modeled plant installed did not line up with our actuals. Can't use it. The wire center areas and boundaries did not match up to what our wire center boundaries are, so you can't use it. The model underestimated switching investment. The modeled general support investment varied significantly compared to actual cost. The model underestimated network operational cost. And the use of statewide average cost was just simply inappropriate. To average my operational area, I'm a small player. Why should I be averaged with someone else? Because I can't cross-subsidize my footprint with my friend's network because he's just not going to give me money. So with all these, the Rural Task Force said you just can't use the FCC synthesis model. But as you look at this, as we look at it today, these are primarily data issues. They are not a modeling issue. From my standpoint with CQBAT, where we can route efficiently along the roads and replicate what a carrier has to deploy, these now become data issues, so they fall away. And with that, I open it up to questions and answers. Or I open it up to questions. I'm not sure I have answers.
So we have a mic. So if you have a question, please raise your hand, and we'll bring the mic around to you so everybody in the room and online can hear it.
Hi. So thank you for the presentation so far. That looks very interesting, and it's very impressive how you do engineering part of it. I'm trying to translate into economic terms what you're giving me, and it looks to me like maybe you're giving me a long-run average cost per customer. Is that fair to say? That's what the model churns out in the end?
Average cost per unit, and that unit right now is a customer, yes.
Okay. And the final product, would it be easy for us to vary things like the types of technology that are assumed in the model? Is this something that is easy to do, or is this something that's embedded in there? Like, for example, could I choose to look at long-run average cost with just copper and then with just fiber? Or is this something that you can't change easily?
The technology that we have available in the model right now are a fiber to the prem design and a copper design that takes you within 12K. We can vary the copper length off of the DSLAM to under 12K or above 12K. Those aren't currently available, but they can be made available. But it's the design. There are a couple choices on design, but they are limited. And
how about the rate of return that is assumed? Is this? Can we look at what happens when you vary it?
Yes. Yes, and I'll get to some of that. So when I go through the user tables, I'll go through each one of those, but there's an annual charge factor table that is based upon a rate of return that is assumed, along with the depreciation rates that impact that rate of return per asset category.
And is this something that you could change on a let's say, a regional basis? Can you assume different rates of return for different areas, or are you assuming a universal one?
It's a universal one, so you'd have to make multiple runs and then combine the runs together to get to that. But right now, it's just a single input for cost of money.
All right. That's all. Thank you.
Thank you.
Jim, in the support model section where you've got the benchmark and the alternative technology cutoff, and I don't mean to sound pejorative, is there any science to how y'all came up with those numbers?
The benchmark was provided by the carriers, and I'd be talking in third person if I tried to defend in the development, but it was tried to mimic the two standard deviation concept of the prior models. So from the benchmark, the alternative technology cap is then a determined number. If you've got when the original model was filed, it was a $2.2 billion fund for the price cap companies, or the companies that we looked at. So what you're trying to do is you're moving that, if you think of the
Back to the
triangle, you're just
pyramid.
moving it down until I run out of $2.2 billion, and that's set that number, which was, if I remember right, 200 and, Mike knows, 260, 256, thank you, $256.
Okay, thanks, Jim.
You're welcome.
Quick request, probably have people identify themselves, they ask questions, just so we know who's out there.
Hi, Jim. I'm Peter Blum. I just wanted to go back to your slide about state and federal responsibilities. I really like the way you presented that making an assumption about what the states are going to do is really a key issue for designing a support mechanism. And I wanted to ask you to reflect a little bit on what that 76% number actually means. The way I understood it was that the 76% that's in the existing cost model support mechanism reflects a decision that about 24% of cost of service is already allocated to the interstate jurisdiction. And the 76% then is the state side, and the averaging assumes that the state is doing something in the way of universal service within its borders, and therefore state averaging allows you to look at the states that can't really do enough for themselves. Does that make sense to you?
Yeah, and that's as I understand the way it was set up, was the states were supposed to implement systems underneath to help fund carriers within their state. The federal portion was then to help push down the high-cost states to a level that they would all be kind of on an equal basis.
Thanks.
Yeah.
Hi, Mike Romano from NTCA. Just one quick question about the benchmark, following up on the question I had before. Am I thinking this right when I conceive it as the benchmark and the averaging within the support model? It was very helpful thinking about cost model versus support model. The benchmark and the averaging interplay with one another. If one were to average more, de-average less, the benchmark may need to be higher or lower to work within the size of the fund. Is that?
Yeah, it is correct.
Okay.
That benchmark is not anywhere near what a carrier needs from a revenue perspective to be made whole.
Mm-hmm.
It's just the point at which we determine what is a high-cost area, and as you change the average, the definition of what is a high-cost area will change, and that benchmark will move up and down.
So, and then one quick follow-up question. What does the support model for CQ BAT right now assume as far as the averaging for distribution of support?
It is at census block level.
Census block. Okay, thanks.
Eric Rolfe, FCC. I didn't quite understand. You said that you model only drops to working locations. Is that the 90% of locations?
Yes.
How do you decide which locations are working locations? I mean, given that within even a census block you could have very dramatic differences in cost.
It's a good question. In the design of the network, we run pedestals. Pedestals are the little green mushroom that sit outside your house if you're in a subdivision. We make sure pedestals are located to serve all households. The drop typically is anywhere from 50 to 150 feet off of that pedestal. So we used an averaging approach. So we assume, in the model, we calculate the drop of 100%. And then we take 90% of that cost to say only 90% of them are captured. So it was an averaging approach. But we potentially have some new data sets that might help us get to that, but it's always a question of how do you determine which ones are working versus which ones are not.
And it's a slightly related question, but I understand that the way your model works, and again, I may not have this right, that once you decide that you've got you've picked your cluster, it's below, you've drawn that line from the top down, so it's in the area you're going to fund. You essentially assume every location within that cluster will have a line, the capability of a line delivered to it.
Yes, it will have a capability of a line delivered to it from that central node.
90% of which will have a line actually costed and delivered.
It'll be delivered. It's just that last drop portion is not necessarily connected.
Right, except for the drops,
yeah.
Right. It may be very difficult, but is it at all possible to make the model so that you knock off, if you have exceptionally high cost, very unusual high cost lines within that location, if the model actually can identify those, to knock those, to drop those?
We can, because we actually, in the model, we actually calculate cost actually at the customer level, and we roll them up to census blocks. So we can identify cost at a customer level and identify filtering at that level. Right now we do it at census blocks. So the census block is an aggregation of the customers in a smaller geographic footprint. we identify the high-cost customers within a census block and throw those out. And typically in high-cost areas, that census block may only have 1 or 2 customers in it anyway.
As a scenario analysis, have you ever tried doing that just to see whether it has an impact material? I'm guessing it probably would, but
Well, right now, what we've done is we just instituted the cap, the alternative technology cap, where we bring it down and we throw out the high-cost customers to help push that fund to the 1.8 or the 2.2. But we've not redesigned the network, per se, to keep those customers out. That could be done. We just haven't done it.
Last question. How long does it take to run this thing? I mean, for example, when you were saying you'd have to run it several times to do certain things.
It depends. So an economist asked me the question, so I'll go with it depends. But what a typical copper design runs in about 12 hours if you're running all 50 states along with Puerto Rico and the Virgin Islands. Full fiber run is about 24 hours. We have identified speed savings that we haven't implemented yet that may take that down by about a half. So.
Thank you. My name is Shomit Tridas from FCC. A couple of questions. One, you have said the take rate is 90% you have used. Do you have the timeline of how long it's going to take the 90% take rate, or are you just saying the year 1 is going to be 90%?
It is an assumed curve that starts at 90% and ends at 90%. So.
Also, the beginning, I see. Okay.
We're going to get there day 1.
Okay. My second question is, you have mentioned the cost of capital is 9%. How did you determine that?
The coalition gave me that as an input, so they gave me their debt equity structure. They gave me the cost of equity and the cost of debt. It was then blended together to come up with the 9%, which is important to us because we keep track of the equity portion is costed differently than the debt portion of the network.
Can you change in the model if you want to?
Yes.
You can do that. Thanks.
Hi, Ed Neff. Just to follow up on my previous question, so you could confirm that the model has 2 parameters. It has the ability to calculate a fiber to the prem cost and the ability to calculate a fiber to the DSLAM cost?
Correct.
So maybe you could explain, would you say that both of those are forward-looking and are forward-looking cost calculations for those 2 investment calculations?
Yes, as we deploy the DSLAM, it is as we would deploy a DSLAM approach today, as is the fiber. It's as we would deploy that fiber build today.
So the decision to choose between those 2 network alternatives is independent of using a forward-looking cost calculation?
Yes.
Follow-up question, when were the assumptions accurate you said they were submitted, this model will be put into place several years in the future. Will it be necessary, for example, for the electronic equipment to take into account cost reductions that may take place going forward? And is there a process for incorporating that?
Yes. Typically within a levelized cost study, you want to look at the planning period or the period at which these cost or rates will be effective. So if it's a 3-year period, you want to incorporate the inflationary trend of that investment class and levelize the expected cost of that because you want to capture the full value of that plant over the planning period. So you would want to include that.
Perhaps we'll get to that last point a bit more detail later.
Yeah.
Hi, Sam Kornstein. I have a question about the way you define the universe in the model. Back when you were the universe of locations that don't have broadband, back when you showed the maps, you said you first calculated the cost for all locations across the country, and then you exclude locations that currently have broadband as defined by broadband from a cable provider.
Yes.
So does that assume that the model's calculating the cost to provide broadband to locations that might already have broadband from a non-cable provider?
Yeah, the way the model works is we deploy an efficient network in that wire center, irrespective of if there's providers there or not. So it's as the network would be deployed in an efficient manner, and then we filter out the areas that are already served to capture the cost of the outlying areas. That's the current approach that is used.
Okay, so in some cases it might calculate duplicate costs for infrastructure that might already exist.
It does in fact do that, yes.
Okay, thanks.
Let's take one last question from Carol.
Hi, Carol Maddie, FCC. You said in the assumptions that the model serves both business and residential locations. What assumptions do you make for the business locations in terms of higher capacity services? And also, how does that take into account anchor institutions,
It's an excellent question. I'll have a slide on it later, but let me hit briefly on it in case you're not here when I hit on it later.
Why would
you
assume
that? You'll leave, but we took a business data set that was melded from a number of different sources. One was the economic census, which was out in 2007. The economic census provides to you SIC code, employees by zip code. We took that data, and based upon the SIC code and the number of employees, we estimated the type of service that they needed, whether it be a DSLAM service or a full fiber service. That was then brought into the model as the service defined. I'll cover a little more detail later on.
With that, let's wrap up the first session. We're actually right on time, which I'm slightly amazed by. The next session, we will kick off promptly at 11 o'clock, and that will run through 12:30 to be followed by lunch. Thank you all very much. If everybody could please take their seats, we're going to get started here. No, I'm a moron. If everybody could please take their seats, we'd like to get started here. Couple other quick notes while people are caffeinating up. There are more printed copies on their way, so keep an eye out on that back table. I'm sorry that we don't have those handy, but there's been more demand than expected. For those of you watching online, we are also working to get the documents, the PDFs, available online. If you go to the FCC website, fcc.gov, there should be a link on the front page for today's event, sort of a Happening Now page. We will get the documents posted on that Happening Now page, and the address is fcc.gov/events/ and apologies for this, Connect America Phase 2 Cost Model Workshop. With dashes between the words. I recommend that you try and get to that through the FCC homepage as your best bet. With that, we'll turn to Jim, and those are not up as of my last check a couple minutes ago, but we are working to get those up quickly. With that, I'll turn it back to Jim for the second session. Thank you much.
I appreciate those who have come back. More came back than I was expecting to come back. This is invigorating discussion, and it's going to get even better. We're going to go into the economics of the model. Not too far into depth on the economics, but enough so you understand what we're doing in the model. So let me go with it. First, let me define cost. Cost is a word used in many, many different ways. I can talk about marginal cost, incremental cost, long-run incremental costs, total element long-run incremental costs. There's various definitions, so you have to really define what we're talking about here. From an economic standpoint, all costs are opportunity costs. So the costs are caused by the contemplation of a decision, the action of implementing that decision, and the consequences of that decision. So when a business takes an action, resources are either used up or committed to one use rather than another. And that's really what we're looking at here. So it's the value of that other use that is really the cost that we want to capture. So the economic definition of cost is the value of the resource that will either A, or one, be used up, or two, committed to, or a portion of the capacity of the resources committed to, a use for a period of time, because of my decision. So by its nature, it's forward-looking, it's a focus on cost causation, and it's a focus on opportunity cost-based. One of the economists that I work with always had a great view of it. It's if you have a forward-looking video camera, and you could look at the future without your decision, and you take that same video camera and look at the future with your decision, the difference between the two views of the future are the costs that we want to capture. So with that understanding of cost, now let me go into another definition of cost, capacity costing. For those who have been around for quite some time, Dr. Rick Emerson was one of the proponents of capacity costing. He pushed this theory and helped prove its conceptual basis in the telecom industry. Basically, it's you take, telecom plant is lumpy by its nature. 25 pair cable, it's a lump of 25. I put in another lump when I get past 25 customers. A DSLAM may be sized for 384 customers. It's lumpy by nature. You can't necessarily determine who drives the cost for the next increment of 384 on a DSLAM. What capacity costing theory tells us is basically you take the capacity, the utilizable capacity of a component, divided by its, or you take the cost of that divided by its utilizable capacity, and that is the cost that you can assign to as a volume-sensitive cost associated with the people that use that piece of plant. There are some key criteria about capacity costing. Is one, the capacity will be exhausted at some point in the future, so that you are growing the lumps. If it is not growing and you're never going to reach the capacity point, it becomes a fixed cost. So you have to understand some of that. But here's from an old client study where we looked at capacity costs, and I'll compare this to working costs because there's two different definitions that you use. So in this one, we're looking at a cross-connect panel. The material price was $12,600. The number of DS1 ports, a DS1 is 24 channels. It's physical. It has 840 ports on that piece of equipment. So you buy the 12,600 piece of equipment. It costs, and it comes with 840 ports. The material price per DS1 port is then the 12,600 divided by 840, which is $15. However, we sell our services to the client on a DSO port basis. The DSO is like a voice channel, similar to that. The number of DSO ports available per DS1 is 24, so the material price per DSO port is 62.5 cents. So that is the raw, pure capacity cost number. However, I want the capacity cost based upon effective, or what I can efficiently utilize. So from an engineering standpoint, I may never run a piece of plant at 100%. It never happens. I need capacity out there for churn, for testing, for other uses, for bad pairs if you're talking about copper cable. So typically you will run capacity up to a point at which point the engineer says, I need to get new capacity in there. I don't want to get above. And in this example, it's 85%. So our capacity cost is 73 cents, or that's a capacity investment. I have an annualization factor which takes into account cost of money, depreciation, taxes, maintenance cost, and it's at 18%, so it gives me an annual cost of 13 cents or a monthly cost of a penny, a 1.1 penny. That, if you're looking at it from a pricing standpoint, becomes kind of your pricing floor. I don't want to sell below that because if I sell below that, I lose because this is effectively my volume-sensitive cost. On the flip side, I have working costs, and this is really the basis behind TELRIC. When we look at working costs, the exercise changes a little bit. The DSX panel still costs $12,600. My effective used capacity, I'm only using, on average, across all my DSX panels, 420 of the ports. So my cost per DS1 port is $30 now. The number of DSOs that I typically have working on each of those DS1s is not at capacity. I'm only really using on average 15. So my material price per port on a working basis is $2, or that's my material investment. I had to buy the same annualization factor, which brings me to an annual cost of 36 cents, a monthly cost of 3 cents. So it's triple the cost. And that is really the basis behind TELRIC costing that has been used in UNI proceedings. It's really the basis behind universal service models, and it's the basis behind what we do here. So when I talk about the 90% take rate we assume, I'm dividing my cost to the network by 90% of the customers that I'm serving. That is the unitization, and that's how we spread the cost out. So with that understanding of kind of the working cost mentality of their TELRIC, let me give you the financial constructs behind CQBAT. It is a forward-looking economic cost model, FLEC. It's consistent with total element long-run incremental cost methods, which were used in the UNI proceedings. So it's consistent with what's been done in the past. We are doing a scorched note, as I've talked about many times. So only the central office location and the association of customers to the central office remain. Nothing else is there. It is a long-run incremental analysis where all costs become variable over time. We do have greenfield and brownfield options within the model, and this is more not from an economic standpoint, but more from a policy standpoint. Do we assume some of that network is there, brownfield, or do we assume that this is a forward-looking cost model, all costs are variable, so therefore everything is included? It includes the shared and common cost, and then the cost attribution is based upon TELRIC methods. Our first step in the process is we develop the investments associated with the network deployment. So we look at the cost to run cable, the cost to bury that cable in the ground if it's buried plant, the cost for poles, the cost for electronics, to come up with the total cost of a wire center or in a census block. We then take that and apply annual capital, or we convert it into annual capital cost using annual charge factors, and I'll walk through each of these concepts in more detail. And then we apply the operational cost. The capital cost, as I've indicated, captured depreciation, cost of money, and income taxes. The capital cost is based upon equal life group depreciation and survival curve. So it's not a straight line depreciation. It's not acres, whatever you may look at on a tax basis. It is equal life group with survival curves, and survival curves capture the mortality inherent in the plant. So most electronics have what we call a bathtub-shaped mortality curve, where you have high retirements in the get-go because of just initial failures. It drops down, and then later in life it tips back up. And that is kind of what has been built into the model, is this whole concept of mortality curves to capture the true economic depreciation of the plant. Equal life group, for those who ever worked in capital recovery, which I'm not sure there's many people here, there's one or two. Equal life groups are, phone companies buy millions of pieces of plant. They have thousands of miles of cable. They have hundreds of DSLAMs. Equal life group is each group of assets falls into its own unique life category. Some will last 1 year, some will last 2 years, some will last 3 years. It's once you use the survival curve to get to the equal life groups, within the equal life group, we then use straight line depreciation. It's a whole theory and concept we could go on for days about, and I'm sure by tomorrow you'll kind of say enough's enough. But we can cover that at another point in time if you'd like. The economic lives we used were in the FCC proposed ranges established in 1999. Whether those are correct for now or not is not the point of discussion. That's just what we used. We broke the operational cost expenses down into plant-specific, plant-non-specific. For those outside the industry, plant-specific are typically like your copper maintenance, your fiber maintenance, are specific to the piece of plant. Non-plant specific may be your network operations center. It may be your testing center. It may be things that aren't necessarily associated with a specific unit of plant, but are plant-driven. You have your customer operations, G&A, and then uncollectibles. And we go through a levelized, annualized cost approach. I'm just not sure I want to go through these next slides. I'm kind of speechless. Some of these slides, I actually had to develop some of this material for the FCC when we did the National Broadband Plan. So when we did the BAM model, we had certain people on the team that I won't point at, who said, I want a business case over a 20-year time frame, looking at 8 million census blocks with all the plant identified within those census blocks. Can you build that in 4 months? And I said, no, you really can't do that. And that's really not the mentality of what we've done in the telecom industry. We really do this thing called steady state. So really what steady state is, it just reduces the number of explicit assumptions and simplifies the whole modeling process. So I'm just looking at a period in time. So I may have assumptions about take rate over time. Typical take rate is an S-shaped curve. It takes a while for that technology to kind of get into the consumer's mindset. There's quick adoption, then that levels off. What we do is we levelize that to the point in the midpoint of the curve. It's a net present value analysis of that curve shape to give us the average over the time plan or the planning period. That's one input for us. versus 20 inputs that we have to worry about. On the CapEx, you may have different capital deployments as the number of customers grow. I have success-based capital that takes place. So I have lumpy capital going forward in the future. What levelization does is it gives me the ability to understand that capital deployment that is required over the levelized or the planning period. So in the end, I have one column to worry about instead of 20, 30. And when you're talking about 8 million census blocks that you're trying to keep track of, it just simplifies the problem. When I said it's 24 hours to run fiber to the prem, think about now trying to track 20 years of fiber to the prem. And this has been used in rate cases. It's been used in regulatory proceedings. This has a historical basis that has been validated over time. Part of it is it has its roots in pricing. So when you go out to market with DSL, and you know you have low demand in the initial period, high demand in the late period, you can't go to market with what you think the price should be in year 1 versus what the price should be in year 10, because you won't get any customers when you price it at $1,000 per DSLAM because you're only going to have 3 customers. And in the end period, you may be able to price it at $2, but you'll never get to that point because you never got any customers because you started at $1,000. So what levelization does is it gives you over that planning period, what is the price I need to charge so that on a net present value basis, I am made whole and I am profitable, is the whole concept behind it. To do that, one is we have to levelize the capital, or we levelize using capital cost annual charge factors. So that captures depreciation, which I talked about was equal life group, and we do that on an account by account basis. We bring in cost of money, which gradually declines over time. The actual cost of money doesn't. The rate stays the same. It's the actual cost that we capture declines over time because the asset base declines over time because you have depreciation that pays back to your investor base, so your natural investment drops. And then we include income tax because as a entity, you have to, one, make an income that is sufficient for your investors. That income should be at the after-tax rate that they're seeking. So we naturally have to include tax dollars in this to capture the full cost. So we bring that in. And then levelization is just the smoothing method that is all based upon net present value. So basically, it takes that curve, which may look like that. The average cost at the initial point is very high, at end point is very low. We levelize it, and we can show from a net present value basis that if we price it appropriately at that levelized value, we will cover and make that revenue over time. If you really want to get into the meat of levelization, I put this spreadsheet together. Basically, it just proves what I said. We make assumptions, and you can go over this later. I'll just hit some of the high points. The investment we're making is $100,000. Cost of money is 11.25%. The depreciation on the frame is 10% per year, and the depreciation on the plugs, we're assuming a 5-year life on the plugs. For simplification, I just assume taxes were 0. So when you look at this, we're looking at the gross capital goes in year 1. You're going to have depreciation over a 10-year time frame. You'll have a net capital. So as you see, the net capital or my investment in the network drops over time. So my cost of money actually starts at 11.25 of the 5,000, which is that, but it drops down to 563 at the end point. We can look at the plugs the same way and get a total and get that total annual cost. So you see the annual cost starts at 26,000, ends at 16,000, and what we like to come up with is a single number. So we come up with the net present value of those cash streams over time. We levelize them, and there's a magic formula to levelizing, which if you send me an email, I'll send you what it is, but it's fairly simple. You levelize that, and then you take that number divided by the initial capital investment to come up with what we call the annual charge factors. So for depreciation on the plug or the frame, it's 5% per year. The actual realized cost of money is 3.58%, which is much less than the 11.25. We've got the gross capital. Actually, these are the key piece components. So now we get down to the total. It's 15% for depreciation, 7% for cost of money, and the annual cost is 22.19%. So that's my annualization factor. And what I had to prove to some people was, well, this is not real. This is not a good number. So then I went through, okay, the network provider borrows $100,000 from a bank and has a balloon payment at the end. So their gross capital is $100,000. There is no depreciation because it's a balloon payment at the end. The net capital remains the same. The cost of money, I have to pay that bank. I'm not paying back because it's a balloon payment. And at the end, I pay $150,000 back. And in the end, my net present value is the same number. My annual charge factors are the same number. So in effect, it allows us to compress everything into, I use these numbers in the model, which lets me expand to a kind of a business case mentality, but without the complexity and added processing of that need. One thing to keep in mind is typically this is it's around a half of the actual cost of money used. This is typically where the cost of money takes place, or where it ends up at. There's a couple things that play into that, which I'll get to, is deferred taxes, and there's another topic. So when you compare the levelized cost to the business case, they both identify capital and expenses, both use time value of money concepts in presenting the results. CQ-BACK captures the one-time capital expenditures, whether they're greenfield or brownfield, and the associated expenses, and uses levelization. The business captures yearly variations in revenue, but in the end, they come to the same number if your assumptions hold true. I hesitate on this one too, but we include taxes in the model, and that's basically because you have a after-tax rate of return for your equity. We want to make sure that we include that tax that you're going to incur on your earnings into the cost. So basically what you do is, in this example, I borrow $1,000. My debt is unequally split. My debt rate is 6%. My equity is 16.5% of what I have to return. My first year interest or debt is $30 on the debt, $82.50 on the equity that I have to pay back. My first year depreciation is 50 and 50. My tax requirement is simply I take the tax rate and factor that to get to the $52.75. So when I come up with what my revenue needs to be, I really start at the bottom to get back up to this number in rate-making practice. From a business perspective, you start at the top. This is how much money I made, $465. If I take out the $200 of OpEx, the $100 of depreciation, I have earnings before interest and taxes of $165. I pay my debt holder $30. I'm left with $135 of earnings on which I have to pay taxes of $52.75. That is a 38 or 39% rate on that, which gets me to my income of $82.50, which is that number right there. So we include taxes because it is a cost that the revenue will have to cover to make everyone whole and happy. And I know you're really, really interested in deferred taxes. We include deferred taxes in CQ-BACK through the annual charge factors. Deferred taxes take into account the fact that on your tax books, you may depreciate quicker than you do on your real books. I'm not saying you have multiple books, but you may have multiple books. What deferred taxes takes into account is many times the tax life is much shorter. So I may have a 10-year book depreciation value, and I'm using a mid-year basis here. My tax depreciation gets me 20% back per year. So I have a deferred tax that occurs, and deferred taxes is I have a liability on my books because my earnings in the initial years are down because this shows my expenses higher. So I'm actually having a liability that sits on the books. So I deferred them. That plays into your capital structure because now you have some interest deferred taxes that sit as part of your capital structure. So we adjust the rate of return for that deferred taxes. And that's all part of this rate of return methodology. So now we jump to annualization. Annualization then takes into account, it is really that levelization applied to the capital structure of the business. So we look at depreciation, and as I said a number of times, it's based upon the FCC's range, which was, I think, out of CC docket 98 and 137, if you're interested in reading that docket. There may be some more recent ones if you're wanting to look at that, but I think that's the most pertinent one. We do use equal life groups, which I've kind of covered. The survival curves are actually Gompertz Make-em survival curves. You can use Iowa curves if you've ever been in the capital recovery groups. And then we take the annual depreciation expense and we levelize it, but it's on an account-by-account basis. The rate of return is the weighted average cost of capital applied to the investment and levelized over the life of the account. So while we might say it's 9%, the rate that you'll see in our annual charge factor table is nowhere near 9%. We include income taxes, and again, it's all based upon levelization. And again, this is both the example of levelization and annual charge factors. It's really, we're trying to come up with these three factors to derive our cost when we talk about annual cost of the network. So in the end, with annualization, we come up with the CQBAT cost, which is one, it includes the depreciation of the network that's built. So you take the investment times the levelized depreciation factor. We include cost of money, which is the same kind of equation, investment times the levelized cost of money factor. Income tax, which is the investment times the levelized income tax factor. So that is our capital-related cost, all turned into an annual basis. We divide by 12 to come up with the monthly cost. And then we come in with the operational cost, which are plant-specific, plant non-specific customer operations, and corporate operations. And I'll go through the derivation of this tomorrow. We'll go through the derivation or the development of the investment partly today and partly tomorrow. I throw this in now because I know it's been a point of discussion. People have different views of this. There's a public notice that came out on the entire discussion of greenfield, brownfield. So what I'm going to talk about is not necessarily the policy issues. I'm going to talk about how we do it in the model. So in the model, there is a toggle in the model when you run and create a solution set, and I'll talk about solution sets later, that you can indicate whether greenfield should be set to yes or no. If it's set to no, that assumes it's a brownfield build. And you go, well, okay, I turned it on. What does that really mean? In the capital inputs, the CapEx inputs, there's a column on every piece of capital that indicates this piece of capital is a greenfield piece of capital, a brownfield piece of capital, or it's associated with any type of build. So for example, in the CapEx table right now, the copper distribution is listed as greenfield. If you use this assumption, I'm going to build the network, but I've got this brownfield mentality, there may be some network that exists. That's really what this is about or meant to capture, that there is potentially some network out there and which network components are out there. So every asset item in CQBAT can be identified as greenfield, brownfield, or all. So you turn on the greenfield, you populate CapEx appropriately, it runs through, and you get greenfield. And part of this was actually based upon what the work we did for the National Broadband Plan. And it was a mentality based upon the National Broadband Plan in which we were deploying a service on top of a network that already existed. So there's a voice and data platform out there. We were deploying the cost of broadband as an add-on service to that existing network was really the evolution of this mentality, in that you didn't need the copper. It was already there. We're just going to pump bits over the higher frequency of that copper to get it to the customer. Therefore, I don't need to consider that cost as part of my National Broadband Plan. The issues, though, with that, with a universal service model, are it excludes all the operational cost associated with that customer, with the copper plant, with the existing plant that you consider is out there. When we're looking at universal service, it is deploying the pipe to the house, not the services that override on the pipe. It is the pipe. So there are operational costs associated with that are included in universal service. The other thing it does not capture is replacement capital. That plant will fail at some point in time, and you will have to replace it with new capital. This approach that we had in the model, because we had not contemplated what was being discussed in the public notice, the approach, it doesn't necessarily fit correctly with the universal service approach. Doesn't mean that we can't implement an approach within CQBAT. It's just that implementation was not necessarily correct. There was an alternative approach where we tried to estimate what the greenfield-brownfield toggle would do. In this approach, we set the greenfield to yes, so we built all the plants. So we built the copper plant out there. We then went through the annual charge factor table and said in that annual charge factor table, let's identify the classes of plant that are, quote, brownfield. So it was aerial copper, buried copper, underground copper, poles, conduit. Brownfield plant. Therefore, let's set the annual charge factor, the depreciation, cost of money, and tax to 0, but the investment comes through the model and we can apply the operational cost. So it gets us to the operational cost. So it addresses this first issue that we have with the current implementation. What it doesn't do is it doesn't address the whole replacement CapEx. There is a continuing, ongoing replacement program that has to take place. And the other issue with it is some categories may be mixed. Some of that plant may be brownfield, some may be greenfield. Conduit. I was trying to come up with a good example and I was late and I just used conduit. But is conduit there and existing, or if I'm deploying a DSLAM with fiber on a route that doesn't necessarily have conduit, I might have to deploy conduit. So there's a mixing thing. So if there is a decision to go to brownfield, there does need to be some conceptual discussion of what that means, what's included and what's excluded. And that's really why I brought this up. This was actually we have a support line. Don't like to advertise it because then we get questions. But questions do come in. And one was a series of questions about this whole greenfield, brownfield implementation. So the person asked, when the model is set to brownfield FTTD, can you confirm whether it does the following? Does it model the cost of additional DSLAMs where DSLAMs are not present within 12,000 feet? These are really deep questions, so there's more to it. But we just came back and said, correct, the DSLAMs are added as needed to support broadband requirements of the model. The investment for these new DSLAMs is captured in the brownfield view. So we're capturing DSLAMs in a brownfield view. Does the model cost for the building of fiber to these new DSLAMs? Yes, we include fiber because we assume fiber is a greenfield or a brown. It needs to be done even in a brownfield environment. Does the model cost the fiber all the way back to the CO, even though where fiber is currently assumed not to exist? In the model, we actually construct a forward-looking model. We take that fiber and attribute the cost of the fiber from the CO out to every DSLAM that is served off that fiber from the CO, and I'll walk through that exercise later. But we do include the cost of that fiber all the way back because at some point, the addition of one extra DSLAM may exhaust your fiber. So we go back to capacity cost mentality. At any point in time, my next unit of demand will exhaust what I have in the network today. Therefore, I should include it as a capacity cost in the network, and that's how we approach fiber in the network. Let me go to the next. Is there other significant costs that brownfield models, other than condition and CP, can you please address and confirm? And our response was the model really doesn't model brownfield differently than greenfield. It is the same network deployed. It is, do I include the cost of various network components? Do I include the cost of that copper, yes or no? Is really the mentality of the model. And then when the model is set to brownfield, does it only affect the CapEx input sheet? If it affects other sheets, please specify. Again, there's multiple ways of going about brownfield. We approach it from looking at the investment classes and determining if it's a cost that should be considered or not. We'll hold the questions and answers till later. So now let's walk through how CQBAT works. First piece of data is we get service locations. Service locations to us are residential and business. Residential comes from census data. I believe it's 2009 census information. So it's 2000 census that has been factored up with county estimates to 2009. Business side, we take 2007 economic census, combine that with a third-party source for businesses to come up with our business location database. We allow users to provide us inputs. We have the network topologies. The network topologies are the design of the network. So when we run fiber to the prem, we capture the length of cable, the length of trenching, the amount of DSLAMs, the size of DSLAMs is in our network topology, and I'll go through each one of these. We then have, that helps us define our capital expenditure that we need to build out broadband. We annualize that. We then add in our OpEx. We then overlay current coverage of telco and cable to understand what we're going to kind of filter out, which then gets us to our results by census block. So we roll everything to census block, and then we throw in the support toggles, which gets us to our CAF2 quote results that have been filed. So let me capture a few kind of overall or overarching things about the model. First is, we've had questions, do you capture company-specific and geographic differences? And my answer is yes. Every cost in the model is specific to that census block. And how do we do that? One is we have a plant mix that captures the variation by state, by density, and differences between distribution, feeder, and interoffice. So within each central office, it will have a different plant mix. It is unique to that central office. It is unique to the route. We have company size impacts for operational cost, which we'll go through, and then the CapEx purchasing power, which right now is set to 1 for all providers. We have terrain and density impacts. So the construction cost is impacted by the terrain in which we have to dig, bury, mount a pole, whatever it needs to be. So I know that in a normal terrain, it may be $2 to $3 to dig a trench. In a hard rock terrain where I have to bore, it may be $10, $20, $30, $40. So understanding the terrain differentials is important to the model and what we do. We have a regional cost adjustment that captures the cost differentials between regions of the country. This is applied to the CapEx inputs, so both the material cost and labor cost associated with CapEx, which then indirectly impacts the operational costs that are based upon factors of that CapEx item. So, if you look at the regional cost adjustment for, say, Hawaii, it's 20% above the cost in the mainland because of transportation costs. Our source is RS Means. It's a national source. Some may dispute that it's applicable in certain areas or not, but it's the best source that we could find. But again, it's an input. Those inputs can be adjusted to reflect the specifics of that region. We bring in sales tax. Sales tax is different in each state, so we have to check, make sure we capture that. And then the loop design is specific to each and every central office. And I'll walk through how that is done. Next item is, well, how do we get and identify the carrier's ownership of service areas? And you might go, well, you should know which carriers own which wire centers. And in theory, you should know that. It's not as easy as you would think. So first, we start with what TeleAtlas provided. TeleAtlas was the vendor that provided us the wire center boundaries. And in that, they give you an initial identification of the SAC or the owner of that wire center. We use some additional files that the FCC kindly lent us to look at this, to look at SAC mapping to OCN. SAC is service area code, OCN is operating company number, for those who are interested in the acronyms. The coalition then, once we took the FCC list and we took TeleAtlas, we blended it together and said, here is the SILI to SAC, here is the SAC to company. please review those. So the coalition went through that. They gave us corrections to that so that we could have what we thought was a good updated list. So within CQBAT, we can control this and changes to it, so it's not necessarily a hard and fast data set. There is what we call the Telco Master, which is a data set within the CQBAT system, which you can get printouts of within the auditing platform of the online system. That gives us the mapping of CILI, which is the wire center. CILI is Common Language Location Identifier. It's the identification of the wire center. That gives us the mapping to OCN and SAC. And then we came up with what we call a short name. There are many names in all the various databases for a common company. Verizon may show up as different names, Windstream, all those. So what we're trying to do is identify all the Windstream properties, and we simply just came up with a short name for Windstream, WND, I think it was, or WIND. The short name is really how we report out results in the model. We can increase the number of short names, but we tried to just group all the small companies who weren't part of the coalition into one big bucket. We also do the mapping of the rate of return and a price cap, and I'll talk through how we do that. And then from all this, we have an OCN to CO size table that lets us identify the size of the company. Size drives operational cost loadings that we use. So if we change the size of companies, we can understand if we assume that there was one monolithic carrier throughout the U.S. who had one operational cost, we could set all companies to a large company and use that to see what that impact has. So additionally, we went through USAC reports to identify that first cut at the rural, non-rural, and price cap rate of return was from USAC reports. We used the HC05, the HC12, and HC9. So we farmed those to determine the classifications of SACs. We then again sent that out to the coalition for review, and that came back. And this process was actually the basis for the CAF1 regression model and is in the CQBAT. So the tables are consistent between what was used in the regression approach and in this model. But again, they can be changed, and I'll show you on the next slide that we did do some. The company size categories, we broke them down into 5 size categories to try and capture the differential in operating costs between companies. So we have the extra small, which was 0 to 1,000 lines, extra small, 1 to 4,000, small, medium, and then large. This is what a telco master table looks like. I know some people in here are saying, what does that look like? Show me. This is what it looks like. But this is a table within the model, but it gives you the service area. So this is the wire center name, the CILI code. This is the company name that we had to deal with. There's a study area name that we had to deal with. There's dominant switches that we looked at, LATAs, but we boiled through all this to try and come up with who owns the wire center, because that really dictates the purchasing power of the plant and the operational cost of that area. And then there's another table that defines size. So in this, we go through all the companies. So, we did not just look at the coalition companies. We looked at all companies and went through and tried to identify things that were common ownership. So IslandTel, Hamden, Heartland, Community. There's a magical approach to say, those are all TDS, and that's some of the exercise we had to go through. There have been some changes in the service area mapping because we continue to find corrections, changes, sales, whatever it may be. So we try to maintain those going forward. The original filing had a Telco Master data set. In the February filings that we made these changes. I'm not going to go through them. And we have some changes that are outstanding. One of them is in the FCC's order, I think it was, all price cap companies and any company that has a price cap property is included in this mix. So we have to go through the tables and modify it so that we capture some changes for Fairpoint and Windstream who have some rate of return properties. We want to make sure that we capture all that. So there are some changes that are outstanding. Now let me walk through the demand data that comes into the model. So for residential data, we take census block data. As I said, it was 2009 vintage. We have the housing unit counts within each census block. We take those census block data and we randomly apportion the housing units to the roads of the census block. We do have additional methodology that I'll talk about tomorrow to improve upon that, but that is the basis of the data. Census blocks typically are small. Typically, there are some quite large census blocks out there. But when we randomly disperse them, we use roads that are classified as what we consider habitable roads. So we may exclude four-wheel drive paths from where we place houses to try and get an accurate dimensioning of that. On the business data, as I said earlier, we had census block data from a third party. I believe it was either Geolytics or GeoResults. I can't remember which. Geolytics. We then pulled in the economic census data, which was a 2007 vintage, which was provided at a zip code level. If you're a GIS person, you really don't like zip code kind of stuff because there really is no uniform, standardized zip code boundary database sitting out there. But that's beside the point. So anyway, the census data comes in at that level. We then find out all the census blocks that the zip code boundary that we used touches. We then randomly disperse the economic census data to the census blocks that the zip code touches, and then we disperse them along the roads. The economic census has, I want to say, 9 million points in it. So it's not all businesses. It's typically larger businesses. So that's where we brought the Geolytics data set back in. The Geolytics is, we took the Geolytics to represent SOHOs and small businesses. So we took the differential between the economic census counts in a census block to the Geolytics to come up with the additions.
And Jim, I got that backwards. On the biz side, it was GeoResults. On the res side, it was GeoResults.
Yeah, let me correct that. The biz side was GeoResults. The res side, we used Geolytics to get us up to the 2009. So I apologize for that error on this slide. So on the business side, Carol's not here. This answers her question, but what we did is, and you really can't see this from where you're at. I can barely see it up here, but on the residential side, we assumed a DSL service to each resident. For basic business, we gave them a DSL. From the economic census, it gave us a breakout of the number of employees for the firm, the SIC code, or the NAICS code of the firm. And what we did is we broke it into two different NAICS categories. Typically, your information services are in one kind of above, I believe, 50, and more your manufacturing and agricultural are below 50. So we tried to differentiate them that way. And then we looked at the count of employees at that site to say, well, if they've got 100 employees at the site and they're a SIC code of 50, we're assuming that they have 2 dedicated fiber connections to their building. They don't need DSL. They've got their own private Metro Ethernet service potentially to the building. So what we do is when we deploy the network, we will run 2 fibers to this location. When we come up with the universal service costs, we filter out the cost of those high capacity business locations from the results because they are not part of a broadband deployment. They've already got their own dedicated facilities to their building. We then added to the business data set a data set of what we had of towers. So these are wireless towers, which aren't necessarily captured in a business data set. And we know towers typically need a fiber connection. On the forward-looking view, all the towers would love to have a fiber connection to them to support LTE deployment. So we threw those locations in, and we had those at a latitude and longitude, so we knew where the towers were. And then we also threw in anchor institutions as additional points, and we pulled those from the national broadband map. So that's that's the customer data set and then the demand that we assumed. And in the end, we're looking in the universal service system to capture the DSL-based customers. So there are some DSL customers down here, smaller businesses, 1 to 4 employees, 5 to 9. We assume they're going to get DSL or broadband service. Those are the ones that get pushed into the results of the model. One of the key issues I brought up earlier was you've got to determine what's in and what's out. So here is the extent of our network. We run from the customer demarcation point, which is typically the NID. In a fiber network, it's an ONT typically placed at the customer's premise, to the router on the cloud. That is the extent of the network. We don't include the cloud. And I'd have to check to see if we even included the router that is on the cloud. But we do include the Ethernet switches and intermediate routers that get you to that point on the cloud where you hand your traffic off. It is an IP-based network. We focus on the cost of that fat data pipe. There's no video gear, no voice equipment. The voice, video, and data are all considered services that ride the bits on the pipe. So that's why we left them out. They're really an incremental service that you price well above and beyond the cost of that data pipe. The network is built to pass and ready to serve all locations, so it is consistent with many state polar color requirements, provider of last resort, carrier of last resort. So this is the network. So this is the cloud, pretty little cloud up here. The router that sits on the cloud, there's rings that connect to each of the wire centers, and we've captured this on down. So within the wire center, we'll have the house or the homes. This is a kind of a fiber view that goes up to a fiber splice terminal or a fiber service terminal, up to the splitter, up to the OLT that sits in the office. That OLT is then connected to a router that then routes up that way. This is the extent of the network. Now let's talk about the existing broadband coverage that we used within the model. We used NBM, the National Broadband Map, Round 2 data, which is fall 2010 ground date. So as of today, it's a little dated. It does need to be refreshed, and we'll talk about that tomorrow. We downloaded the data on March 2011, and it's in Census 2000 format. As we move to updates of the National Broadband Map, it is now in 2010 format. So there is some underlying structural changes in the model that need to take place to move to 2010 census blocks. There are different shapes. There's more of them, and we need to capture that. We broke the coverage into 3 technology groups. Telco, which in the NTIA data is the Trans-Tec of 10, 20, 30, and 50, for those interested. On the cable side, it was Trans-Tec of 40 and 41, which is NTIA DOCSIS 3 and DOCSIS Other. And on the wireless, while we brought it in, it was not used. We did bring in NTIA Mobile Wireless and Fixed Wireless, which was Trans-Tec 70, 71, and 80. So the fixed wireless was included in the wireless category. Well, now you have to kind of farm the data, because within each census block there may be different information about the census block. So we had to come up with, first, the coverage speed winner. What speed do we assign to that census block? So within each of these technology groups, the top speed was calculated based upon the top speed in each technology category. So if there are multiple cable providers in a block, we took the fastest speed available in that block as being assumed for the entire block. We need a speed per block. You could go with the lowest. We chose to go with the highest because that is what is available. We did this on a block-by-block basis, technology-by-technology basis. There's also the problem of they provide an upstream and downstream speed tiers. So the tier 3 is 0.768 to 1.5. Tier 4 is 1.5 to 3. We brought those in, but we assigned the lowest on this side to that speed tier. So when we look at the census block to identify which tier they fill in, we picked the one of the highest provider. But as we looked at the speed triggers in the model, we took the lowest of the range associated with that tier. And you'll note here, there is not a tier 4 that goes 1.5 to 4, so there's some disconnects between what's kind of desired a 4 down versus what's being collected. So there were some data processing issues. If you've worked with the National Broadband Map data, It takes some exercise to understand how to use it and go with it. We only included blocks that had a valid TransTech. If the speed categories were below the FCC threshold, which was 768, we ignored the block and gave it a 0 speed. But no, if the speed categories were below, but if there was no speed categories, we assumed it to be 768. Again, these are assumptions that can be changed, but this is what was done. So now let me get into some of the issues we discovered and the fun we had to go through. This was round 2 cable coverage in Kentucky. So as you look at this, the yellow is what was reported in the National Broadband Map. We note here that Lexington is shown as non-covered. We knew that not to be true because we know Lexington has cable coverage. So what the coalition asked us to do is come up with some methodologies to kind of true this up to what we think is the cable coverage. So we looked at a number of third-party sources, Warren Media. We looked at one other one, I can't remember who, and it's not important, but we looked at a number of data sources. It's really indeterminate what is the best source, public source for data coverage, because they all differ, and none of them are really, if you're a third-party provider here, none of them are really right, but they're best guesses of what the cable coverage is. Some use zip codes and round out the zip codes. If they find a subscriber in a zip code, you blob in the whole thing. We chose to use Warren Media as an alternative source. One was the price was good, and we thought it was a fairly representative match. So what we did is, here is the Warren Media coverage on top of the national broadband data. So you can see there's quite a difference here. And if we just relied on the national broadband map, we would have had more blocks potentially coming through than should have. So we overlaid the Warren Media, and you see the Warren Media is a fairly big blob. And we said, no, we're not sure we believe all of that. So we came up with a process in which we filtered down the Warren Media. One is we removed any Warren Media CDP, which is a census designated place, that contained SPDD coverage. So if we saw the designated place being shown in the National Broadband Map, we took the National Broadband Map as kind of the source. Then we removed any Warren census designated place that had a linear density, which was homes per road mile, less than 35, because that's typically a cable company's threshold. It's anywhere from 30 to 40, but it's in that ballpark. They typically will not build when you get below that because it's uneconomic. So when we did that, we identified these additional pinks as things to add to what we considered the cable data coverage in the model.
Jim, just to be careful here, Lexington actually, just to be careful, the Warren Media doesn't pick up, in round 2, it didn't pick up Lexington because there was a little bit of SBDD coverage in there. So we were trying to balance between going overly aggressive with the Warren Media and staying conservative, and we didn't pick up Lexington as a result. It's obviously covered now in further rounds of data, but in the model right now, the Warren blend doesn't pick it up. So.
And I'll give you a fun tidbit. You're looking for some fun, I'm sure. This really doesn't matter in the end. And you go, well, we sure does, because cable competition, we want to make sure that those areas that have cable competition are excluded. Well, what you find is when you use an $80 benchmark, there are very few, if any, cable providers in high-cost areas. So when we ran with just the SPDD, we ran with the Warren, we ran with the aggressive Warren, the end results really didn't change a lot. There was some modification, but when you set a benchmark at $80, it typically already accounts for where cable is. Cable is not going to build where it costs more than $80 a customer. They can't make money. So by the use of a benchmark, you naturally filter out competitive areas. So while we wanted to get this right, The coalition came back on us and said, "Are you doing this right? This just doesn't look right." And as you talk through it and you look at it, it then starts to make sense. So here are the data sources. I'm not going to go through these, but these are all the data sources we used in the model. It is in an appendix in the filed document, so you can go through this. And now my favorite part, the guts of the model. So back to my slide. So this is the simplistic view of the model that we put in the documentation. So you've got your user inputs, the toggles that drive. You've got the cost to serve module, which takes what we call the cost pro network topologies, which I'll go through the development of this. It takes the census information, the SPD overlays of where coverage is to come up with that cost to serve. That SPDD feeds just a field in the data set so that we can then come to the support model. User has their toggles of what's in, what's out. Do I take out cable served areas? Do I take out telco served? Whatever I want to take out goes into the support model, which gives you reports. So that's the 50,000 view level of the model. Here is kind of the guts of CQBAT, and it's really not the guts. It's just these are we only have 16 steps. Note here. It's important to note that. But within those 16 steps, we might have 10 to 15 substeps. And within each of those 15 substeps, there may be even further substeps. But that is the steps that go through, and we can walk you through the source code. The source code has been provided through the second supplemental protective order, so you can view the source code. But this is really the logic of the processing of the data. And basically what we do in quasi-English is our first thing is we create what we call a solution set. So it's our nomenclature of I run the model with user inputs. I create what we call the solution. The entries into the solution set are driven by what's in the network design distribution table. And I'll walk through what this is. This is the network topology. We have one record is created for each census block, service area, node 2 ID that meets the criteria. A node 2 is, consider this, the DSLAM. So a census block in the solution set actually can be partitioned up into multiple records. The solution set contains census data, coverage data, speed, the number of node 4 working lines, the structure and density. All the guts are captured in that solution set. And I'll walk you through what's in the solution set later. We process through in which we update the node 2 and node 0 fields based upon the feeder data. So we're bringing in feeder. This gets us our distribution side. Our feeder comes in. We apply the take rate for business and res. We apply the bandwidth. We roll up the bandwidth up to the node 2. How much relative demand by customers is that in my node 2? I prepare then these CapEx tables for both the distribution side and the feeder side. I apply the CapEx distribution. I apply the feeder CapEx. Middle mile then comes in. I then apply OpEx, or create the OpEx, apply the OpEx, which gets me to my total estimate and total cost. And if you have a few weeks, I can walk you through it all in the code. So now let's walk to the solution sets. The solution set is really, it's the collection of output data processed by the model based upon the user-defined settings and input collections. It contains what's a function of the user specifying the states to be included, the toggle settings that define the network that's being deployed, whether it's fiber to the prem, fiber to a DSLAM, and then the two main types of data that feed it is the input collection, which I'll talk through, and then that network topology. So the network topology is what the network, that's those maps I showed you of here's where the feeder pathing is, here's where the distribution pathing. The input collection captures the cost of the material, the operational cost, and those two are combined in the solution set. So these are all the fields available in a solution set. And you get down to the ones where we've got these things called node 2, electronics, investment, Node 2 fiber cable investment. So it captures for each census block all the investment associated with that census block. For the IT people among us, I thought I'd throw in a much more expanded chart. So you can see the flow of information through. It actually goes through. The Tiger data comes in this point. The Wire Center TeleAtlas data comes in here, where the coverage data comes in. So this gives you an expanded view of that model. And then we just have a different view that kind of gives you, here's the input collection tables you control, compared to the various system tables to get you to reporting. And I'm not able to kind of go through this in more detail right now. So let me cover the network topologies. This is the first input, and I hate to use the word topology, but it's the best one we could come up with, but it's the basic architecture of the plant in the network. So as I said, it's how many feet of cable, how many DSLAMs, the size of the DSLAM, how many NIDs, the length of the drops. All that is captured in this network topology. We run these in the background, so this is not a user-driven set. So we've loaded a fiber to the prem topology and a fiber 12K topology. We can create additional topologies. It takes about a week of processing to create all the topologies across the 50 states, but it can be done. We just need to know what the design criteria it is you want in those topologies. So this is what the distribution topology looks like. It actually has a record in here for each census block. It's got the service area identified, how many customers are in the census block, how much drop cable is in that census block, how many working res, how many working biz, the length of the cable needed, the distribution cable to get to that census block, the actual apportionment of the cable that we assign to it, the splicing. We actually capture all the splicing costs. The setup cost for the splicing is captured in here, and then all the structure cost. We also have, in addition, so all the structure is identified, so we know if it falls into normal terrain, hard terrain, if it's in medium terrain. The node 3, which is your pedestal, how many pedestals serve this census block, the density, which drives cost, and then what DSLAM ID serves it. And that table exists for each and every wire center across the U.S. So it's really it's almost the bill of goods of what you need to deploy that wire center. The feeder path is the fiber that comes back from a DSLAM. We have similar information here. We go through and understand how many splices of the fiber are associated with that DSLAM. So what we have here is an entry per DSLAM. The structure needed to connect that up, and it's broken up into urban, suburban, rural, and hard, medium, and soft so that we capture the correct structure cost. We also capture that on the feeder pathing, it's shared sometimes with the distribution pathing. You may use the same pole. If both distribution and feeder are aerial, you don't necessarily put in two poles. They are on the same pole. So we capture that there is sharing of that structure between distribution and feeder, but we don't assume it's sharing all the time. There is a table that defines how much of that shared path is actually shared. So these tables I'll actually go through so you can actually see pictures and get this visualized, but I just want to get you familiar with there's network topologies that sit out there in a database. We then bring in all the tables that you as a user control. The first is the annual charge factor table. We supply this table based upon our cap cost model. It is based upon a number of assumptions. One is, as I've talked about, we use equal life groups. It's a levelized approach. It assumes a 9% cost of money, and the lives are within that FCC's basis. This is basically the inputs that you, through us, can control. Because I have to run a model behind this to kind of come up with this end result table. But you provide the economic lives for the assets. These are all within the FCC range. You provide the tax life for the asset. and then the future net salvage. Future net salvage is what will that piece of asset be worth, or how much will it cost you in the future to remove it. Again, all costs that are incurred by the telco, so we will make sure we capture that. You provide return on equity, 9.7%, debt rate, 7%, debt ratio, 25%, which when blended together comes up with our discounted cost of money rate of 9%, which we use in the model. We use a 34% federal tax rate and a 5.3% average state tax rate. So these are the inputs to the annualization. We put that through our COP cost model, which then ends up, these are monthly numbers. So the cost of money for area copper is 0.0042%, or it's actually 0.42% per month. Depreciation 0.59%, federal tax 0.18%, state tax 0.03%. So this is something you can control. If we wanted to say a brownfield build, I don't believe there should be any cost of copper in the model. I could come in and just zero these out and run with a new annual charge factor table. Bandwidth is, again, it was supplied by the coalition but was consistent with the National Broadband Plan. It provides the busy hour bandwidth on a customer who is taking that data service. We looked out into the future during our planning period and said it's 440 kilobits, or almost a half a meg, in the busy hour per subscriber. It didn't have a big impact in the model because in the rural areas where you have a DSLAM, a typical backplane of the DSLAM has either a gig or a 10 gig pipe coming off of it. And if you've got 10, 15 customers on there, they could have this plus a lot more. So this really doesn't impact the final results of the high-cost areas because it's that capacity that's been installed out there is well beyond the capacity that's going to be utilized. The business take, we have the capability in the model to vary take rates by density, actually by census tract if we want it, so that you give us what is the percent of active customers who are going to take broadband service. We've set it to 90%. We also have the capability in the model to actually factor in competition. So we could factor down the take rate in a cable served area by recognizing that there's competition there, which would then, we assume it's an equal distribution of customers. But this capability exists. It's not used right now. It has been set to 90%, which is this value here, and it does not vary across the country. The CapEx, which are the investment inputs, this was developed by us based upon inputs provided by the coalition. So each coalition member, or most coalition members, provided to me the cost of various items of plant. So how much does a 25-pair, 24-gauge cable cost was provided. What we did is we looked at those inputs and came up with an average or regressed value, some value that was representative. There are issues in looking at multiple providers because multiple providers do different things. One provider on the distribution terminal expenses it. Or it doesn't expense it, it is captured in a factor, so they have no cost associated with the distribution terminal because it's considered minor material and they don't track it. So when I get a distribution terminal cost from one provider, it's zero. However, other providers track distribution terminals. Those are the pedestals. So given the fact that I also asked for factors from the providers, I had to use the zero numbers and the other numbers in the averaging so that in the end, my investment averages were consistent with my factor averages. Because on the factor side, I had to come up with in-plant factors, labor factors, shipping factors, all those things. They had to be consistent, so I had to use all that data. That input, all these inputs have been released publicly, so you can get these off the CQBAT site. They are a public document that you can look through. When you look at that table, it's got about 15 tabs. This is just the end result of that. There's a tab on there for copper plant. There's a tab for fiber plant, and one for DSLAMs, one for drop. There's a factor tab, a structure labor tab, all broken out to match what the coalition, and if I'm daring enough, so in this we have customer premise material, we have copper material broken out by the type of plant. So how much is it for drop per foot? Conditioning, if we were going to use conditioning costs, the NID, the various types of cable broken out between 26 gauge or 24, 26. We have 19 and 22 over here. We assumed in the model 24 gauge, so this is what we use. We come up with an equivalent 25 pair cost ratio, which I'll show you later on why we do that, but this is the cost used in the model, and it's broken out by the type of cable. So this table goes on for quite some time. And then we've got FDI terminals down here. I'll just open up one other one. On the DSLAM table, we have the cost of a DSLAM. 3 different sizes. So this size 3 handles anywhere from 0 to 48 customers. Its fixed cost is $8,370 for the cabinet to shelves, the power panel, common equipment. It's tied to the plug-in channel units down here on that $8,370 piece of plant. This is just the material cost. It already includes the plug-ins to provide the service, so there is no additional plug-in cost. When you get to the bigger DSLAM systems, this one goes from 97 to 768. This has multiple shelves. On those shelves, you put plug-ins to provide the service. And that, we have a separate cost for the plug-ins. So these are the inputs into the CapEx workbook.
Jim?
Yes.
So we never want to stand between people and lunch. So we're approaching Q&A time.
Oh, okay.
I know that you're in the middle of a long run of the different inputs, so maybe at the end of CapEx we can take some questions. Is that fair? Okay.
And in the end, this all gets boiled down into the input. So a lot of the logic on the CapEx side is actually captured in this workbook. And if you're up for it, you can look through. It breaks it down into the, this drives the annual charge factors, and I'll go through this structure later on. But it really boils all that input into what can be input into the model. So if you look at that CapEx workbook and you have questions, let me know. If you're wondering how we map the CapEx items, so all the various pieces of plant, to what goes into the solution set, I provided here just a nice simple mapping of, if you see what we call Node 4 copper cable investment, what goes into that? Well, it captures the ONT, the NID, the drop, all get categorized into that. And this is a mapping that is controlled by that CapEx table. The CO size adjustment is another user input that you can adjust the purchasing power. And we broke this into copper and fiber so that you can control it separately. And then broke it down into the sizes. This is small, medium, large. This is extra small, extra, extra small. And you go Y, Y, and Z because we only had one character field to use. So that's Y, Y, and Z. OpEx was supplied by us. We developed it. It was based upon NECA and ARMIS information for the most part, and public reports. The coalition members did provide to us information that we use for validation purposes, but for the most part, the information comes from a 5-year review of NECA. And I'll walk through that in detail tomorrow. And that tomorrow as well. The plant mix was provided by the coalition members, broken out between distribution, feeder, and inner office, then broken down between area, what percent is aerial, buried, and underground for the various densities. So we have that table in there. You can control that table. This drives the determination of the type of cable on every route in the network. It's an average basis, but it drives that. So if we're in a rural census area, we may use this underground mix, but if we go into an urban portion of that same wire center, we may have a different mix to try and capture that reality that you do use more conduit systems in an urban area.
Jim, why don't we pause here? I know you're on a roll. I hate to break that up, but let's pause here, see if people have questions. If not, maybe we can sneak in another couple slides before lunch.
Yeah.
But any questions?
Jeff Reynolds. Jim, this node concept in the topology is, seems to be where you kind of break the costs apart. Is node 0 where that router hits the cloud? Is that?
Yeah, I'll have a slide later, but node 0 is your central office.
Okay.
Node 00 is the kind of tandem point of interconnection with the cloud that we assume. Node 2 is your DSLAM. Node 3 is your pedestal. Node 4 is the customer.
Okay, thank you.
Luis Reyes, FCC. So 2 questions. And I know this is probably a big picture kind of thing, but regarding the cost estimates that we'll be able to see in the solution set, right?
Yes.
You're ultimately giving us a model, right? So you're, in a very general sense, you're estimating this parameter that is the cost per customer.
Correct.
Right? So my question is, do we, as the users of the model, get a point estimate, or even better, can you give us a range of what costs could be like? Or even better than that, can we get a density?
What we do is we come up with the cost of each subscriber, one value. You can run multiple scenarios to kind of get that range of what it could be based upon different assumptions, but it's a deterministic model that comes up with one value per subscriber that we roll up within the result set to a census block level. Certain users can see the census block results. Then those are further rolled up into census block groups and then into the results that show up on the reports.
All right. Okay, but then one set of assumptions gives me a 1 point estimate.
Yes.
Okay.
Yeah.
The second question, and you may have gone over this, so I apologize if this is clear to our audience, but can you vary the business stake in your solution sets? Like, this is something that I can do. I can make different assumptions about the business stake, the number of customers that are being served potentially in each region, and then get results on the basis of that?
Yeah, you can. The current take rate that we have on the business side, you could put it in a different one by census tract or by, I think, even county. So we can vary it down to that level. We can also try and work into competitions to get varied competition rates, but right now it's just one single number. But you have to make separate runs with those assumptions to get the results out.
Okay, thank you.
Susan Lee, FCC. If I recall correctly, you can filter on cable served or unserved or telco served or unserved towards the end of your 16 steps.
Correct.
And I understand that sharing is something that can move the results of the model. So I'm wondering whether the fact that the filtering of served and unserved happens towards the end, will that impact the sharing calculation?
There's 2 approaches to doing the modeling. One is to assume we have to build an efficient network, and this is what the provider builds. And we're just trying to identify the pockets that qualify under the plan. So we have that network designed, and we don't care about how cable impacts the network because I still have to build the network efficiently. So that's one approach. The other approach is, if I've got existing plant, I want to build incrementally off that existing plant to recognize that some of that stuff may be routed a certain way and it exists and you're going to go back. The approach we've taken is a greenfield view of the entire wire center. We build an efficient network in the wire center, and then we filter the cost out. So the sharing does not get impacted in that. We still share the fiber back to the served area in the same manner as we did to the unserved area before the filtering.
And can you give me a sense along your 16 steps, where does the sharing get calculated roughly?
Sharing gets calculated actually in step 00. It's in the network topology, and I'll walk through actually how the sharing works so you can see the logic that takes place to see whether you agree with it or not.
Okay, thank you.
Hi, Bob Loeb, Roca Loeb Sulzer Associates. When I was looking at some of your outputs, I noticed that census blocks could fall in various categories. In other words, you have 3 cost categories: below 80, between 80 and 256, and above 256. The same census block in a number of instances, wasn't the majority, but in a number of instances, fell in 2 or in sometimes 3 of those categories. So therefore, I'm wondering, what is the smallest unique area? Is that your node 2 DSLAM? Would that be unique? And that's for the copper. What is the smallest unique area in the fiber design?
So on the copper side, the smallest unique area is the census block. It's serving DSLAM, and the wire center it falls into. So starting at the top, a census block can be bifurcated by a wire center boundary. So one provider serves a portion of the census block, another provider serves the other portion of the census block. So that's your first bifurcation. On bigger census blocks, where the roads are broken apart, you may have one DSLAM serving one set of customers and another DSLAM serving another set. So you'll get a breakout by census block DSLAM is serving, which is the node 2 and the service area. On the fiber side, it's the same service area bifurcation of census blocks, along with the fiber splice terminal that serves the census block.
The splice terminal, is that where you put splitters? What is the splice?
It's the splitter. I'm sorry, the splitter terminal.
The splitter terminal is the smallest.
Yeah.
Okay. Then my second question is about your brownfield. When you create a brownfield, you're essentially creating your underlying cost pro model and then determining part of that model would have been brownfield.
Correct.
Right. Rather than going out and saying, what does the carrier currently have built and where any location is? So it's not a brownfield from the point of view of what's there.
Correct.
Okay.
It's a brownfield estimation on a forward-looking basis. Yes.
A real simple question, where you've essentially randomly allocating business and households along serviceable roads. Have you done any analysis at all as to how, on average, that tends to under or overestimate costs?
We have. We've actually we do a lot of client work where we actually have customer locations that we geocode. We've run the network with that, and then we've run networks where we do a surrogation of all the data, and it's typically within about 5% typically, within 5 to 10% typically.
Is it plus or minus, or is it always lean one way?
It varies. Mark, do you?
It varies, and it really depends on the rurality of the area. Because as you become more rural, it's more likely that nobody knows where that customer location is unless you site it with, an aerial kind of thing, and you know what is a house versus a barn, what's somebody actually living in. So the estimate widens out, and I would say in a rural area, our cost probably gets closer to the 10 side rather than the 5 side. So, but I could make a pretty good argument that in these rural areas, it's very difficult to find out who's living anywhere anyway, and what the actual habitable structure is, what the actual business structure is. We've been fighting this problem for a number of years, and we've still not found a very good source of actual living unit locations and actual business locations in a more urban area, in a more rural area.
But there you're talking about the boundaries move, the plus or minus range moves as you move, gets wider as you move to more rural areas. Is it, though, still essentially plus or minus and equally in both directions? Your estimates aren't biased.
Is it equal in both directions?
It's when we look at a total. So we will take a state from a client, run a surrogation. The state on average is 5 to 10% different. Each individual wire center, we'd have to look to see how that varies, and we can check that.
I'm not sure you answered my question.
Probably brought
I'm
up
not
additional
concerned
questions.
about how it moves to the. I'm concerned about whether the error terms are equally likely to be 5% understated or 5% overstated, or whatever the correct number is for whatever unit of aggregation, your geographic unit you're using. Did I make myself clear?
Systematic bias, in other words.
Well, the problem is you don't know what you're measuring against. You don't know where that location ever truly is. We don't have an objective source of all these locations. So when we can do it, we do the analysis on an area, and we come up with that 5 to 10% range. We don't have a measure of where everything is to do the which side.
We have an estimate. So when we get the customer data, it's an address data set, but your geocoding never gets you to 100% accuracy on it. Rural areas have a worse geocoding rate than urban areas. So what Mark's getting to is, while we have a data set of the customer locations in rural areas, some of those are yet surrogated because we didn't have a good geocode. So we will fill in. So when we do a client study, we take their address data, which is not Latin long, it's just address. We geocode those to get a Latin long on the Earth's surface. Typically, we get about 95% of customer data geocoded to roads. We will then fill in the other 5% that didn't geocode, along with estimates given the customer data we have now. You only have 30 to 40% of the customer locations. We now got the problem of we have to look at alternative sources to bring in. So our studies are kind of polluted studies, not a true measure of what you're trying to get at.
Okay, but that's the world you live in, right? I mean, I wasn't expecting, if you knew the right answer, we wouldn't be doing any of this modeling, right?
Exactly.
To start, let me just ask the question one more time. To the extent that and to the extent that you have tried to tie back your random modeling to actual data, to the extent that that's possible, is there any systematic bias that you've observed? Maybe the bias is less or not at all in some types of locations than others, but is there some kind of systematic bias that you've observed or not?
And let me get back to you. I don't have a good answer right now.
Thank you.
That's why I'll have to look at it.
Why don't we break for lunch now? We're going to continue, I think, with the model inputs. And so if you have further questions, I think you have an opportunity to ask them. It is now just a couple minutes past 12:30. We will kick back off here at 1:30 promptly, if all goes according to plan. For those looking on the web, we also have trouble sometimes with our website internally, but I've been told and see that we do have these presentations now loaded on the web on the event website. So if you go to fcc.gov, click on the event website for today, you will see two presentations by CostQuest, one for today, one for tomorrow, and the one that ACS will be presenting later on today. Thank you. So we are going to get started again after lunch. I hope everybody was able to find something tasty to eat. Jim continues to pace slightly ahead of what's on the agenda in a way that I'm finding quite unnerving. But we're going to continue right where we left off before lunch, talking about some of the input tables, starting with plant mix, and go from there. We had brought down a few more of the there are actually two sets of files, both available online for the CostQuest presentation. We brought down a few more of the first half ones. We are printing more of the second half ones, so those should be down shortly if you don't have one. But Jim is going to keep on rolling through.
Thank you all for coming back. It's nice to see everybody. And I am from Cincinnati, so the y'all is kind of okay. We're northern, but we're near Kentucky, so y'all comes out quite frequently. I just want to point out some potential issues that were in my prior discussions. Sometimes I say things I don't know what I say. So during the break, some people said, you might want to correct some things. So first on the depreciation lines, those actually are from a much earlier period. The 99 order was a reaffirmation of the numbers that had been used prior, and many of those things actually date back into the early 90s. So they are quite dated, the depreciation lives in that FCC order, but the last document that I think has come out from the FCC was that 99 order. The other thing is on where our network starts and ends, I was kind of questioning if we include the last router that connects to the cloud, and I still need to verify, but I'm 99% sure we include the last router that touches the cloud in the cost. And then the last one is just, it gets to the questions on, the whole testing of our random customer locations and accuracy of this information. Now, if we had a 100% accurate data set of customer locations across the U.S. with their exact latitude and longitude, the model would produce 100% accurate results of the network to get there. The problem is there is not a data set that gives us 100% accurate locations of each and every latitude and longitude in the U.S. So we fall back to, in our case, we're using census block, which is apportioned to roads. We think it's an unbiased approach because it's randomly placed along the roads within the census block. That said, any particular census block or the costing of any particular customer within the model, while we can produce cost by customer, it's not necessarily a representation of the cost of that customer within the census block because we're not quite sure where that customer is. So I just want to, we can be as accurate as the data we get, but if the data is somewhat questionable and we're doing random allocations, we believe the cost rolled up by census block to carriers is good. It's when you get down to census block or below census block. Am I 100% sure that that's the right number? No, but on average it's a good number. So I just want to clarify some of that. So now let me jump back to plant mix, which is where I kind of ended. Again, just to refresh you, I'm walking through all the inputs into the model. These inputs are available online. The coalition released the data set that was used in CQBAT in a public format. It's on, you can download it as a link from the CQBAT online website. And it has all these tables in it. So as I go through this, I'm just trying to give you a background of the tables, where they came from, and how they're used. If you have questions about specific inputs, I'm not necessarily ready to kind of answer some of those questions because some of them are not necessarily my inputs. They were provided by the coalition. So where I ended up was plant mix. Plant mix guides how we deploy aerial, buried, and cable plant within the system. It is based upon what is existing in the network and what the providers gave to us. And we do try and come up with plant mix specific to each wire center based upon the density and the breakout between distribution feeder and inner office within that central office. The next table is called the P-tax table, and it is the property tax table. What it is property tax is the levy of taxes on the investment owned by the company within that state. It varies by jurisdiction within a state. Property taxes are captured in the G&A factor that we have in the OPEX side. What the property tax table is, allows us to modify that G&A factor for the differential in property tax rules and rates amongst the states. So this will adjust that G&A factor up or down based upon the state you're in. So this is not necessarily the property tax rate within the state. It's the differential between the nationwide average rate and what we see in that state to adjust the G&A up and down specific to that state. The regional cost adjustment table. Again, we provided this table. It is sourced from RS Means. RS Means is a construction, outside construction specialist. They provide books that outside crews use to get do their estimation from. So it'll give you cost of potential pieces of plant. You can actually find, I think, telephone poles in it. But it also has labor rates adjustments across the U.S. This is what we used as the best source that we could potentially, or we found, to capture the differential that, Hawaii costs more because of the shipping over there, the potential labor cost differential in Hawaii versus in Kentucky versus in California. Those are all captured in this. It's at a ZIP 3 level. So for each census block, we capture the ZIP 3, which is the first 3 digits of your zip code, the ZIP 3 level, and we apply this regional cost adjustment to the CapEx input, so both the material and the labor cost. It indirectly impacts the operational cost. We didn't want to apply it to both because it would have been a double count. But as since the operational costs are a factor, if we adjust the CapEx up and down on like the cost of pole maintenance, the pole maintenance expense will go up and down based upon the regional cost adjustment going up and down. And that's how we get the regional cost adjustment into the OPEX side. Here's a sample of the table. It is sitting out there that you can pull down the whole thing, but just let me walk you through some of the inputs. And had I thought about it, I might have left Puerto Rico off here because it potentially is an issue. But what this says is this is the adjustment rate. A 1 is your costs are on average equivalent to the U.S. If it's above 1, it means your costs are higher than average than the U.S. If you're below, it means your costs on average are below. So as you go through here, we'll hit to San Juan, Puerto Rico. So we've got the 4 zip code breakouts in San Juan. And this is just showing that on average, the labor cost differential between San Juan and the national average of the U.S. it's 22% lower. So when we develop the cost for San Juan, we take the material cost and labor cost for that plant, multiplied by 0.78 to reflect that the cost to install that will be much less. However, when we get to the Boston area, Boston is at 118%, or it gets an 18% bump up. So this is how our attempt at trying to capture those regional cost differences in building the plant. The state sales tax is to capture the cost that is incurred as you buy material. You will have a state sales tax applied to that material cost. In certain states, other states may not charge any. In Delaware, there is no sales tax on some of the plants, so there is a zero factor. But what we do is we take this rate, we apply it to the material costs that we get in the model, so that that material cost is then adjusted up. Residential take rate. Much like it's the same table as the business side, but we allow you to control residence and business separately. Right now, this has been set at 90%, so 90% of the housing unit locations that we identify have broadband service. There is one thing that came to me probably a few weeks back is we use housing units in the model. So a 90% take rate of housing units is probably 100% take rate of households. Hadn't thought about it when we originally did the model, but it's a fairly high number because households, from the census definition, are populated housing units. Housing units are habitable structures that exist in the U.S., and there's typically about a 5 to 10% difference between the two. So in effect, we are at 100% take rate on the residential side. I put this chart together at one time because someone asked me one time, who cares about take rate? Why does it matter? I said, well, it matters a lot from what you have to deploy. And it matters a lot from if you're going to use active customer locations as your divisor to come up with the cost per unit, you can have dramatic influence on the costs that come out. So what I did is I just threw this example together fairly quick, which was you got a central office, you got a street that is in the cable served area, you got another street that is in a non-cable served area. The darker households are those that do not take your telco service because they're in a cable served area. They have got other potential providers. Out in the unserved area, you've got, I've assumed, 100% take rate out here. So we've got all the customers out here. So what I did is I just simply modeled the cost of that deployment in this area along with this area. The central office, I put $100,000 worth of cost. The cabling, I put $10,000 of cost for this fiber that runs out to this DSLAM. I put the DSLAM at another $10,000. This cable out here is $20,000, and this last is $10,000. I look at, part of the cost analysis exercises, we got to identify the best driver of that cost. What is it volume sensitive over? So the equipment in the CO, which includes routers, termination gear, whatever it may be, I said active customers is the driver for that. This fiber, to me, is not really driven by customers per se. It's a much higher level. It's a step process. The fiber is driven by the fact that I have a DSLAM location I need to hit. So this fiber is driven by the number of DSLAMs. The size of the fiber cable is sized by how many DSLAMs I have to serve downstream. I can run a 6-strand fiber, a 12-strand fiber, 24-strand. If I'm doing fiber to the prem, I'm up to 784 strands in a fiber cable. That is all driven by the demand downstream. How many things do I have to hook up? So in this simple exercise, I got 2 to hook up, so this is sized at potentially 6, 12, 24, whatever your engineering criteria is. The DSLAM, I just made it all volume sensitive on active customers. There's actually multiple cost drivers here. One is the location of customers. The fact that I have a customer out there drives the need for the DSLAM. The count of customer size, how big that DSLAM is. This last fiber, again, driven by DSLAMs, and this last DSLAM by active customers. So I go through and I count up the cost drivers. So I've got 10, I've got 5 active customers here, 5 active customers here. I divide this by 10. This DSLAM fiber cost I divide by 2 because I have 2 DSLAMs attached to it. This divide by 5. And in the end, let me jump to the numbers then. So in the cable served area, my cost is $13,000 for that cable served area when I apportion things out. So I'm spreading. But I'm spreading based upon what I think are the cost drivers of the plant. This last section is $17,000 because it includes the cost of this piece of plant as well. I'm just thinking something doesn't look right, but let's just go with that. Yeah. So that's with take. So I'm dividing the cost by the active subscribers because in the business sense, I'm only able to recover money to cover these costs from the people that are going to pay me money. So I can't go levy a tariff on these unserved households to give me money. I've got to be able to cover this cost by the 5 active subscribers. So this is kind of the working TELRIC view of the world. I then jump down to say, okay, let's say take doesn't matter. Let's just run everything at 100%. So now instead of dividing by 5 here, I divide by 10. This gets still divided by 5. My cost down here changes. It drops down to $8,157. Huge change. And this 50% take rate is not a made-up number. This is probably high for many of the phone companies right now in their competitive areas. Because in addition to the cable served, you've got wireless competition. I think wireless-only households is well above 30% now across the country. So potential take rate here is not 5, it may be 3. So this number jumps up even more. But you can see that take rate does matter in that end result. So this is from a costing exercise if you're trying to do pricing, trying to understand what your rates need to be. From a universal service perspective, what this will do is you potentially make you raise the benchmark, lower the benchmark because you've got a fixed allocation of money, $1.8 billion. It's a balloon exercise. I'm going to squeeze, it's going to come out somewhere else. If I raise the cost of everybody, I'm going to spend that money quicker, so I got to raise the benchmark even higher so that I can get that triangle. If you think of the triangle, I need to manage that triangle down to $1.8 billion. So in the end, does this impact the results? I can't tell you. I didn't run the exercise to kind of look at that, but it could potentially be run. So with that, let me just ask if there's any questions on the inputs before I jump into. There's a question over here.
You mentioned that you had competitors in this.
Ramesh at the FCC here. In terms of the number of competitors, that was one of the toggles that you had. Would that be something that you'd account for because you're taking the take rate there, but that's assuming if it's 100% take rate for the one carrier that's in the marketplace, but if you have 2 or more, how do you account for that component piece of it?
What we can bring into the model, or a model that's deployed, from the National Broadband Plan, we can identify the potential number of broadband providers in an area to actually come up with a true count of competitors. You could use that, but it then comes back to once you find the count of competitors, say there's a fixed wireless entity there, a cable company and telco, you got 3 companies. We have no more information to understand if it's an equal take rate or not, so we would just come up with a 33% take rate in that. It's actually on a census block basis because the national broadband data comes in at the census block. So we could do some of that analysis down to census block level.
But your cost would increase in that case here.
It would increase. So yeah, what you'll find is potentially your high cost areas could be the areas where you actually have competition. You have much higher cost on a per active subscriber basis than out in your rural areas where you've got potentially 80 to 90% of the customers.
Larry Zhang from USAC. My question is for the company size, is the model sizing at a holding company level or at the individual carrier level?
I was hoping someone didn't ask that question. It's holding company level typically within a regional area like in a state. Because we classified Windstream as a mid-sized company even though they have more than 1 million lines. AT&T and Verizon typically have states that have over 1 million lines in them, so we put them in the large. All the other carriers in the coalition we put in the mid-size because most of their operating footprint are well below 1 million within a state. And then when we looked at the small carriers, we looked at a holding company level because typically they're within a state. So it was kind of a state sizing exercise. If there's no other questions, I'm going to go into middle mile. And I do middle mile first. Some of you might say, well, why are you doing middle mile? I'm going to go through the loop portion and the middle mile portion of the network. I wanted to make sure I covered the middle mile first before the next presentation because I know in Alaska, middle mile or the backhaul, the transport is a bigger issue. You know, we assume it's a fiber-based network connecting things together that go back, and I just wanted to get this out before the next discussion. Then I'll jump back to the loop network. So this is actually a diagram we put together when we were working on the National Broadband Plan, but it captures the middle mile approach. Basically what you have is you have your customers down here connected to a remote terminal. That remote terminal connects up to a node 0, which is I should have put our node definitions earlier on in this presentation, but the node 0 is the central office. We also call it a POI, point of interconnection. We also call it a SILI. We also call it a Wires. We also call it an exchange. There's probably 30 names for what this is, but we decided let's come up with a unique name called node 0. That node 0 is then connected to a parent site, and in this exercise we chose regional tandem locations. And our unique naming structure, actually when we started the naming structure, we started at 4 and we said, oh, we're going to just go down to 0, so that's why we got 0. Well, then the tandem is sitting behind the 0, so it's node 00 in our creative naming process. And then you potentially can have regional tandems interconnected together, which gets you up to kind of the cloud, the router on the cloud somewhere. So when we talk about inter-office, middle mile, transport, whatever the term you want to use, we're capturing the connection from the central office to the regional tandem within, I want to say a state, it might be a LATA, but I can verify that. If there are multiple ones, we'll ring them together, but this and then this cabling here, we capture this cabling here, and then we capture the routers that are in these points of the network. There is potentially some DWM gear. We did not capture that we stopped at that point in the network. We got it up to here, and that was left out of the network. So the middle mile connects the central office with the cloud via connection to the point of interconnection at the tandem, I should have read my slides, within the LATA. So we start with identifying the nearest access to a Tier 3 internet gateway for each central office. So our central office is the node 0 or the POI. The surrogate for this Tier 3 internet gateway we took as the regional access tandem within the LATA. The regional tandem locations were pulled from LERG based upon feature D accessibility in LERG 9 for that regional tandem. So we were just trying to find a point that we could use as a surrogate for this Tier 3 internet gateway, knowing that we didn't necessarily have a good list of these Tier 3 internet gateways. What we then did is we developed the middle mile as the connection from the node 0, the POI, up to the RT. We did that let me read this first. The assumption is that the internet peering point is located at the RT on the RT ring, meaning that if you get the model up to that RT ring, the customers have connection to the cloud. We do the middle mile process on a state-by-state basis. We look at all CILIs in the state, which are the central offices. We home them to their closest RT, so we're not necessarily looking at company ownership here. We're just looking for the nearest regional tandem in the LATA. The regional tandem location is assumed to be where the internet gateway is located, as our assumption. The CILI locations are then routed to other CILI locations with the same RT parent using a spanning tree approach. So these aren't necessarily rings. I believe on the costing side, we double the cost to reflect that there will be a connection of the rings. But this is a way just to connect the rings and come up with an understanding of that distance of the central offices. And in the cases where we have multiple RTs within a LATA, all the RTs within the same LATA are put together on a ring to ensure that we have, and we use a shortest ring distance to connect those things together. So this is just a simple example, a stick diagram that shows it. So these are the regional tandems. When we connect these together, we look for the shortest pathing to connect those things together, and then we will connect the central offices up to those regional tandems. We will then capture the cost of the fiber for all those regional tandems and the CILI connection to the regional tandem. The distance of the RT ring is attributed to each CILI on the ring in proportion to the number of service locations at each CILI. So if I go back to this ring, how do I apportion this fiber cost out to the three that are connected back through the network? We do it based upon the number of customers within each. There really is not a cost causation case for some of it. I mean, you may size or need additional fibers because the number of customers increase. You have to go to additional equipment. So there's a loose fit to cost causality. But we spread it based upon that. For the electronics, we place an Ethernet switch in each CILI. So as you look at this, we have an Ethernet switch here. So as the DSLAMs, if you're doing a fiber to the 12K build on copper, the DSLAMs are routed back to an Ethernet switch like a 7550 or 7550 if you're talking about Alcatel-Lucent plant. We assume sits in here, or we assume it sits to handle potentially multiple switches. And then we have a broadband router in these. We've got paired routers, and those are like a 7750 if you're talking Alcatel-Lucent. If you jump to that last one, this one may be the most contentious thing about middle mile. For the route-related cost, the electronics we can identify are directly attributed to broadband service because we're putting those 7750 routers in for broadband service. When we look at the route-related costs, so the fiber and the structure, we assign only a portion to the broadband network because we assume the network is built for multiple purposes. And then this becomes the complexity of trying to build these models, is that network also carries dedicated data demand. I sell private line services, special access services that have to transmit over the inter-office network. So I size portions of that fiber for that inter-office network. So what we did is we said, there's really not a cost-causative approach. Let's just assume we're going to assign a half. People can come up with better measures. We chose a half. In the National Broadband Plan, we used a third. And you might ask why. In the National Broadband Plan, we assumed there was three networks. There was a voice-only network, which was circuit-based switched. There was a data network, and there was the private line network. So three networks traversing that network, we split it three ways. In this one, since we are deploying a fat pipe over which voice, video, and data suffice, we've now reduced the number of overall networks going over that inter-office network down to 2. When we run middle mile runs is run by us. We populate into the model a table that captures everything about that middle mile connection. So it tells us how long the length is to the node 0. It tells us how much cable to associate with this, and I'll walk through all these columns separately. It gives us the node or the normal terrain type, because all this was in terrain. There's actually more columns to this. I just pared it down. What density it is, how many node 0 working lines, so this is how many customers are out of that central office, how many customers are on the whole regional tandem ring, how many working lines are in the whole LATA, so that we can then use these numbers to apportion cost out. So you might say, how does this test out? So we did do some testing. And most of the testing was on when we did the broadband, the BAM model for the FCC. We looked at what the monthly costs are coming out of this. Because sometimes carriers don't own their middle mile. They actually pay lease rates for that middle mile. We assume that if we built the proper TELRIC-based costing methodology for the interoffice, it would approximate the cost that would be incurred by those that lease interoffice facilities as well. So what we did when we worked with the FCC in this effort is we took those monthly costs out for a sample set of data. They compared it to some tariff rates, and lo and behold, they were within a reasonable range of those tariff rates. If you look at what we've got in CQ-BAT right now, the average monthly cost for the node 0 component, so that for that interoffice, is around $3,000 per central office. It ranges anywhere from I think around $200 or $300 for urban areas, up to well in excess of $30,000 out in the rural hinterlands. So the numbers didn't seem out of line as far as estimating what that inter-office cost is on a monthly basis. Any questions on that? Yes.
Jeff Reynolds with Reynolds Schulteis Consulting. Jim, how did you size middle mile? Is there any oversubscription or any of those kinds of rates baked in there?
No, we size the fiber with either I have to go back and look, either a 48 strand or a 96 strand fiber as the assumed size of the fiber for all interoffice routes. And then on the electronics, we size the electronics specific to the demand coming from the central office to know how many Ethernet switches are the 7550s to put in each central office, or if we could aggregate those up. That was all based upon the demand from the loop side up to that. And then the broadband router was based upon the number of 7550 connections. So the router on the cloud has so many ports you can terminate on it. We counted up how many of the central office thingamajigs that we were sending up there to consume those ports. I couldn't think of the term, but so that's how we size the electronics and then the fiber.
Okay, thank you.
You're welcome.
Thank you in advance for answering all of my questions. You actually made a comment in the previous Q&A session that I'm still processing because I thought it was interesting. You said that you can observe higher average costs, and correct me if I'm wrong, in areas where you have more competition. Can you elaborate on that? I find that very interesting.
Yeah. So what you have in this particular case is if both of these areas had 5 customers, so let me try and figure out how to do this best. That's total cost. If you assume that there are only 3 customers in this census block, what happens is you're taking this total cost, and instead of spreading it out over 5, you're now spreading it over 2 customers on a per active customer location basis. Your divisor keeps continuing to get smaller, and at some point, this goes from $13,000 at 5 customers to potentially about $20-some thousand with 3 customers. which now exceeds this high cost area out here that we've identified because your assumed take rate. It all comes down to the divisor, which is an issue, a policy discussion. What do you divide the total cost of this area by to determine the cost? What the unit? And it's a question that I can't answer. So.
Thank you.
This goes back to historical reasons. So the existing model does it based on per active subscriber. So the take rate drives the number of active subscribers. If you have lower take rate, you're amortizing your fixed cost over a smaller and smaller number as the take rate drops. If, on the other hand, you parameterize based on the number of homes passed, then the take rate doesn't have that same effect because you have a constant, in this example, 10 homes on the left-hand DSLAM and 5 homes on the right-hand DSLAM, independent of the take rate. So an open policy question as to whether you would want to parameterize by cost per sub or cost per homes passed.
Correct. Well, you've made it through my first 160 slides. Now let me open up slide deck 2. And you know it's bad when it takes a while for it to open up. So, here we go. So here is, actually, it's my funnest part of the presentation. It's just talking about how we design that local loop network. So the first part of this presentation, I'm going to go over that network topology development. How do we develop the structure needed on the local loop side? Then I'll talk about the differences between fiber to the prem versus fiber to the DSLAM, which are the network topologies within CQBAT, some sizing assumptions, the interplay of the user inputs as we do this, and then how do we how do we share the cost out? So to develop the CapEx, and this is on the loop side specifically, I went through the middle mile, so now we're on the loop side. The demand information for the entire U.S. was captured. From that demand data, forward-looking network designs were deployed. So we determined the locations of the serving nodes, so the DSLAM, the fiber node, the fiber splitter, depending on the network topology. We also determined the routing to serving those nodes. So, and in that, we captured the shared nature of network cabling, that as you run down a street, that street may be serving 5 or 6 different DSLAMs, so we have to apportion that cost out. The network data was then mined to develop attribution of nodes and routing to each census block. So we developed this big network. We push the cost, all the cost out to the cost of a census block. So think of it as we're coming up with the cost of a customer. So we need to know all of the costs that customer incurs all the way back to the central office. We roll all the customers within a census block up to the cost of that census block. So we're pushing everything out to the census block, and I'll walk you through how we do that. We then come up with the CapEx for the nodes and routing, and then we apply factors. Cost people always apply factors. We like factors. They capture everything that we can't get in detail. So we got factors for engineering, for tax, for warehousing, all that type of stuff. And then, factors weren't enough. We made some final adjustments to make sure the costs are representative of the company size, the density that we're in as we go through it. So we get business data and census data, which gives us, if you saw it over there, this is what we call in the model our census block master file. It is our repository of every piece of information that we know about the census block. So it captures the demographics, the residential household counts, the business locations, the number of employees. everything we need to know. That is then what is fed into the next step of the process, which is we need terrain data, road data, and other information that we run through Cost Pro, which is our loop model, along with that census data to give us, and then we farm it to give us our CostQuest landline database that sits within CQBAT. We did it this way, and you might say, well, I don't have the option to rerun the network topology. And I say, yeah, you don't have that option. And I'll tell you partly why. Is one, it takes about, as I said earlier, about 5 days to run. And we parse that out over 6 to 10 machines to get it to run in 5 days. So it's a heavy-duty process. And hopefully when you see the pictures, you'll understand why it's a heavy-duty process. So it's not something that we can necessarily put out on a user platform, and if you're only using one machine, check back in 3 weeks, and we might have a number for you. So what we do is we pre-process the network topologies, which really don't change. If we have the assumptions correct about it's a 12K design, 12K is 12K, and I'm trying to find the customers within 12K of nodes. That really doesn't change. What I do, and how we've tried to make this more dynamic, is we moved all the costing into CQBAT. It's just coming up with how many feet of cable, how many splices, how many feet of trenching, how many DSLAMs do you need is done in this network topology deployment, and that is what's captured in this database. We then do the middle mile, which I walk through, and that gets mined as well to populate the CostPro middle mile database. We then bring in the material prices, the EF&I, which is engineered, furnished, and installed, so it's the labor component and the factors. We apply plant sharing, which I really didn't discuss because I don't want to say it's hidden, but it's kind of hidden in the CapEx workbook. There's a plant sharing table. There's 4 plant sharing tables in the CapEx workbook that maybe I should hit right now real quick. Plant sharing is a fairly contentious item of discussion. I talked about the poles. A pole is not necessarily 100% telco owned. If you look at the buried trench, is the buried trench 100% associated with the telephone company? If you look at the HCPM inputs, there was an assumption made that as that trench was open, there would be other providers ready to kick their cables in the dirt or in the hole or in the trench at the same time, and therefore the cost of that trenching can be shared. Many times that cannot happen because the timing of construction is different between the providers. But if all providers were building a forward-looking network at the same time, it could potentially happen. So that is the plant sharing table on structure cost. And that's really what comes in here. We want to know what that sharing is. The coalition provided those sharing numbers of that are in the CapEx workbook. There's also concepts of sharing between feeder and distribution. If I'm running a distribution network that runs down a street and a feeder network that runs down a street, I potentially can share the structure. We've got a structure sharing table specifically for feeder distribution sharing identified. And not that that was not enough, there's also a third network that you got to worry about, which is the inter-office network. The inter-office network connects, it's the middle mile, it's not the feeder, it's not the distribution. You actually have 3 potential networks there. So you have a sharing between the inter-office, the feeder, and the distribution, and that is shared by or controlled by a third table. So that is what this is referring to. It was a very contentious issue in the original go-around of the HCPM. It was a very contentious issue in uni proceedings. Depending on which side of the table you're on, it really drove what sharing percentage you liked. And I'll stop there because that's enough. So with that, we also find the capacities and drivers of the plant so that we can unitize the cost appropriately, which gets us to our CapEx inputs. We feed CostQuest and the CostPro middle mile through that CapEx inputs to give us our result, which we adjust by the regional cost adjustment. We apply the sales tax to it. We filter out greenfield, brownfield at that point in time. We hit it with the company size adjustment at that point in time to finally come up with our total CapEx adjustments, which then gets us to the magical solution set. So to get to that network CapEx, the first thing is we have to farm our cost pro model. So CostQuest loop model is used to generate the model topology for two right now, the FTTD 12K and the fiber to the prem 5K. We've also run, when we did the BAM model, we ran additional copper scenarios of 15K, 5K, and potentially a 3K. So we can run these in the background and put them out there. So if there's requests to do an additional topology, we can run those. The one thing I'd like to point out here is I use the term D, and I'll show it later. AT&T deploys what they call their UVerse on a fiber to the node deployment. There's also typical DSLAM deployment, which is you're pushing the fiber out to the node, but the node typically is near the carrier piece of equipment, and it's 12,000 feet out. Fiber to the 12 feet out can't support video services. Fiber to the node, which is typically 5 to 3,000 feet from the customer, can support video services. I'm just using a fiber to the D. It's a fiber out to a DSLAM point, and it's 12K from that. So the nomenclature sometimes gets confusing, but if you just look at the D as a DSLAM, and the number there is the distance from the DSLAM to the farthest customer off of that DSLAM. The 5K is the fiber to the premise, and the 5K designs how far off of the splitter, or the splitter that you run. And typically it kind of correlates with the real distance of a fiber reel. And you typically, from what I've talked to engineers, is they try and design these areas somewhat consistently with some of the copper designs. You don't want too many customers on that splitter. So they try and limit it to about 5,000 feet. We've hit this, and hopefully you know it by now, but I thought I'd repeat it repeatedly. We are doing Scorched Node, forward-looking. The service that we're costing is broadband. The network is built to all customer locations, but not all customers are hooked up. It is based upon that take rate. We bring in additional data so that we can filter on the results. So the network isn't reconstructed. Sharing is not reshared. The network is built as an efficient carrier would build it, and then we filter it. And that's what these are, filter values. So now let me walk through the architectures that we're talking about. This is a fiber to the DSLAM, where the DSLAM typically is 12,000 kilofoot or more from the farthest customer it serves. In the central office, in this exercise, this is a TDM deployment. So in this exercise, let me start out to customer. Customer has a modem in their home. Customer typically owns that modem because it's an expensed item. Telco doesn't typically own that. You have your NID, demarcation point, you have your drop cable. You have your pedestal, which is that green mushroom box that sits in your front yard, or it can be a drop terminal that sits up on a pole. At a building location, they can have building terminals, which you have punch down blocks and connect the cables up. From that, this is then the distribution cable. Engineers and telco people might call it the F2 side. This is copper, because we're still in a fiber to a DSLAM approach. So everything off of the DSLAM back this way is copper. You have your FDI. FDI is a feeder distribution interface. It's also called an SAI. It's also called a crossbox. There might be another name for it, but that's the most popular names. Basically, what it does is on this side is the feeder network, on this side is the distribution network. You have copper cable coming back from the FDI to a splitter that splits voice and data. Data goes to the DSLAM, voice goes to the DLC or MUX system if these customers are beyond 12,000 feet from the central office. You then have fiber coming back from the DLC, which hits a MUX. A central office terminal goes on to if it's of sufficient demand, it will go directly into the class 5 switch on a DS1 traffic stream. If these customers were copper, they would actually hit a main distributing frame and be then connected into the Class 5 switch. The DSLAM is connected to a router. It's typically a gig-E fiber that connects it. It's usually a 1 gig or a 10 gig or a connection point. That router then connects up to the internet in simplistic terms. Now, here is that same network, but this is an IP architecture. So we're assuming you'll see that this does not look any different on this side. We're still delivering 12K of copper to that presence. We still have the pedestal. We still have the FDI. We have the splitter. Actually, we actually don't have a splitter. We just need the DSLAM. That DSLAM then sends the traffic back to that Ethernet switch or the router, which then hits the router on the internet. So it's a much simpler network. The central office becomes a little simpler because you don't have the Class 5 switch there anymore. You don't necessarily need the MDF for these customers out here. We're assuming all customers will be terminated on a FDI DSLAM so that we get that termination to the DSLAM for all customers. And then voice connectivity comes through the IMS platform, or if you're not at a full IMS, you may have a soft switch, intermediate soft switch approach, in which these packets that come back to here go through, I can't think of the signaling platform on the VoIP side. Anybody help me? Signaling? SIP. Thank you, SIP. Yeah, SIP. So you'll have SIP signaling. That SIP signaling will tell, if this is a smart switch, will tell the packets where to go. So it signals up to the IMS platform. The IMS platform says those packets need to be routed to that router. These packets are jumping around, ready to go. They get the signal where to go from the SIP. They run to that next router. So that's your voice conversation, little packets floating around in the cloud that get reconnected, reconstructed, all in a time frame that you don't even notice. This is the fiber to the what we call the node, and I threw this in just because that nomenclature has been used, and I've used it before. But basically, this is a video-capable architecture in which you limit this distance now to no more than 3,000 to 5,000 feet, because at that distance you can get upwards of 20 to 25 megabits into the customer's home, which can then support video capability into the home. You still have the same design over here. You got a near the pedestal. The FDI and the DSLAM all become co-located because what you're doing is you're pushing the DSLAM farther out in the network is basically this design. The voice is then brought back to the MUX and sent back. The IP architecture looks like that. Much simpler, flatter network because you don't need that voice capability on the TDM side. So this TDM architecture disappears, which simplifies the network. And you might say, well, why aren't the phone companies doing this? Part of it is, I've got that switch. I've got this architecture. It costs me incrementally to move to a different architecture. So it's an over time move to an IP architecture, not a flash cut. But if I were building a network today, in my imaginary network, I'd be deploying this, just because it's a much simpler architecture. These are some of the design attributes of that model. So as we look through it, and I'll just hit on some of these, the design capacity per FDI, we said it's 600 lines. The max capacity of a CSA, the carrier serving area, which is the size of the cluster, we try and get no more than 1,800 lines in that. Max capacity of a drop terminal, we said at 6. Max capacity of a NID at 5. Max drop length, we set at 700 feet. On the fiber side, we set it to 500 feet, which I'll show you and I'll discuss that. This is the max capacity per building terminal before we jump into an integrated DLC within the building to provide capability. So if there's less than 400 lines at a location, we will still place a building terminal, multiple building terminals to serve it. Here's the gauge crossover. Is at 12,000 feet because we've assumed we're going to use 12,000 or 24 gauge cable all the time. And we've actually, even though this says 9, we still use 24 gauge. This is the design pairs per housing unit. We put in 1.5 pairs. We used to put in 2 pairs per housing unit, but with the advent of competition, we were able, and we talked to some engineers that they said you potentially could live with 1.5 pairs. There's the gauge, minimum fiber size, maximum fiber size, maximum copper size, and then the pole size. So how tall is that pole? So those are some of the inputs that go into creating that network. Now we jump to the fiber to the prem architecture. This is a I can't think of the term, but there's no active electronics. Passive optical, thank you. Yeah, it's getting late. So it's a passive optical network. Basically what you have is at the customer's premise, you have an ONT, a battery backup capability, so that they have power during blackouts. Inside the house, you'll potentially have a modem for potentially some services, or the ONT may have it integrated in that. You have fiber that goes out to a pedestal. That pedestal is like a fiber splice or a fiber service terminal. These are typically pre-connectorized, so you just snap the fiber cable in. You then have fiber running from that pedestal, and it is a dedicated fiber. There is a single fiber per customer going up to the splitter. So if I've got 600 customers out here, I've got 600 fiber strands coming up to the splitter. From that pedestal, we hit the splitter. The splitter typically is a 32-to-1 splitter. So it'll take the traffic of 32 customers, mux it together into one fiber strand. So coming out the backside, we have one fiber per 32 customers on this side. This is a modularized unit. You put a structure in, and then you've got cards that add additional splitter capability into that. On the back side of the splitter, then you have a fiber coming back to an OLT, which is optical line terminal. That has a termination point per fiber. So there is one point on this consumed per 32 fibers out here, typically, if I remember right. And then if you're in a TDM architecture, what you have to do is you have to peel the packets, the voice packets out of here. You run it through a voice-type gateway that converts the IP traffic into a TDM signal that you pump into your switch. This voice gateway and this switch don't necessarily have to be here. They could be pushed back in the network, but there's got to be that gateway capability to convert it into that TDM signal. And then the data hits the router that goes out to the internet. In the IP architecture, again, simplified on the CO side, this is basically the same architecture here. It hits the OLT. All the packets go through the Ethernet switch out to the cloud into the internet. There is no need for conversion through a gateway to turn it back into a TDM signal. So again, a little bit of a simplified architecture. There is the need, there's a floater OLT up here. The fiber, depends on the provider I talk to, can go out off of that central office-based OLT anywhere from about 10 miles to 12 miles before you need to regenerate. So if you get beyond 60,000 feet, your customers, you may have to remotely place an OLT out in the field to provide that service. Some carriers have decided that fiber is only, and this is in the reality, they only deploy fiber out to the limitation of the fiber out from this, so potentially out to 60,000 feet. Anything beyond that, they revert back to the older architecture because it just gets too expensive to deploy these OLTs sitting out there remotely for these customers. Key attributes on this engineering is the max drop length is set at 700 feet. I'll have to check that, but there was an issue. This was a FCC issue in Unis that if you deployed a fiber network and the drop was under 500 feet, you're okay. If it was over 500 feet, does anybody remember this ruling? There's a 500 foot that you didn't have to unbundle your fiber network if the length of your drop was under a certain distance. So when we ran these models originally, we had this at a shorter distance to fall within that, so that, or it might have been the opposite. If it was under 500 feet, you had to provide unis. If it was over 500, I forget the rule. It's a fun fact that apparently no one remembers but me. We ran the max distance off an OLT to 52,000 feet. The max design capacity of that depends on the person you talk to, what the splitter is called. One company calls it a PFP. Many companies call it a feeder fiber distribution hub, FDH. We try to keep that under 400 lines per splitter. We try and keep the distance under 5,000 feet. The max capacity of that OLT, we try and keep under 100,000 lines. So effectively, there is no capacity. We can keep pumping in OLTs as we need them, as we deploy these splitters. Most of the rest of the rules are fairly similar. And then we do have a distance limitation on the splitters. I've seen the distance limitation change between providers, but typically if you go out to about 30,000 feet, you can do a 32-to-1. Once you go out beyond 32,000 feet for at least a couple of providers, they go to a 16-to-1. There's actually an 8-to-1 splitter that you can use if you even go out further. But these are the ratios that are in the model right now. We use our loop model then to generate the modeled network based upon, one, that architecture that I've shown, two, the inputs that I've shown. So to do that, we have to go through an exercise on our side. One is we have to collect the plan information. Plan information, actually maybe it's easier with pictures. So we collect the plan information, which is the wire center boundaries. I choose Kentucky to show you because these are publicly available exchange boundaries. If I were to show you TeleAtlas, I might have some issues because TeleAtlas doesn't like me to show their boundaries in public, or they really don't like me to use their data, but that's another point. Yeah, I'll stop there. So these are the exchange boundaries. So this is a wire center with a central office sitting in here, but these are exchange boundaries, and I'll hit on exchange boundaries in a little bit, I think actually tomorrow. When the FCC issued their request for boundaries, you have to think about what boundaries do I want. Exchanges can be completely different than a wire center boundary. An exchange may actually encapsulate multiple wire center boundaries. And it comes from the derivation of the word exchange. The exchange was, I won't go into it because I don't remember, but it was an old calling area. It was like a calling area that you call within as an exchange. You had an exchange boundary. The state identified the exchange boundary, but within that exchange boundary, you may have had 5 or 6 switches, which were then the wire center boundaries within it. So as you try and collect this information from public sources, you got some issues because some things may be exchanges, some things may be wire centers. When you ask the companies for their wire centers, they may give you wire centers. It's just somewhat of a mess. But anyway, let's start with, we've got these boundaries. We then take our customer information, which is customer data. We've done census block-based demand that is randomly placed on the roads within the census block. That census block-based demand is biz and res. So what we get is the customers along the road. We can use other data sources. If someone was able to get out of the Census Bureau the actual location of each and every household in the U.S., we could use that. If the Postal Service was able to give out a complete data set of all the postal deliveries things, we could use that. So there are alternative sources to get this. The issue comes down to, someone told me at lunch I should use this, if anybody, money. These data sets can get quite pricey. And for the potential marginal gain in the accuracy of what you get, is it worth the money to spend to get that? Additionally, there are license restrictions on some third-party sources. If we use Dun & Bradstreet for business data, Dun & Bradstreet's licensing restrictions are quite extensive on who can use it, how it can be used, how the derivative products can be used. And there is even a concern with what we've done here. We've used Geolytics to true up our census counts to 2009. We used geo results to get our business data at census block level. Those came with license restrictions that we cannot release the information at the census block level. So for those who have complained to us that I want to see census block results out of the model, it's not us. It's our data vendors require us to restrict the flow of information out. So that's why we need either license agreements, NDA signed, whatever it may be, to view some of that data. We can allow viewing on a small subset, but when you get into a national data set, the third-party vendors get quite touchy on the use of their data. So again, as you think about this is what we used in the current CQBAT. I do have an improved methodology that I think will improve upon that, and I'll talk about that tomorrow. And then I put on here again, we talked about the polar issue, what network are we building? So we're basically going to connect these dots together. How much time do I get? How much time?
This session ends at 3, so maybe 5-10 minutes.
We do. Okay. So as you look at, let me give you a background on what this is. This is a wire center boundary. We pull into our process Tiger roads. Tiger is census-based road data. It's got a geography to it. It tells us the actual vector shape of this, tells us the beginning point, end point of that node. Does Tiger tell us anything else? Type of road, whether it's a four-wheel drive road, a main highway, regional highway, or interstate highway, on-ramps, can get that. The problem that we've faced with Tiger is they've simplified the road classification over what's been done in the past. They used to have a CFCC, which gave you a much greater detail on the road types. In their ultimate wisdom, they've rolled it up to MTFCCs, which we have about 6 usable classes now. So the road definitions that we get from Tiger have diminished, which impacts the ability on some of this, because we're trying to identify where customers can live and which roads are routable. So you want a good road class. You can use third-party data sets for the road data. What the third-party sources do is improve upon the geography, naming, and other attributes about that road data, connectivity, amongst a number of other things. TeleAtlas or TomTom is one source of that data. Navtech is another source. Again, those all come with a price to be paid, which is the licensing terms that you have to sign to get access to that data. So we use Tiger because Tiger is free.
Have you compared it to, say, E911 databases?
I'll let Mark answer that question because he's best able to answer that. He's the GIS guru in the company.
Mr. Upper, repeat the question, please.
Yeah, with respect to E911 data sources, it depends on the state. There's not necessarily, and even within states, it tends to be a county-based issue. So there's not a uniformity in those data sources. Some states are absolutely spectacular. Locations, you can get great locations for certain classes of structures. Other states, all you're getting are center lines of roads with address points. So one of the things we need to look at is if we're doing a national study, we need a nationally standardized input data set. That's made E911 kind of difficult to deal with in this platform. Some states some states, I should say, are better than others in summary. And the one other thing that really plays in is we need alignment between these road sets and census geographies. It makes it very difficult if a road meanders along a census block to determine what block that road is in. What Tiger tells you, it's topologically integrated. So all of the census block edges align with the roads perfectly. So you have that integration, your data sets work. E911 is very problematic from that standpoint. It doesn't necessarily exist within a census universe.
Nor does it exist with TeleAtlas or...
1 year census alignment, you mean,
Yeah.
Jim? Yeah. Right now, 1 release per year of TomTom data aligns with census. The other 3 releases don't. So you have to pick and choose when you get that topological integration.
And while this map's up here, I'll just point out what a census block is for those. I usually talk about what census blocks are. Census blocks are the natural polygon formed by the intersection of roads or natural boundaries. So this potentially is a census block because it is the natural polygon formed. It was historically defined by that which could be walked by a Census Bureau worker in one day, if I remember right. But that's what a census block is. So it's a fairly small unit of geography, except when you start looking at this big boy polygon here. But again, that's what census blocks are. They're not a uniform unit of geography, but they are a geography that is something that we can capture within the databases because we do have the Tiger roads to understand what that census block is. The other issue with census block data and customers is these customers actually potentially fall in multiple census blocks. Left side could be one census block, right side could be a different census block. So as we design the model, we actually keep track of the customer points, knowing left side and right side, to understand that as you go down this road, you're going to install one pedestal. The telecom engineer doesn't care about the census blocks. They're going to put the pedestal to serve. We care because we're trying to roll up cost by census block, so we will keep track of the census block of the point and roll that up through the process. So back to this image. So this is the roads that have been cut out in the wire center. Part of our process is we had to walk through and do connectivity. You would think that roads connect, but what happens is if you do, you see these down here, there's no connection. So they're in an island, but they do connect. The fact is maybe the wire center boundary cut it, so we will do connectivity to make sure all roads connect together. The other issue in code that we face all the time is a loop. If you ever wrote code and you say walk down this path and you're on a loop, you never get off the path because you just have no way. The beginning and end node are the same point, so you just keep circling around. So there's issues to cleaning this road data up for a modeling purpose. We then locate the data. In this exercise, we randomly apportion the points to the census block road, the roads within the census block, so we get random apportionment. And I can't tell you if this is actually a random apportionment or a client data set. I've used this slide for so long I forget which one it is now. If we have client data or if we have address data, we actually geocode it to the latitude and longitude and then place it upon the road. So now we've got where the roads are, where the customers are. Our exercise, as I indicated earlier on when we were comparing back to the synthesis model, is basically connect the dots. And we connect the dots in the most efficient pathing that we can find.
Is that a good place to stop, Jim?
Probably.
Okay. Why don't we take questions before the end of this session? Any questions?
Bob Schoonmaker, GV&W Consulting. You mentioned when you were talking about the structure sharing that was a major point of contention in the earlier models. Is there any reason to think that it's less contentious in this model?
No. Honest answer, no. But what I did as the modeler, I just took as inputs what the coalition provided, which is what they actually recognize or what they observe in their network today is what was used in the model.
Okay, and you used a much broader set of inputs, as I recall, in terms of by location, by state, by...
On the sharing is at a fairly narrow representation. Is rural, suburban, urban. Broken out between aerial, buried, and underground. So it's 9 entries. The FCC's was expanded over that. I'm sorry.
Your sharing is also broken up by feeder distributor.
Oh, and feeder and distribution. I'm sorry. So there's 18 entries.
Hi, Richard Russello, CenturyLink.
Yes.
Could you kind of go over how we should think about unit cost versus unit revenue when we're thinking about the model?
So what is are you getting to what should the cost be unitized over?
Right.
It's an excellent question. From a pricing perspective and what you as a telco provider you recognize, it's really over the working customer base. You have to recover revenue only from those customers that pay your revenue, which are the working ones. So therefore, the cost per subscriber that links up to that revenue is unitizing by active subscribers, is how I view it. But what that does from the balloon perspective, if you got $1.8 billion to spread, I don't know the impact of that decision on a fixed level of funding exercise. It'll push the benchmark up, it'll push the alt-tech cap up, and you'll spread that money. I mean, overall, the fund size, unrestricted, would grow. Yes.
Okay, thanks.
Yeah.
Susan Lee, FCC. You mentioned that the network topology portion takes 5 days to run, and so I guess you have a few solutions that are up on the website.
Yes.
I was wondering, to what extent, how many different scenarios do you have up there, and how different are they?
Currently, it's just two. It's the fiber to the prem design and the 12K copper design. Okay. Additional designs can be added. We just need to know what the copper distance limitation is, and then the general engineering constraints on that network. And then they can be run and posted on the network. So when you come onto the online network, there's a pull-down box of what network topology do you want to run broadband over, and currently there are two selections.
Okay, so you varied according to technology. So setting that source of variation aside, let's assume that we're talking only about fiber to the prem. Are there different ways that you could run the network topology simulation that would help us understand how sensitive the results could be to that portion?
From a network design perspective, I don't think there's much difference. The only things I can think of is the distance of the splitter is from the resonance. But beyond that, there's not much difference in a passive optical network design. You've got to route the customers back to a central node. It's where you place that central node is the key. If I say it's 5,000 feet, I want to find all customers within that 5,000 feet. If I say it's 10,000 feet, then I just rerun with a different clustering approach. But I'm still always trying to find the minimum pathing possible. And that minimum pathing is not the shortest distance of a customer back to its node. It's the shortest collective distance to reach all the customers served by that node. So that doesn't really change unless you change how many feet you want to go off the node. So that's why we don't view it as something you rerun. It's more the assumptions on sharing, the assumptions on the type of plant that you're putting in, the assumptions on how you equip it are all put into the CapEx workbook. So that CapEx workbook controls the equipment that goes into that network.
So I think the question sort of came to my mind thinking about the FCC's old model that had a clustering and a loop design component. And the clustering, you can use, you can choose your algorithm. Yeah,
you can use an agglomerative, you can use a divisive. What was used in most runs of the model, if I remember right, was divisive. Is that right, Bill? Yeah. We are actually implementing right now what we think is a natural clustering. It's a cumulative clustering in which you look at nearest neighbors. So we're trying to identify neighborhoods. Because the clustering does not result in a ultimate or a minimized solution set. It depends on where you start, defines the clustering. And in both the FCC's model and our model right now, it starts at the farthest customer away from the central office, and then you start dividing off clusters. If I start the clustering process with a different customer, I will end up with a different solution. Is it significantly different? I don't think so, but it is a different solution. What we are trying to do with our latest clustering code is, I'm pretty close to Steve. I shouldn't be broken apart from Steve, but Bob's sitting far back in the room. He's farther from me, so I'm more closely associated with Steve in distance than Bob in the back. So we're working on new code that tries to take into account naturally grouping things together that still runs in a relatively quick time frame.
Thanks. I definitely appreciate sort of the difficulty in making that tractable. So
it is quite difficult. We brought in the head of the GIS department at Ohio State to kind of help us think through this, and he's like, there's not any published textbooks on. There's published textbooks on traffic routing, not on network routing, and they're a little bit different. As I send out my FedEx people, there's algorithms, and people have looked at that in depth and detail. Network deployment of fiber to the prem, have you found anything that really hits it well?
When you move out of the literature, the problem is it gets constrained by the engineering. So our networks are directed very differently than a traffic network is. It's directed really differently than how you route snowplows. So there are algorithms. They come up if you go and you buy Intergraph, they would have an algorithm. Esri has an algorithm. But running those over long periods of time, over lots and lots of geographies, the answers don't significantly change. What would make the solution change is if you could make the whole road laid out like downtown Washington, D.C. If the whole country looked like Washington, D.C., you could have a lot more clustering fun than you can in Kansas because the roads are so far apart. That's really what constrains the problem. Right. Nothing against Kansas, but that's just the way the roads are.
Where Google is.
I just annoyed the entire state of Kansas.
Yeah.
So.
Thanks.
Thank you. Ed Neff. I was just wondering if, from your perspective, whether there was any difference in the accuracy of the cost model in terms of running the different architectures. From your perspective, are they all functioning as they should, the fiber to the node versus the fiber to the prem versus the fiber to the
We've done some testing on both architectures against some actual engineers, not speed-wise, they take a little bit longer than we do, but they have laid out networks determining where they would place DSLAMs, how many DSLAMs they would place in a central office. When we run ours against theirs, it comes in within 1 or 2, both sides. Sometimes we have an additional one, sometimes typically they have more because we're able to optimize a little bit better within the computer code than what an engineer would lay it out. Same on the fiber side. We don't see any accuracy differences between the two. The accuracy comes in the customer data set used. That, as I've discussed earlier, how good your customer data set will lead to how good your results are at a refined level.
So are there any differences in the customer data set in this implementation that would yield the different architectures to have different results?
There are different customer data sets that would lead to different results for both architectures, not one over the other. Because basically, the copper design and the fiber design, once you're out from that splitter, the design outward is very similar. You're running 2 customers, and that architecture, the layout really doesn't look much different.
That makes sense. So we should consider them equally usable and analyzable for our purposes.
Yeah. There's one back there.
Do you ever put multiple splitters at the same location in order to save the OLT costs? Is there any?
It's the splitter is not what drives the OLT. It's the number of fibers coming off the splitter that drive the OLT. So.
But if there are multiple splitters in one box, then can they share the fibers out the back of that box?
Yes. Yeah, you put in, so in a box, the box typically, I think it's, I'll ask Bob, I'll put Bob on the spot. Splitter box is 864, do you remember? Yeah, it's something times 32 gets you up into the 800 range. So you put one splitter card in for 32 distribution pairs. So the distribution fibers come into that splitter. Out the back of the splitter is one fiber. That one fiber coming off the splitter card is what consumes up the OLT. It's not the splitter cabinet, it's the card that consumes. So putting multiple splitters at a point doesn't necessarily matter. What you want to do is get full utilization of your splitter cards. You want to try and get as many customers. You don't want to have a splitter card supporting one customer because it's very inefficient, because you're consuming a termination point on the OLT for that one customer when in fact you should be trying to get 32 customers aggregated together on that fiber to eat up that OLT.
So one final question from me. It's a follow-up to what Susan was asking. You say that there's an implicit assumption on the distance between a customer and a node, right, that feeds into the model.
There's a max distance assumption between the customer and a node. So the clustering looks at, if it's 12,000 feet, I'm looking at all customers that are potentially within 12,000 feet of a central node. So the cluster size could be actually as big as 24,000 feet side to side. But I'm trying to place as few nodes as possible in my network that still sits within the constraint of no more than 12,000 feet off of that DSLAM.
Okay, that sounds sensible, I'm sure. My question, the engineering the details escape me completely. But do you think this assumption would be sensible to change it depending on the industrial organization itself? Like if we had something like if you were running the entire telecommunications infrastructure of the United States, would that lead you to different assumptions as to the current state of the market?
No, I mean, I've worked with multiple providers, and their fiber to the prem builds look amazingly similar. I mean, there's not much different. And if you look at the architecture or the literature, they're pretty much consistent in how you deploy fiber to the prem. The same on the DSLAM side. It really comes down to the equipment that you use. Typically is different between providers. Some providers don't have small DSLAM boxes because they don't serve small pockets of population. They've just chosen not to serve them. So the smallest box they have is a 384. Mm-hmm. Other providers who like to serve the rural areas may have a box, the pizza box on a stick that they sit out there. It serves 24 customers. And I think some of them are down to 12 lines. I don't know, someone may know in here. But some of the smaller DSLAM boxes are getting quite small. That gives you the efficiency to go serve rural America. And that's more the difference, not necessarily the engineering and how you lay out the network. Mm-hmm.
It'd be really interesting to see when you made those comparisons. If we could take a look at that, I think it would be fruitful. So,
okay.
Thank you.
You're welcome.
Last question from Shomitra.
I have a couple of questions. Shomitra Das from FCC. The first question is about your FTTN and FTTD network architecture. How do you differentiate between those two, and why are you doing that?
Yeah, the biggest difference is when we ran the National Broadband Map, or data for the National Broadband Plan, we ran 5 copper architectures, do you remember?
3, 5, 12,
15,
18, yeah.
So 5 architectures. And the real difference is typically fiber to the node is for when this DSLAM gets out to 3,000 to 5,000 feet. So no more than 3,000 to 5,000 feet from the customer is typically what you call fiber to the node. When you push that back, so this copper now can be 12,000 feet, this is what we call fiber to the D. There really is no standard term. I think I potentially came up with that term because I didn't know what to call this design. It's not fiber to the node, because fiber to the node is typically classified as that service that you can provide video service to the customer. You can't provide video service to the customer here, but it still provides data capability. So if you put a ADSL 2 Plus in here at 12,000 feet, I won't give you the number that it supports because I'll invariably be wrong with the coalition members because they all have different opinions of what you can pump over at 12,000 feet. But that's the biggest difference. Fiber to the node is typically what we classify as video capable, and it's under 5,000 feet. Fiber to the D is over 5,000 feet, is not video capable, but is data capable.
Thank you. My second question, in terms of capital expenditures, Are you assuming that central offices are connected with fiber, or in terms of capital expenditures, are you including that connectivity?
Yeah, that is the middle mile portion of the network. We do assume a fiber connection from all central offices back to a internet site or a level 3 provider site. And that is then what is captured in the middle mile component of the network.
And we assume that that in building the network, we have to build that middle mile as well.
Yeah, correct.
Thank you.
You're welcome.
Thanks, everybody. That takes us through the end of I guess that's session 3. We'll reconvene at 3:30, where we will be hearing from the folks from ACS, and we will kick off right at 3:30. Thank you. If everybody could come on in and take their seats, we can move on to the next session. Happy to be joined here for this afternoon session by David and Karen from Parish Blessing and Karen Brinkman, respectively, to talk about the model filed in the record by ACS.
Thanks, Steve. Can you all hear me in the back? ACS appreciates the opportunity to contribute to this discussion, appreciates all the efforts that have been made by the Bureau and the participants to develop a better understanding of the cost-quest modeling process and the strengths and weaknesses of the national model as it's been developed to date. I'm a lawyer. I'm not an economist, an econometrician, accountant, so you all know far more about this than I do, but I do know that the Commission requires that the model that's ultimately chosen by the Bureau has to accurately estimate the costs of an efficient wireline-based provider of fixed voice and broadband services in the location in which it provides those services. And only a model that accomplishes this type of accurate cost estimate can reasonably calculate the amount of support that should be made available in all areas of the country served by price cap carriers, including in insular areas such as Alaska. As you've heard through the course of the day today, and as you've read if you looked at the CostQuest materials, and as Jim did a really good job describing, CostQuest worked very hard with a group of companies known as the ABC Coalition to develop a model that summarizes the forward-looking economic costs for many companies, but not necessarily for the whole country, and certainly not, we believe, for the price cap ILECs in Alaska, which are owned by ACS. The ABC Coalition made a number of key choices in design of the model and in inputs. Jim mentioned a couple that were simply selected by the coalition, such as cost of capital, bandwidth choices, others that were determined by the inputs that were provided by the coalition, take rate, cost assumptions, architecture assumptions. These things all heavily influence the outputs that the model produces. And ACS came to the determination fairly early on in this process that the model was not producing results that were even remotely accurate or predictive for ACS in Alaska. So though it is a very small company, ACS has devoted a substantial amount of resources to this modeling effort to try to supplement the Commission's record and provide accurate information for forward-looking costs in Alaska, because we don't believe the CQBAT model captures all of the cost elements that are present in Alaska, nor that the cost elements it does capture accurately reflect the costs that ACS knows to exist in Alaska. So let me start with a little bit of an overview about the company. I promise I won't spend too much time on it because I know you really want to hear from Dave and about the modeling that ACS has done. But ACS has 4 ILECs in the state of Alaska. They operate 6 study areas, 5 of them rural, about 120,000 access lines. Like many, perhaps most ILECs, they've come down substantially in the past 10 years. They're less than half the size they were on the wireline side. They also have a wireless business. More than half of their customers are in Anchorage, but the other half are distributed among 5 different wireless study areas, and I'll show you in a moment that they are located throughout the state. They have 81 local serving areas, and only a small handful are in Anchorage. The vast majority are separated from one another and from Anchorage by significant distances. ACS central offices serve anywhere from 12 customers to 23,000. 75% of their central offices serve fewer than 1,000 households. And more than half of their local serving areas are in what's called the Alaska Bush. This is the area, these collective areas of the state that are not on any road system. They're also frequently not on any electric grid, so they're quite challenging to serve with advanced infrastructure. This year, the ACS ILECs together receive about $19 million in frozen support, high-cost support. ACS also provides backhaul to many other carriers, particularly wireless carriers, and operates 2 submarine cables, which I'll show you on this map. The red lines on the map in the southern part of the state are submarine cables that connect the state to the lower 48. They provide long-haul voice and data service, but especially relevant for this proceeding, they provide internet connectivity to the state. There is no internet access point in the state. And the map shows how ACS delivers its internet traffic via one of those 2 submarine cables to internet access points in Portland or Seattle. The map also demonstrates that much of the cost in Alaska is in the form of middle mile connectivity. Jim mentioned this morning, I believe, that most of the cost of high-cost local exchange for high-cost local exchange carriers is in the local loop. I think Alaska is very much the exception to that. Much, if not most, of the cost in Alaska is in middle mile. And we'll talk a little bit about that. And that's one of the principal reasons why ACS did this modeling effort. The lack of an internet access point in the state and the lack of middle mile connectivity, fiber-based connectivity in the state, meant that there are 2 major cost categories for ACS: undersea fiber optic cables and satellite transport, microwave transport in the state that simply aren't reflected at all in the CQBAT model. The map also shows some central offices, and I'll just point out a couple of areas. Caltag, the western part of the state, and some of these locations on the Aleutian chain. Each place there's a white dot is an ACS local serving area. Most of these are not connected to one another by any fiber, nor connected to the 3 fiber rings that ACS operates in the state in Anchorage, Fairbanks, and Juneau. The southeast part of the state, where Juneau is located, I'll show a closer map so you can see a little bit more about what that part of the region looks like. But the overall impression of the state that you should get is that the network's very far flung, and the provider of last resort in the state, which ACS is for roughly 80% of the customers in the state, has obligations to provide both voice and broadband services that are simply unmatched by any price cap carrier anywhere else in the country. Which leads us to why ACS thought it was necessary to have a model. The modeling process, as I mentioned, was intended to get to forward-looking economic costs at the granular level for particular carriers serving particular locations. The Commission ordered that if the Bureau could not come up with a model that could accurately predict the costs of serving remote and insular areas such as Alaska and ensure thereby sufficient support, that the Bureau could exempt such areas from the Phase 2 CAF fund. So far, ACS believes that we have not developed a model that accurately predicts Alaska-specific costs, and ACS has advocated that more work be done in Alaska, or Alaska continue to be funded, universal service support continue to be funded in Alaska through frozen CAF 1 support. But the increased obligations that ACS and the other price cap carriers are asking to undertake to deliver broadband throughout the state simply can't be funded with the amount of support that's been predicted so far. Just briefly touch on some of the major cost differentials for the state, the reasons why it's so expensive to provide service in Alaska. First of all, the lack of fiber-based middle mile connectivity, as I mentioned. Many communities historically were not connected at all to one another. They were connected locally by the local exchange carrier and then by a different carrier, an intrastate long-distance provider, AT&T, had regulatory obligations to carry the traffic from the bush to Anchorage and the lower 48. But the local exchange carrier doesn't own any of those long-haul facilities, and the satellite connectivity is quite expensive. Second, as I also mentioned when we were looking at the map, the distance to the nearest network internet access point and the distance from the bush to the nearest network point within Alaska in either Anchorage, Fairbanks, or Juneau are very great. They're hundreds and sometimes thousands of miles. The undersea cables alone are 2,000 miles long. These significantly add to the cost of providing broadband service in the state. The geographic scale of the state alone means that loop lengths, even though calculated in the CostQuest model, are probably understated. Believe that loop lengths in many cases can be significantly longer in Alaska. Cost of transport, just the same way. The lack of road access and lack of access to the power grid is one of the reasons why we have no middle mile transport. When a local serving area is on an island, connected, it can only be connected by satellite transport. If a community can be connected by microwave, it will be. That's typically less expensive than satellite. But again, it may not be on a power grid, and so those microwave facilities have to be fueled with generators. The generators have to be refueled with regular trips by air. So you can see where the costs begin to mount. We'll talk about some specific examples. The sparse population means that the cost of an individual microwave or satellite link, or fiber for that matter, but particularly the non-fiber-based locations, the cost per customer is significantly higher because a system may be serving only several dozen or several hundred customers in a remote location. So whether it's a single microwave hop or a satellite link, the cost per customer can be many, many times higher than a community that's on the grid. Terrain and weather and the short construction season all mean that there are fewer opportunities to bury plant. There are more obstacles to overcome in constructing the network. And frequently, the choice of technology is discussed a great deal here earlier today. There are far fewer choices in Alaska than in other parts of the country. And then finally, labor constraints. It's not all that well recognized outside the state, but not only are labor costs high, but frequently there simply isn't labor available in the state. So with a short construction season and a limited labor pool, it can sometimes be very challenging to get facilities deployed in a timely manner at a reasonable cost. And then lastly, I just wanted to mention again the take rate. It was discussed at some length that the CQBAT modeling process assumes a 90% living units take rate, which is a 100% populated living units take rate. I don't know anywhere where a broadband is deployed and the take rate is 100% on day one, but it certainly isn't that in Alaska. And ACS's take rate is significantly lower in real life, and we have assumed a more realistic take rate in our modeling. Categories, once again, that ACS is focused on modeling so far are undersea cable connectivity to the state and middle mile transport. And Dave's going to talk about those because they are not captured at all in CQBAT. But we're also going to mention a little bit later on the other categories of costs that are captured in the CQBAT model, but we think are significantly undercounted, at least as for Alaska. Turn it over to you.
Thank you. First of all, the first thing I'd like to say is what we're trying to do, or what we were doing, is a lot different than what Jim and Mark have undertaken. And by a lot different, I also mean a lot easier than what they tried to do. They're building a national model that can estimate costs across the entire country, across the areas within the entire country. What we're trying to do is just a small portion of it. We're talking about Alaska, and we are talking about basically the middle mile. how to get from the serving wire center to an aggregation point in Anchorage or Fairbanks in that case. So first of all, when we talk about that the CQBAT did not estimate or cannot estimate costs accurately for Alaska, it's by no means an indictment against the model. It just means that it may not work for Alaska. Because those of you who have done any modeling in the past or statistical modeling, this kind of cost modeling, know that the value of a cost model is based on its ability to capture the variations in cost. In the case of a cost model, the variation in costs between companies or locations within a company. Okay, in order to do that, you develop a series of variables. You get different values for those variables for various companies, various locations, and you run your estimations or your simulations, and you get your results. Underneath all of that, underlying all of that, is an assumption that there's some degree of similarity or homogeneity between the places or the companies that you're trying to estimate. And what we have discovered, and it's pretty obvious when you look at the map and some of the things that Karen mentioned, Alaska isn't very similar to, say, Kansas, to use Mark's example earlier. If we're going to offend a state, we'll just stick with Kansas and leave it at that. Alaska and Kansas are not the same. And I think if you look at this and you take a look at the map that Karen showed, the map sits up there. Alaska, I think, looking at in the latest statistics, has, I think, less than 0.5% of the total population in the country. But it also has 17% of the land area in the country. So it's a lot different. Karen mentioned the fact that we, up in Alaska, the road system doesn't connect everywhere. Alaska is the only state in the union and probably the only area, one of the few areas anywhere in the world probably, where the largest city in the jurisdiction can't reach the capital of that jurisdiction by road. You can't get from Anchorage to Juneau by road. Okay, it's a lot different. A lot of the central offices you saw on the map, shown on the map, they're up in the middle of the bush. They're up along a river. They're along a coastline. They're on an island. There's no power grid. There's no road system. You just can't get there. So I guess what I'm trying to say is to expect the CQBAT model or any model designed to estimate costs nationwide to also be able to estimate costs in Alaska is asking a lot. And I think the conclusion that we've reached is attempting to fix it, attempting to get it to estimate costs well for Alaska, most likely are going to diminish its ability to predict in the rest of the country. So with that in mind, what we did is when the CQBAT documentation came out, we looked at it and we noticed the first thing was that, well, wait a minute, CQBAT assumes that there's a fiber-based middle mile, and we don't have that in Alaska. There are a large percentage of the serving areas or the wire centers in Alaska that would have to be served by microwave or satellite. Okay. Second thing, the CQBAT assumes a regional internet access point within the same LATA. Jim mentioned the regional tandem. We don't have that. They have to take it via undersea cable from a concentration point in Anchorage down through Homer all the way to Seattle or Portland. Again, as we've mentioned, the CQBAT assumes a ubiquitous road system, power grid, so that you could power all the facilities. Many of the Alaska areas aren't on a road system. There are no power. That has a couple of things that we'll get to later. Not only does it cause a problem with the middle mile, it also changes the cost dynamics. In other words, to get even a technician up to perform maintenance on some of these facilities isn't the same proposition in Alaska as it is in Kansas. for example. So we're dealing with a different animal here, and the question is, how do we try to get those costs into the discussion? So what we did is we developed a model that tried to do that. We're only halfway there. We've done the middle mile part, where we've estimated the cost of the satellite, we've estimated the cost of the microwave, we've estimated, well, not estimated, we know the cost of the undersea cable because they just built one. And so we can add those costs to what we would get for the portions of the network devised or defined by the CQBAT. But there's a lot of other things that need to be dealt with. Number one, there's differences in the installation and maintenance costs due to the nature of Alaska. The central office equipment, we're talking, we believe that the model or the Universal Service Fund should support both voice and broadband. So we're talking about central office equipment, switches, as well as the routers. As Karen mentioned, the per unit costs in Alaska are going to be a lot higher because you're talking a lot of locations with those 12 households or 12 households in a general store or 25 households or something along those lines. Installation and maintenance costs. When you have to use a helicopter to take a technician up to the top of the mountain to fix the microwave tower, it costs a lot of money. And then the labor costs. What we initially did is we tried to look at ways to adapt the CQBAT model or the framework to fix this. And it was easy enough to say, okay, we can just add modules for the middle mile, which is what the ACS model as you see it does. But some of the other things where we're trying to estimate the loop cost, the differential in the loop cost, we started working with the engineers who basically develop simulations and say, okay, this is how much it would cost to build a loop in this area now. And then we realize when they're doing that, the simulations are probably a lot better than a predictive model because they're actually focused on building it from point A to point B. The households in that area, they know where they are, they know where the central office is. They just say we need this much cable because the road goes this way. Instead of going through the machinations that Jim and Mark had to do, i.e. getting all that data where they could figure out where the customers were and the roads were. In our case, because we're only dealing with a small little piece of this, the engineers knew it, and they could just kind of simulate it out. So the bottom line is maybe for these areas, maybe we don't need a predictive model. Maybe in having to develop a specific model for Alaska, a more simulation approach is the way to go. Let's talk about the middle mile a little bit. Again, the middle mile, we're talking about a serving wire center from out maybe on the Aleutian chain or up in the bush or on the west coast back to Anchorage or Fairbanks, one of the aggregation points. We looked at the situation in the network. Most of those areas are served by, that are off the road system, are served by microwave at the moment. There's some, satellite at the moment. There are some microwave facilities, but not as many. Over time, the company has built out its fiber, and now we asked the engineers to take a look at it, and they've converted, hypothetically, several of the satellite links to microwave links. Okay, but at the end of the day, after they did all that, 63% of the wire centers or communities served by ACS are not on the road system, could not be served by fiber, would have to either be microwave or satellite. Karen mentioned the fact that these communities tend to be very small. The per customer or per unit cost of doing this is that much higher. And the bottom line is these middle mile costs are a lot higher in Alaska than they would be in the lower 48. Basically, we've heard over the past 10 years or so that transport was becoming a commodity, It's really not a commodity in Alaska in these areas that are off the road system. I've kind of talked about some of this stuff already. Let's talk about the undersea cable a little bit. The peering locations that serve Alaska, there's one in Portland, there's one in Seattle. In order to get to those peering locations, you have to come via undersea cable. A few years ago, ACS was experiencing issues with capacity on the existing undersea cables and the prices for the IRUs for those cables. As a result, they determined that it made the most business sense to build their own cable down to it. And in fact, they did that over the past couple of years. That gives us a very good idea of exactly what it costs to build a cable. It gives us a very good idea of exactly what it costs to maintain that cable. So those are the costs that we've included into the ACS model for the undersea cable. Here's what we're looking at now with the broadband network in Alaska. And maybe I should stand up and look at this. Oh. What you got here, you start at the customer premise and you have a central office. This is the microwave example. And then you have a microwave hop that'll take it all the way to the nearest point on the fiber network, wherever that is. And that's generally going to be around Anchorage or Fairbanks. In this case, it was up near Fairbanks. It went to the CO in Fairbanks, onto the fiber network down to Anchorage. From Anchorage, it would be put on the fiber down to Homer, and the fiber here is a combination of both marine and terrestrial fiber. Down to Homer, to the landing station, onto the undersea cable to the west coast of either Washington State or Oregon, and then it would be put on terrestrial fiber to the peering location. The undersea cable was purchased, this whole thing from the peering location and even the equipment in the peering location owned by ACS, all the way up here is the ACS undersea cable. These microwave hops were built, they were clustered. In other words, if you recall looking on the map, there are certain of these villages or communities that are nearby. They would be grouped together on a microwave hop and then brought to the nearest point on the fiber. So in all, the model, I think, contains about 14 or 15 different microwave hops up to a certain point. Once the distance got too great, then it was deemed it would continue to be satellite. Then we have the satellite situation over here, which is the community central office, a satellite link to Anchorage, and then again, Homer down to the peering locations. Bottom line on the satellite, ACS was able to build its own undersea cable. It was not able to buy its own satellite. So it leases capacity on the satellite. The satellite costs we're using for the ACS model is based on the lowest lease rate that ACS currently enjoys. Unfortunately, that lowest lease rate is on a satellite that has 5 years of useful life left in it. So we don't know what's going to happen at the end of those 5 years, and it's kind of ironic that we're talking about 5 years because that's the length of the CAF2, but I think that was just accidental. Okay, and now Karen's going to start talking about some of the other things that we need to take a look at.
As we said, the work isn't yet done. The modeling that ACS has done so far is focused on these two critical pieces, middle mile transport and transport to the internet access point, that immediately we noticed were missing from the CQBAT model. But the company also believes that the local circumstances in Alaska are so unusual that any national average set of cost modeling, even if it purports to show regional differences, is going to undercount the costs in Alaska. So some examples of that, the network sites that are accessible only by air, which are a great deal of them, the fuel costs that they pay, the additional hours of labor, the transportation costs themselves, all add to the cost of installation, maintenance, and replacement of facilities. In Nikolsky, in the Aleutian Island chain, access is only available by air and only when weather conditions permit. And this is an anecdote I just learned about yesterday, or Tuesday. The way to get out there is a flight from Anchorage via Dutch Harbor. It's a double hop on a small plane. The technician has been trying to get out there this year, which means since the weather turned well enough to fly, in 5 attempts at a total cost to the company of $54,000, they still haven't been able to get to the island and make the repairs that they need to make. I mean, this doesn't happen with every repair call, but it does happen. Another example that I've put up here, to replace a single cable in Port Heiden cost the company $44,000. It required freighting not just the cable itself, but the tools, the heavy equipment, and the diesel fuel to get to the location. And, of course, the technician expense, labor of flying out there, again, a double hop flight. So we raise these examples because the vastness of the state and the vastness of the costs in the state are sometimes hard for people to conceptualize. So I wanted to provide you just a few specifics. There are many more of them, of course. In Southeast Alaska, which I'm going to show you a map of in a minute, which is the area of the state that includes the capital, but which, as Dave pointed out, you can't get to except by air or boat. It is cut off from the rest of the populated world by mountains and water. Routine service calls take 21 more hours there than they would in a populated area such as the capital, Juneau. There are 2 population centers, Juneau and Sitka, and in the remainder of the communities, which I'm going to show you on this map, the work time and the complexity of serving the area, and even communications itself. There may be no wireless coverage, so technicians can't call back if they forgot a tool, they need some additional help. If there's no wireless coverage, it can multiply by several times the amount of time it takes for a service call. So the area of the state that we're talking about, each one of those little yellow pins to the left of the map is about 400 miles long and 200 miles wide. Many of those locations can't even reach one another except by air or boat. There simply are not roads connecting those locations, even in this small part of the state. So hopefully the visual is helpful in letting you think about the reasons why added fuel, transportation, labor costs for construction and maintenance of a network, just a voice network, let alone broadband, are significant. One last thing I wanted to mention as an example, or one last slide. Also in Southeast Alaska, in the same part of the state, there are 15 exchanges, 15 of those yellow pins. Each one of them is configured a little bit differently. There is some fiber in Juneau. There's a fiber ring. The other exchanges are configured with standalone COs. Each one of them is a standalone CO. They're configured with copper feeder, copper distribution cables, copper drops. Some exchanges don't have copper drops. They may be served by BEDRs, basic exchange telephone radio service, or cellular, or rely on microwave for distribution feeder. There is a lack of technicians sometimes, in addition to the costs that I mentioned. Sometimes they simply can't get people to reach the remote locations. They may have to get out there by all-terrain vehicle. A four-wheeler doesn't mean four-wheel drive. It means a little ATV, a cart, a push cart, or a small boat. So there just are not regularly scheduled truck rolls to these locations. And the The CQBAT model simply does not have a place in its columns and rows to reflect these kinds of additional costs. At least we don't believe so at this point. So, final word about additional costs that we have not yet modeled, but which we'd like to see reflected in any tool that's used to predict support for ACS in Alaska. The longer loops and transport lengths that we see in Alaska affect not just the deployment of microwave and satellite as an alternative to fiber, but affect the cost of fiber as well. Many times we believe the loop portion of the CQBAT model understates the cost of the loop itself. Fiber loops, even where ACS has deployed fiber, it believes its loop lengths may be much longer and have to go around mountains and go over rivers at a particular place that simply aren't reflected in the model. The fiber to the DSLAM costs, where fiber to the DSLAM has been deployed in Alaska, are also more expensive due to greater second mile lengths, middle mile lengths, and even where the serving wire center is accessible via the road system, the middle mile transport to the nearest fiber ring can be far, far greater. You may have a regional tandem in a state. You may have 2 or 3 in some states. There is no tandem in Alaska. So the middle mile fiber can be hundreds of miles even from a switch that's on the fiber system. And then finally, I think Dave mentioned earlier, but I'll note it again, the CO costs themselves may be above average as well. We have we believe the obligation to continue to provide voice service, not just broadband. We don't view voice as an over-the-top application that's someone else's responsibility. We believe it's part of the Commission's requirements, and it certainly is part of ACS's local regulatory requirements to provide voice service. It's very hard for the company to see how they're going to continue to maintain a voice network, let alone expand to broadband, if they can't upgrade their facilities and continue to maintain them with the support that they've been getting, and additional support if they're going to upgrade to broadband. They have the same costs as everyone else for a DSLAM, but a DSLAM that serves a population of 300 is going to have a far greater per unit cost than a DSLAM that serves a population of 30,000. ACS conservatively estimates that if its costs were used in the CQBAT model, thousands of additional end-user locations would qualify. In other words, would be above the $80 benchmark. Dave, you want to talk a little bit about our modeling process?
Yeah. The model, the first version of the model captures the satellite, microwave, and undersea costs as sort of an additive module to what the CQBAT produced. It's virtually identical to the CQBAT in terms of the framework. It estimates the required investment. It uses cost factors to estimate operating expenses and capital costs. And then it uses an estimate of demand to develop the unit costs by dividing the annual costs derived from the factors in the investment by demand. One thing, we follow the FCC's guidance in the order in terms of speed, latency, capacity, those sorts of things. One thing that wasn't in the order was what take rate to use, and as I think Jim was very clear in explaining, the take rate makes a big deal. It can change the costs tremendously. We did a lot of analysis of the actual broadband take rates in Alaska, not just looking at ACS's take rates, but also the market as a whole. ACS has a very successful broadband competitor in the state who has to, their figures have to be considered in order to get sort of a statewide take rate. We did. It turns out to be quite a bit lower than the 90% assumed in the CQBAT. The capital costs, we use the exact same HCPM style approach for depreciation and cost of capital used by CQBAT. One difference is the cost of money assumed in CQBAT at 9%. We used 11.25%. We know that there is a lot of talk about that the cost of money should be lower these days, but frankly, given the increase in risk that carriers face, especially a carrier that requires universal service, and all the doubt about whether that universal service funding will continue through 5 years and or beyond 5 years, seems to me there's a lot of risk. And that we haven't even started talking about the competitive risk and the changing dynamics in the industry. I got to think that if I was going to invest my money, I would have to look long and hard about whether I would do it in an ILEC these days. But that's just me. What did we do to develop the model? I think we can skip this slide because I think I talked about all that. The first thing we had to do is we had to figure out, okay, what would be the bandwidth requirements at each customer location? And in order to do that, what we did is we took the FCC figures that were in the order, and we worked with the engineers to develop what that would mean on a per customer basis. Basically similar to what Jim had talked about. We used an oversubscription approach and said, okay, given a customer, we would have to engineer the network to provide this amount of bandwidth. Next thing was to develop the customer count, figure out the customer count. We used household data from the Census Bureau. We also had to adjust that because, as Jim mentioned, there's a difference between occupied housing units and housing units. In Alaska, because of the seasonal nature of many of the industries, there are a lot of housing units that aren't occupied 100% of the year. So we had to adjust the demand data for that. And then we had to estimate the number of business locations based on company records, number of business access lines the company had a few years ago before any competition occurred, and now, so we came up with the business locations. We developed the cost factors based on the ratio of expense to investment. To me, the easiest way to look at what these cost factors are for operating expense, corporate operations, these other things, is for every dollar of investment you have, how many dollars of expense do you expect, or what proportion of a dollar in expense do you expect? We developed that using the data available at ACS. And from there, okay, it's time to sit down with the engineers and figure out what the investment costs were for the three types of middle mile: satellite, microwave, and undersea cable. If we start with the satellite, I think I mentioned we used the lease rate from the recently negotiated contract. Oh, I'm sorry. Okay, yeah. In addition, we had to incorporate the costs of the landing station, the equipment at the landing station, and getting the signal from the landing station over to the CO. Now, in a lot of cases, on the one end, the landing station was in the same building as the CO, or like across the street, because there'd be only like one street, and everything was pretty close to one another. But those costs had to be included, and we developed them by, we kind of grouped the communities and said for this kind of size community, this would be the let's call them the landing station costs, or the earth station costs, and for this other one it would be different, and so forth. For microwave, the first thing we had to do was develop the groupings. Okay, in other words, the microwave is a series of hops that starts at one community, hops to several others, and then finally ends up at an add-drop multiplexer at an existing fiber ring. So they would bring it in, and most of the time those add-drop multiplexers were at a CO that happened to be on that fiber ring. So once we did that, we would do the hop, and then we would figure out, based on engineering parameters, like, for instance, how far apart the microwave towers could be, how many towers would be needed, and then how many radios needed to be on each tower, depending on the number of customers that needed to be served. Again, when we did this, all the equipment, the engineers would supply the data, they would supply the cost based on the currently available costs that they would use for their projects. So in many cases, they made a detailed list of the equipment required, and they called the vendors. Said, what can we get this for? And that's what we used. The installation costs for contract labor and company labor were based on the estimates that they use for their capital budgeting process. In other words, the same numbers that they're currently using for any capital budgeting, they would use in this exercise. Bottom line is, we had those three types of middle mile, and then we figured out, or that one of the engineers pointed out, that some of the communities, there was a fourth option, and that was fiber and short-haul marine cable. In general, the short-haul marine cable would be used in the middle of a microwave hop. In other words, there'd be microwave, 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 then they'd use the short-haul marine cable, then microwave, microwave, back to the fiber area. Oh, if anybody has any questions, feel free to ask. Okay, the undersea cable. The last part about it, the undersea cable. Again, there is no peering point in Alaska. Everything had to be brought down. It was a little bit easier on the undersea cable because the engineers will tell you that capacity is not an issue on the undersea cable. Once they get the cable down there, it's a question of changing the electronics, and they have plenty of capacity. But that was the easy part. The hard part was actually provisioning the undersea cable. Efficient routing would require redundancy. So there, as Karen mentioned, there are two cable routes in case one is broken. There are two peering stations. One goes to Seattle, one goes to Portland, and then those two are connected in a little bit of ring between them that again, ACS owns. The costs that were included in the undersea cable includes all the cable landing stations, all the terrestrial fiber, and all the equipment required at the peering locations or the hotels that ACS needed. Yep. So, Karen, I'll let you go to the results.
It's yours.
Oh, the results are me? All right. Okay, so just briefly, what we did is we built the model so that it can calculate the number of households and bring it down to the census block, everything down to the census block group, the number of broadband customers, the type of middle mile transport required, the cost per location of the middle mile transport, the cost per location of the undersea cable, and then therefore aggregating those, we have a total middle mile cost. Then that could be added or used as a module to whatever is estimating the loop and then fiber transport aspects of broadband. I think, as Karen mentioned, based on this analysis, it's a lot more expensive in Alaska than what the CQBAT would estimate. Again, the reason is CQBAT is based on a set of assumptions or a network paradigm that doesn't really fit the situation in Alaska. It's a different place. In fact, we'll mention in the slide, the CQBAT estimates about $6 million in support for ACS. ACS currently gets $19 million just for voice. Estimates of by the company put the figure, not what the support should be, but if it was going to build out everything, it would be closer to 75 to 100 million. And that is adding on to what they already have. That's not the greenfield approach. That's just saying additional dollars that would be required.
I'd say that's adding on, that is building to unserved locations. It would be on top of that another 50 million to upgrade underserved locations and bring them to 4 and 1. So it's a significant lift through some combination of ACS investment and support.
Okay, so
Why don't we stop there and see if there are questions?
Any questions from the audience?
Okay, we've done.
Oh.
Hold, wait.
Jim Stegman. Was the 75 to 100, is that annual or is that total cost? It says total. I didn't know if that.
Total. Yeah. It's a construction cost.
Okay.
It doesn't include any ongoing maintenance or anything like that.
Got it.
Anyone else?
David Zussiger, FCC. And you mentioned that in a number of locations, that just the bullet above that on the same slide, the variation between your results and the CQ-BAT results is as much as several thousands of dollars per location. Can you be any more specific than that or give any specific examples of that?
Well,
we do. I'm not sure how much of that isn't confidential, though. We did submit numbers that would just show the additional middle mile transport and undersea cable transport. We have not yet completed the modeling process to show the additional costs beyond those, and so I don't think we have those yet to give out.
But conceptually, what I can say, David, is that what we did is we took what the CQ-BAT number was, and then we figured out what the middle mile costs and undersea cable costs would be for for a specific location. If you took one of the location, say out on the Aleutians, and factored in what that satellite cost would be and then the undersea cable cost, that would be an additional $2,000 or so a month on some of them.
Shomit Rudas, FCC. I'm trying to understand that conceptually, that if CQ-BAT modeled correctly, then the assumptions that are lacking or specific to Alaska, if you put back those assumptions, CQ-BAT model should generate the same result as yours. I don't know whether you have looked into this or not. Maybe one of you can respond to this question. They should be similar if the assumptions that you think specific to Alaska, you put it back in that model.
Well, we have thought about that, and usually the first thing you go to in a case like that is to say, okay, is this an omitted variable problem? Is it just that there are certain variables that would be required in Alaska that aren't found in the CQ-BAT model? And the next stage you would go to, or the next step would be, okay, can we change the variable values? Is it just a question of taking the input values and changing them for Alaska? In some cases, there is, especially on the loop in the customer connection. We could change the installation and repair cost, and then therefore adjust some of those things in the CQ-BAT. I'm more concerned about the changes in the algorithm because, as Jim mentioned, the CQ-BAT is set up based on a certain network paradigm, and which doesn't necessarily fit in Alaska. So I would suspect this is like a tail wagging the dog, because I think of the customer locations, for price cap customer locations, 98 point some odd percent of them are in the lower 48. Less than 2% are in Alaska, Puerto Rico, the Virgin Islands. So it's a sort of a tail wagging the dog thing. I would be afraid that if you did something like that, you may improve its accuracy in terms of what it does in estimating Alaska costs, but what's it going to do when it's estimating the other 98% of the costs? That's the first thing. The second thing is, this is a relative model. The whole point is to figure out how to allocate that $1.8 billion. So when you estimate it and you make your tweaks to it, to the CQBAT to try to fit Alaska, are we sure that when it says that Alaska's costs are, say, on average, $120 per subscriber, and Oklahoma's costs are $86 per subscriber, are we sure that that relative ratio or relationship is holding? And I'm not.
Liz Reyes, FCC. So I'm curious, what percentage of the difference in the cost in your model is due to the different assumption on the rate of return? Because you're assuming 11.25, whereas they are assuming 9%. That right there, I mean, is substantial, right? That's like a 20% increase just because of a different assumption?
Well, it's funny because I thought that it would be more significant than it was, and when I looked at it, and what I didn't do is I didn't pay attention to the capital structure they were using. And I think, Jim, you mentioned you're using 75% equity, 25% debt. Okay, we were using a much more balanced capital structure. So when you just make the changes at 11.25, I think we're using 7% debt and 15 or 16% equity with a 50-50 capital structure. It didn't make that much difference. I mean, there was a difference, but it wasn't enough to...
Do you know how much?
No, not offhand, no.
Okay, that'd be good to know.
Mm-hmm.
Okay, well, why don't we take the couple of minutes between now and 4:30. We've got one more session without a coffee break. So thank you guys very much for coming in. Definitely appreciate that. And all the modeling work you did. We can now transition back to Cost Quest for the last session of the afternoon.
Thank you.
Assuming anybody lasts that long.
There's a good crowd here, yeah. They're all attentive.
You should dive, seriously, you should dive in. Believe me, nobody wants to say past 5:30, so.
Sure.
Hello, sir. I'm Alec. So if everybody can take their seats again, we'll finish off and try and get everybody out of here right at 5:30. I know it's been a long day, so we don't want to run later than that, especially since we have to come back in the morning and start all over again.
You're not selling the excitement.
Yeah, I know. It's a shame.
I got. All right. So I should start? So let's all jump back into it. There's fewer of you. I'm actually surprised there's this many at 4:30. Where we ended off was I had my pretty chart up here of customer locations along the road. We've got them located either geocoded or spread randomly within the census blocks based upon the data that we have. We have the roads, and now we're going to connect the dots together. So we take the engineering rules that I've walked through, the limits on copper distribution, which we use 12K for the DSLAM runs. We have to decide if it's fiber to the prem or fiber to the D. The fills that we're going to use on the cable, so you don't necessarily, we talked about earlier, you don't size plant to 100%. So you have to leave some fill available for spares, maintenance and whatnot. So we have that as a fill going into this, and then the whole polar issue. So the first thing we do is we will create a what we call a minimum spanning road tree for the entire central office. Basically, to connect or develop an MSRT, we start at the central office, which is the blue diamond, or that's the source node. From that, you then will connect up the next closest point. You go through that exercise of connecting points together, and then you relook at the routes that you started with. So I may have gone out this way, come back here, and connected it, but when I went out this way, it opened up this node, which meant this was a shorter path. So in total, what that minimum spanning road tree is meant to capture is the minimum total distance to connect all the dots together back to that source node. So this is just an expanded picture of that around the central office. So around the central office, we know we can go out 12,000 feet from the central office and serve all those customers off of a DSLAM and be within our 12,000 feet. So that's kind of called the donut hole. We will go after that first and make sure that we can connect all these customers back within 12,000 feet along the road path. So everything that is highlighted here is all within 12,000 feet along a road path back to that central office point. We then may break this up into multiple serving areas because a DSLAM can only serve so many. In telco architecture terms, there's an allocation area. You typically size an allocation area similar to how you size a carrier serving area, in which you typically do not want more than 1,800 customers in that area. So we may break this minimum spanning tree up into smaller trees by breaking off branches of the tree and say a node will be placed here to serve these customers, and there are no more than 1,800 customers on that tree, branch of the tree. So now we go to what's remaining from the entire central office. So you can see we've carved out the donut hole. We're left with the donut. Now we have to figure out the clustering of the donut. What we've done, and it's very similar to what the HCPM or the synthesis model did, was we used divisive clustering. So you start at the customer who is farthest back or farthest from the central office along the road path. So we look at all customers, and it somehow turns out to be this customer here is the one that is farthest from the central office, and that is the point at which we will start the clustering. Now, you may question why that is, and I think it's that way, but it doesn't look that way on this picture. But we start here, and we will start physically just walking down the streets to the central office, and as we walk down that street, we will keep track of the number of customers that we hit. So here's a blow up. So we're walking back this way. We've got constraints of we want no more on a DSLAM, or we want no more than 12,000 feet from the DSLAM, and we do not want more than, I think, 600 customers off of the DSLAM, I think is the input it may be. So as we walk this path back, we will keep track of the distance and the number of customers that we hit. So we will walk back until a point that we get to 12,000 feet, and we say we cannot go any farther than this point. Once we reach this point, we then release this customer. We start from this point, and we walk back towards the central office and collect those customers who are within 12,000 feet of this. So that's how the minimum spanning road tree works, and the clustering is. You start with the first customer to determine how far that node can be back. You walk from that node then back to see how far or how many customers you can grab. What we want to make sure is we do not split a leaf. So say, for instance, you could go up part of this tree and still be within 12,000 feet. What that does is it orphans off this branch of the tree you do not want to orphan, so you stop and you do not walk up that path. So that's why this link was broken. The same way here, we don't mind going down when it doesn't create an orphan path. We don't mind going down that street, and we don't mind crossing intersections with multiple cables. But there are certain rules in the clustering that we try and honor what an engineer would do as they try and create that cluster. We do have additional rules in the model to allow us to let some what we call extenders to be served off of this DSLAM. And what we call extenders are those that go beyond our design limit of 12K. So we may say we'll allow a few extenders because it's inefficient to deploy a single DSLAM out to this customer because, say this road is 12,000 feet long. I can't physically cluster them with anyone else. It's inefficient to place a single DSLAM out to that customer, so we may, in a model run, and I'd have to check what we did for these runs, but we may allow this customer to exceed 12,000 feet to a certain extent where we put a hard physical limit. You cannot go beyond the hard physical limit, but you can go beyond the design limit, but we only allow a few of those to take place. And that's, again, trying to minimize overall costs. This customer can get data service potentially up to 15,000 feet, potentially up to 18,000 feet, but it's a degraded data service. But from the perspective of designing an efficient network, you don't necessarily want to deploy a single DSLAM out to that customer if they're close enough to still be able to get a level of service on the DSLAM. So as we go through, we will pull this cluster off, and that's why it's called divisive clustering. You start from the outside, you divide or cleave off a cluster, and then you go to the next farthest customer. You continue to do that until you have all clusters defined. Agglomerative clustering on the flip side starts typically from the central node, agglomerates, captures customers, and adds them together until you run out of customers to agglom together in the agglomerative method. So in the end, this is a picture I showed you before. We come up with the engineering areas we would define that are road base for this central office. So there's the central office here. These are the clusters that we have created based upon a 12K design. And in our view, those clusters really won't change based upon user inputs. It's not that I can change 12K. 12K is 12K. And this customer will always be 12K from this cluster point. So that's why we have these predefined network topologies that we create that we do not think change based upon most of the user inputs. However, if you said it's a 5K design, I need to redesign this. And what we found is typically if you're providing the longer the distance, the cheaper the network, because DSLAMs cost money. You want to get as many customers on that piece of electronics as possible to share that cost. So if we went to a 9K design, the cost will increase. If we go to a 5K design, even more. A 3K design, even more. A fiber to the node network design is actually more expensive than this design because effectively you're putting more DSLAMs out into the network. You're still potentially putting in the same amount of cabling because you still have to connect all the customers together. It's just now you've doubled or tripled the number of DSLAMs. So from a policy perspective, the fiber to the node network, a 3K fiber to the node network is going to be more expensive than a 12K fiber to the D network from a initial basis. Yes. Yeah, I can take the question now.
I was just curious how the model treats those. Thanks. Richard Cameron, ACS. I was curious how the model treats those roads in the lower left that, in fact, don't appear to connect to the rest of the road system.
Okay.
Thank you.
On this one here? Like here, these? Yeah, that is a connectivity issue. So, and this is a bad picture. They were cut off by the wire center boundary, but we will capture the road segments to make sure that will connect. So we typically buffer out the wire center boundaries in these runs. Do you remember, Mark? 50 or 100 feet? Probably 50 to 100 feet out. If we still have road connectivity issues, we create a connection to the nearest road segment that we can connect to. In the newer versions of the model that we're working on, we're buffering out actually a mile to make sure that we can be able to connect up those little orphan segments that you're seeing up there. I'm just trying to think if there's anything else in this picture of worth a lot, but we'll go to the next slide. So once we create these engineering areas, we've identified the customer association to their DSLAM. The next part of the process is we locate the DSLAM to make sure it's centrally located, because as we walk back 12,000 feet and then we walk out, we may end up with, when we walk out, we only get a customer 6,000 feet out. It may be more efficient to move that box, that node, a little bit. So we'll recenter the position of the DSLAM. We will then take this and run a minimum spanning tree within this cluster. Each cluster is then re-optimized based upon pathing back to the central node, because minimum spanning trees work on the node that you're looking at. Our original minimum spanning tree started here, and this was the central node, so everything was minimized with respect to this point. Once we create a cluster and we create a node, we want to rehome it and optimize it to that central node again. So all clusters have a minimum spanning tree run within them. Once we have that minimum spanning tree identified, so just going back to this, we now have the distribution pathing. We know how to connect all those customers together. So in this example over here, this is our customer data set. This is the minimum spanning tree to connect those customers together. And all we're doing is then taking that minimum spanning tree and running cable along the minimum spanning tree, because that minimum spanning tree is along a road path. So it's a realistic representation of where a telecom provider would build that network, because they build along roads, usually. On the feeder side, we do very similar to what we do on the distribution side. Once we've identified all the nodes in the network, all the potential DSLAMs, carrier systems, whatever type of network we're designing, these were splitter positions. We look at those nodes. We have the central office here. We will create the minimum spanning road tree to connect the feeder system together. So this is a minimum spanning tree for the customers connected to their node. This is a minimum spanning tree for these nodes connected to their central office. So it's always a minimum spanning road tree to that central node that it is feeding those areas. As we do that, I don't know if I have a slide here. Maybe here. So in the end, we end up with the design. This is the topology design for this wire center. We've identified the feeder pathing. We've identified where we got to place all the DSLAMs. We know how many customers are served off of each DSLAM. In the database, we keep track of every point that you see up here. There's an entry in a database that says how many customers. This is actually a pedestal, not a customer. We've converted to pedestals by the time this picture's created. A pedestal is the green mushroom outside your house that can serve anywhere from a couple customers to 5 or 6. So these are the pedestals. We know for that pedestal how many customers are served out of that pedestal, what type of services those customers receive. We know if we had actual customer data, we know how many were working versus non-working. We know the distance of this cable. We know how big that cable has to be, because we know how many customers are served. If there's only 5 customers out here, this cable only needs to be a 25-pair cable going down that street. If we hit this point and we determine that this now becomes a 50-pair cable, we keep track of that is a change in cable size, therefore a requirement for splicing and a requirement for a truck visit to do the splicing. So we will keep track of the splicing visits in this network. We keep track of the size of the cables, the types of the cables, all the various nodes throughout the network, and that sits in a database. And that's really the detail that sits behind that picture is quite immense. The other thing we keep track of, this is the feeder distribution sharing, is you'll see that this blue cable actually overlays on top of the yellow cable. So there's an opportunity to share the structure costs. The pole cost can be shared, the trenching cost could be shared, the conduit could be shared. So there's a sharing table in the model that specifies how many or what percent of the time is that path shared. Many times you may have underground transport or feeder and above ground distribution, so there is no opportunity to share, and that's why you don't typically set them to 100% sharing. There is a sharing, but not always 100%. I question myself whether I should put this in or not. This was an old chart I had put together a long time ago just about the cost profile of that local loop. And this was on average that you see this big part of the pie is your distribution structure and cabling. If I look at this right. The blue is the electronics. This was in a voice network. This was your structure and cable cost. And then the key components that drove cost. And part of the reason I did this was you want to really focus your energy on the things that really drive the cost. So it's distribution structure, distribution cable, electronics, the feeder. Then you get into the NID, drop in the distribution terminal and building terminal. The final things are the feeder distribution interface, the building cable, and the main distributing frame. As a percentage of the total cost, they're a relatively minor portion. So you really want to focus on making sure you do this really well. These, potentially you can use a factor to get those in to make sure you capture the cost and you're not impeding the quality of the study. So here's just some more pictures. I like to show pictures. This is a wire center. Again, the customer location's in that wire center. This is a blow up so you can actually see all the points in that wire center. This then is the pedestal locations that we designed. So we will walk the street two ways, up the street, down the street, to determine where the pedestals go. There's rules that guide that pedestal installation. So you can see it's a reduction in the electronics, but off of each of those pedestals, you now need to run drop to all the customers who are on that. You then run the feeder cabling, which is the blue, and the distribution cabling that is underneath, which gets you to this design network. So I've taken the road layer off, so now you can see the design network that takes place. Again, this is the network topology that comes out for an area. In that database, we keep track of the size of the cable and how many customers are at each one of those. In CQBAT, it takes the design of this and applies the costing, the sharing, and all that. So in the end, you end up with a design network for that wire center that looks like this. So we went from customer data and roads to the design network that we cost out in the model. And then if we take it down to what can that support, well, this is the visualization. And again, this is one of the benefits of using CQBAT is now you can go down to the cost of a census block. Each of these is a census block. Yellow is lower cost, blue is high cost. The ones that don't have shading are no-cost census blocks because there's no facilities or no customers in those census blocks. Again, this is my favorite wire center. We walk through, we've been through this, we get their nice network. We then have the different cost layer, but we can actually go down below that. This is if I have good customer data. This is actually the cost of customers. Yellow, low-cost customers, blue, high-cost customers. It doesn't show up well here. It shows up really well here. So if you could see this, you could actually see it. But given customer locations, we can move beyond census geographies. We could overlay 500-foot grids. And Mark's probably ready to shoot me because I think I asked him to do this one time, and he was just going, "What are you doing?" But this is then the cost of 500-foot grids. We could do 1,000-foot grids. But all it is an aggregation of the customer points within the unit of geography we select, and you roll it up. So this is just a grid. The next one is just, Mark went crazy one day, probably because I asked him to do it. I said, can you do like a nice, cool three-dimensional figure? So this was, take that, we threw it into Google Earth. You can add dimensions on the cost, so the height of all these polygons is then the relative cost within that. So it's a quick way to visualize where are the high costs if you're looking at a map. Doesn't work well when you do it nationally, but in a small geographic footprint, it works fairly well. So before I go into the farming, you didn't know you were in the agriculture class, but we're going to get into agriculture here in a second. So before we get that, any questions on that topology deployment? It's specific to each and every wire center.
Hi, it's Ed Neff again. Just wanted to confirm, you talked quite a lot about the difference between the different architectures, fiber to the DSLAM versus fiber to the Prem. And earlier in your presentation, you talked about greenfield versus brownfield. Could you speak to, and you've calculated it, in a quite sophisticated way, the cost of outside plant in the fiber to the DSLAM approach. But can you confirm that when you run that on a greenfield basis, that you include the costs all the way to the Prem?
Yeah. So between the two networks, so we will, in the network topology that sits within CQBAT, we've got this network topology, which is a fiber, a 12K copper design. We also have another topology that will look a little bit different from this because it's a fiber to the Prem design, where we've pushed these cluster sizes down to 5,000 feet. So we've got two different designs sitting in the model. When you run the model, we keep track of this copper distance here. So when you run that greenfield approach, it will include the cost of the 25 pair cable, the distance of that cable, the cost to splice that cable, the construction cost for the poles, the trenching, the conduit systems, whatever they may be, all the way back through this, so that it will include the total cost of that copper deployment along with the NID and the drop. When you get back to the DSLAM, this is also included because it's a DSLAM to service these customers along with all the fiber going back. The difference between the brownfield versus greenfield toggle is you tell me which of this part of the network is brownfield versus which is greenfield. So if you look at the CapEx inputs, there's a flag on each CapEx input, and you specify greenfield, brownfield, or all. And in the defaults, these would be labeled as greenfield only. So they only show up in a greenfield run. If you turned it to brownfield, the yellow on here all disappears. All you get is the blue network along with the DSLAM location. And that's all the costs that come out in the current toggle that's in the model.
Great, thank you. One follow-up question, if I could, just quickly on tax rates. If companies accelerate their depreciation, would you be understating the taxes from a time value money perspective in the way that you do things?
If they accelerate, and typically they accelerate their depreciation on the tax books. For tax purposes. We capture that in our deferred tax calculation. So we take the latest Makers, I don't know if it's Makers now, but it was Makers. We take that tax schedule available for Makers, so that's as quickly as they can accelerate. We take that, compare it to the economic life, and come up with a deferred tax that then impacts the levelization approach that we use. So it is accounted for in the model. It is an accelerated depreciation. It's an accelerated depreciation on the tax side. It does not accelerate the depreciation in the study. The depreciation in the study is, quote, the economic depreciation. It represents the life of the asset.
This is Shomik Tridas again. Going back to your greenfield versus brownfield question, I wanted to understand that, what did you find in terms of cost differential between these two deployment, if you run these two models?
If you look at this network, by far the biggest cost component of this network that you're looking here is the distribution side. It is the copper plant getting out to the customers. It is the structure costs, the poles, the conduit to get out to those customers. It's probably, I think I looked at it one time, probably at least 60% of the network cost on average is in the distribution plant. Another 20% in the feeder, and then at the time I looked at it, we had switching and transport was probably another 15%, 20%. So the yellow goes away in the current brownfield toggle unless you use, and the operational costs go away as well. And the question is, from a broadband perspective, do you need, from an opportunity cost basis, from a cost definition basis, does this have value, and is that value part of the USF study? And that's as far as I'll go on that discussion.
Just to follow up on that, greenfield. So in terms of greenfield, are you assuming fiber to the prem is going fiber directly to the premises, or are you considering DSLAM to copper?
Well, there's the two approaches. On the fiber to the prem, it's fiber to the premise, fiber right up to the home, and there's a fiber connection at the house. And that is part of the greenfield study. So in a greenfield fiber to the prem, everything's included because there is no, unless you talk to Maggie, who's left, I think, Verizon. They're one of the few that have a fairly broad fiber to the prem deployment already. But for most carriers, a fiber to the prem would be a greenfield build. On the copper build, we run fiber just to this point. And on the greenfield portion, we include then the copper connection to the customer's premise.
Susan Lee, FCC again. You'd mentioned in your a couple slides back that when you assume 12,000 feet is the maximum distance, you then minimize the number of DSLAMs to minimize cost. And the 12,000 feet is a parameter that is taken as given. So if you increase the 12,000 to a 13,000 so that you can decrease the number of DSLAMs again, do you have a sense of whether cost will go down?
Cost will go down. The longer that you make the loop calculation, the cost will go down. The problem, the dual problem you have to think about is on the 12 or 13K design is, does it support the broadband speed that you want in the network? So if you say it's a 4-1, 4 down, 1 up, let me stick with 4 down. If you do a 4 down, you potentially do 4 down at 12,000. If you go up to 13,000 feet, it's not a guarantee that the customer at 13,000 feet will get 4 down. So that you have to then bring in your engineering side to determine what size cluster makes sense.
And then following up on Shaumitra's point, taking the next step and looking at, in your diagram, the yellow portion that is the distribution network. If you go to 13,000 feet, will the yellow bits be larger?
Yes. Yeah, because what will happen is potentially clusters there may been 60 clusters here. With 13,000 feet, it may drop it down to 55 clusters. So the yellow will naturally increase somewhat, but it still won't increase a lot because you still always have to connect customers back to a point. So there's a point at which I don't think the distribution cabling will cut down a lot. What you're cutting down is the number of DSLAMs for the most part.
Okay. And one general question. This morning, you had a goal slide that showed the picture of the United States and cost as the ultimate goal. And then shortly after, you mentioned both a cost module and a support module. Are you going to cover the support module tomorrow, or?
Some of it. I'll show you the toggles that are available, but mostly the support toggle is just how you use that cost information. But I will go through it in general. And if I don't answer your questions, let me know.
Okay, thank you.
You're welcome.
Jim, I want to set you up for your next slide, and in that, with the land and soils, I'm hoping that you'll cover some kind of how you got there, because in HCPM, it starts with like 200 to 300 different kinds of soils, and then puts it into soft, medium, and hard, and then says there's a additional cost associated with soft, medium, and hard. And if I remember correctly, all of that came from Mike Lieberman and AT&T or one of their consultants, and I don't think anybody understood how all of those associations were ever made. And I was just wondering if you know how.
Yeah, because I was around at that time. I don't know if it was Mike. I think it might have been Jim Dunbar who was at Sprint.
You know, who made those associations or where they came from, and.
I'll blame it on Peter up here. Peter may have done
okay.
it.
Well, maybe it's Peter's. I don't know whose fault it was, but they got in there.
Yeah. So let me expand on what Bob's asking and kind of discuss what we do. So as you look at this is a black and white picture of the Earth's surface. We don't understand what's behind this. There's two things that we bring into the construction cost side. So when you're putting up poles typically don't vary a lot based upon terrain or density. You may have an extra cost if you have to bury it in a rock and bore it into rock. But what we look at is for the construction cost on trenching. So if you put a conduit system in, which is you put plastic pipe into the ground and you have manholes, you have to dig the dirt. If you put buried cable in, which is you dig a trench, you kick the cable in, it's got a sheeting around the cable, you kick the dirt back on, you stamp on the ground, you're done. Either one of those, there's cost to do that digging of the ground, putting the dirt back on, if there's concrete, you got to restore the concrete. If it's bedrock, you may have to bore the cable. There's various construction costs that are incurred. So to try and accurately capture the cost out here, we bring in two items. One is a density database. We look at the relative density out here because we know you can negotiate different contracts in a high-density area versus low-density area, and we know that in a high-density area you may have additional costs for flaggers. You may have to do the construction at night because of traffic patterns, whatever it may be. So one is we want to understand the relative density of the area we're building in. Two is the terrain. And terrain then is broken down into subparts. So that terrain data that is used is been used, has not changed since time began with universal service models, is the StatsGo database. StatsGo is a U.S. Geological Society.
NRCS, National Resources Conservation.
That's why I bring Mark.
Yeah.
So we've got the StatsGo database, which gives us soil type, and I think actually in our model we might have 600 different soil types. I remember the discussions we had when the soil types went through on the BCPM model team. We have sandy, loamy soil. First, we had to find someone to explain what loamy is. I still don't know what loamy soil is. I think it's light and airy. It's from composted material. I don't know. But you got clay, and there's various combinations of all the soil type, and there's a database of all the soil types available in that StatsGo database. We had engineers, and it was, I believe, Jim Dunbar, who was an engineer at Sprint, go through and say, will this impact the construction costs? Yes or no? And that was the 0-1. So each of the 600 was reviewed, and we had a 0-1 put in, and that was then a piece of information that we took, a first piece of information. Second piece of information is we have the type of rock, bedrock. Is bedrock in the area?
Depth to bedrock?
Depth of bedrock, I'm sorry. Depth of bedrock. How far is it on average to the bedrock depth in this StatsGo area? And from that, we had a measurement if it was within 24 or 36 inches of the top of the soil. That was another influence in determining our terrain type. Third one was water table. We looked at how deep was the water table. to understand if that was going to be a concern in burying cable. And there might have been one other one. Rock type?
Rock hardness?
Oh, rock hardness. What was the relative hardness of the rock in the area? Because that can indicate, can you trench or do you have to bore? So we boiled all that together and we came up with 3 terrain identifications in an area. Normal, soft, which we call medium, and then hard, actually it's 4, and then water. So in each one of those, we then asked for this study, and for back in the HCPM days, it was, what's the relative cost difference if I'm in a normal terrain? Normal terrain is ideal, sandy, loamy soil. I can run a ditch witch down. It costs me a couple bucks a foot to open up that trench, kick the cable in, put the dirt back on. If I go into hard terrain, which is the highest category, that means I potentially have to use a borer to bore in, or I may have to have something to cut the rock as I do the trench. Very high cost, or much higher cost. It could be $8 to $10 in a rural area. So then we layer that density, or the terrain layer in with density. Now we say in an urban hard rock terrain, hard rock in an urban area could be a lot of asphalt or concrete. So that now becomes a hard urban area, and cost in those areas could well exceed $100 a foot. Not in the inputs we have because we took an average across the U.S., but I've seen in individual studies we've done for clients a trenching cost in excess of $100 a foot. So you combine the two together, so now you have 12 entries for trenching cost on buried and 12 entries for trenching cost on underground to capture differences in the terrain type that we recognize and the density type that we recognize. And we do that on each and every segment. We identify the density and terrain on each one of those so that we capture the correct cost for trenching. And I'm not sure anybody wants to validate. I've used the soil table now for 14, 15 years, and no one's ever questioned it. I've been in hearings and no one's ever asked me on the stand either, so it will come now because you brought up the question.
Schoonmaker from GVNW Consulting again. How do you allocate or assign, say, the costs of the whole feeder plant to individual customers?
That's an excellent question. I'm glad you asked that. Let me go into the next set of slides.
All right.
So what I call this is we call it the farming. It's the farming of the information because, as I said, it takes days to run this output. It's a massive amount of information. To run 8 million census blocks in a relatively quick time frame of 12 hours to process the entire nation, we had to figure out ways to collect all the information in an economically correct way and push it down the census block. So we go out and we farm all the information that we get. So as I said we've got a database. Let me go back. I've got a database record for each one of these nodes that captures the node and the cable segment to it. That is captured in a database, and this is just a slice of that database. But it'll tell us what type of node it is. It's a distribution terminal. It's 404 feet to the next terminal. It's a distribution route. I've got, actually this MSRT route count tells me it's fully shared with feeder cable. So I should be able to share the structure cost on this. It's copper, 24 gauge. It's got one cable in it. It's a 50 pair cable. It doesn't require splicing or a setup. This is the number of customers connected to the terminal. This is the number of customers writing over the cable. This then is the information about bedrock depth, water table, rock hardness, soil type, terrain, the minimum slope and maximum slope in this area, which gets me to determining the structure cost. I have the percent aerial buried and underground, the density, The equipment size of that drop terminal is a 25-pair terminal, and it is a distribution terminal. So there's a database on each and every record that contains this information. So what we did is, some of this bleeds off the chart here, but I've got my customer location here. So this is where Steve Rosenberg lives. This is his central office down here. In the database we have, we know the exact path that we're taking to get Steve to his central office. Along that path, I know every time I have kind of an intermediate junction point where I interconnect with other distribution terminals. So what you're seeing is Steve's connected to his distribution terminal here. There's two other distribution terminals actually come in and junction here and traverse down this path. Another two come in, traverse down this path. Until you get down to the serving DSLAM, and then the DSLAM has a path going back. So this is kind of trying to give you a pictorial representation of the information. This then is actually a dump from the database, and it was actually how I tested to make sure everything was working, was this is the length, this is the drop length, so it's 50 feet is this distance. On this next segment, I know it's 194 feet from this terminal here down to this terminal here. It's 211 feet from this terminal to this terminal, 118 from this terminal to this terminal. So I've got all those distances in the database. I then go, well, I want to push all this information up to one record in a database for this customer. And that's what the whole farming process is. So I've got this distance, and over on this side, I know the density group it falls in, the terrain it falls in, how many working pairs are on that, how many cumulative working pairs, the media, how big the cable is. So you can see that cable grows in size from a 2-pair drop to a 25 to 100 pair to a 200 pair. I've got the copper splices required, so I need 25 splices here, 125 here, and this goes back. Fiber optic splices, the number of setups required, I need a setup here. I've got the MSRT route count, which tells me if there's sharing with feeder. And then finally, this cum node 2 is how many DSLAMs do I have on that path? So there's none up here because I'm in the distribution side. But as I go down here, you see I start to have multiple DSLAMs writing this fiber back. So now kind of using that capacity cost, well, more the TELRIC approach, I look at this 194 feet. And I go, well, of that 194 feet, I know that, and the 194 feet is from this to this, but this is shared amongst this terminal and these other two terminals. So I spread it based upon working lines. So I've got out here how many working lines I have here, 13 working lines. For Steve Rosenberg's home, there is only one customer assigned to this distribution terminal. So that's what I'm keeping track of. So I take 1/13 of the 194 feet, which turns out to be 15 feet. So I'm assigning 15 feet of the cable to Steve Rosenberg on this first run. Same on the structure side. And I'll explain why these start to differentiate as you go down. I do not have any shared structure because there's this number is 1 means I do not have any sharing, so there's no shared structure. I do not have any splices or setups to spread. So I go through that exercise, and actually, I have it written up here for you to go through. So this is the 13. So from the TELRIC option, I take the 25 pairs. I've got 211 feet times, actually this is a different record. So let me go back to this and I'll get you to that. So now I get down, so now I'm on the 211 record. On the 211 record, I look out here and I've got 51 cum pairs. So my apportionment is 1/51th of that cable. But I want to keep and simplify my database. So what I do is I look out here and I understand there's a 100 pair cable. I don't want to have all the various cable sizes in the database. So I turn that 100 pair into a 25 pair equivalent. And I showed you earlier It's all based upon the cost differential. In the cost data that was provided, I came up with the equivalent 25-pair cost ratio. So as you see, the 25-pair cost ratio on the 25 is 1. As I move down, 100-pair, it is 3.23 times more expensive than 25-pair cable. So, on the cable side, since this is a 100-pair cable, I really am converting this to 323 feet of 25-pair cable. It's equivalent in cost to 323 feet. So, calculation is, I take the 211 multiplied by 3.23. I multiply that by the working pairs, so this is the Telric formula, which gets me to my 13 feet of cable. The structure, there is typically no cost differential between kicking the 25-pair cable and the 100-pair. So I don't do that multiplication of any adjustment for the fact that it's 100-pair on the structure cost. I still keep track of all the splicing and setups required, so I go through this process on every record in that database. So I will go through, and by the time I'm up to the last cable, it's 1,300 feet long. I only assign 111 feet to Steve, and I do 111 feet because it's actually a 200-pair cable, so this equivalency is much bigger. But he only gets 18 feet of that. So I tally that up. So on the distribution side, I've assigned to Steve's pedestal location 8,992 feet in length. That's how far it is, actually. But he only gets 779 feet of cost associated with that, 142 feet of structure cost, 4.17 splices, and 0.008 setups. So now I've got a data set. This is one record in a database versus this entire structure, but I've captured all the cost detail in that one record. So that's our farming of the data to get to an intelligent topology database. We do the same on the feeder side. So I will look at, on the feeder, I will look at that record. I do the same thing, the Telric approach. So I've got 4,559 length of fiber. There's one pair equivalent here because it's a 24 pair fiber or 24 strand fiber. I look in this table, it's 1, but you can see the relative cost ratio of the fibers. I multiply that by 1/3 because I have 3 D-slams working off this fiber. So I am apportioning 1,500 feet of the cable to that particular D-slam. You might shake your head of why did you go through all this, but this was really a way to get it into a database that we could use in a quick and reasonable fashion. So this is then in CQBAT, there is a distribution table in each and every state for each and every wire center, for each and every census block record. For that census block record, it tells me the number of working customers in that census block, the length of the drop cable, the number of working res, working biz, how many working lines there are, the length, which is just the raw length of this. So this is the max length of all the customers. So I got 2 customers there. I look for the maximum, and that's what I report here. This is the cumulation of all the node 3 cable distance assigned to these customers. The same with splicing. And then I got the structure table going out, so I understand structure in medium, hard, terrain. I've got shared structure identified. Shared structure allows me to share the cost between feeder and distribution. So this 420 feet of shared structure has a different cost than 420 feet of normal structure. I keep going out. I've got the equipment quantities. It tells me how many pedestals are assigned to that CB record density, and then it's got the parentage. This exists for each and every wire center. This is the 12K copper design. And there's one that looks very similar to it for the feeder side. The difference on the feeder side is each record represents a D-slam. That D-slam is then apportioned out to the customers based upon working pairs as well. So that this gets me to the total DSLAM cost. I then apportion it to every customer attached to that DSLAM based upon working pairs divided by total working, or this client divided by the total working pairs on that DSLAM. Does that help on your question? Hopefully some people said, oh, I see how that works now. Which now gets us to, so as you look at this, I've got no cost information in here. I've just got lengths and counts. That's what we farm out of the topology. So when we run CQBAT, all I want to get is kind of an inventory of how many feet or how many units of something I need. And that's all resident in this database. So you'll see I need 0.31 splices. So now we've got a CapEx table, and there is a entry in here for cable splice. It is $1.73 per splice, based again on coalition input on how much time it takes to splice, divided by the number, and it turns out to be $1.73 per splice. So that's what I assign to that customer. I find out that the setup is $63 for a setup. So when I go back to my other table, the census block here has been assigned 0.31 setup. So I'm going to multiply 0.31 times $63 if it is aerial. So we go through and tally all those costs up. So as you look at this CapEx has kind of the intelligence of the costing. The CQBAT that we farmed is the intelligence of how many units I have. And that's where I said I don't think you have to rerun the topologies often because the units aren't going to change. I design a network, it is what it is. This is what changes. I may have different assumptions about do I include customer premise equipment or not? Do I include the NID or not? Do I include the drop or not? If you look at the drop, this will answer a question. I go across here, I am putting the demand that drives the drop cost, which is it's $49 for the labor, $8 for the material for that NID. I've multiplied by the take rate, so that's telling me take rate, my data take is number of successful or subscribers. So I'm only putting NIDs in at installed subscribers. On the drop is multiplied by the node 4 cable. But then I have another column here called multiplier because I really want to capture all the cable out there, but I only want to apply the data take rate portion of that cable. So this will give me back on this record. I have a node for length of 100 feet, 2 customers. My data take is 90%, so I assume 1.8 customers, which you might go, how can you have 1.8? But on average, it works out. So I take 1.8 multiplied by the 100, which gets me, I take 0.9 multiplied by this 100 feet of cable, giving me 90 feet of cable, and I multiply by that to get my drop cost associated with that census block. And that's basically the structure of this CapEx workbook is, this is the raw cost of the plant. It accounts for sharing. So when you look down at the structure cost, 64 cents for a pole, $1.55 for a pole, and that is on a per foot basis. So I've taken the pole cost, and it might be $800 for a pole. You own typically 50% of the pole, so it drops it down to $400. I divide that by a pole spacing, which is an input. Pole spacing may be 150 feet, which gets you down to about $3 a foot, which is pretty close if I was ballparking. This is a $2.19 per structure foot for aerial. I take the structure normal footage that I have in my topology table, and then I have a multiplier, and I can get into that potentially tomorrow morning. But here I just tried to identify each of the entries in this CapEx table if you've used the CapEx table. The Tech 3 matches to the topology I've selected. So in that CapEx table, you'll see entries for fiber to the D, fiber to the P. The terrain and density allow me to do lookups. If it's NA, it means it's just not applicable. Like for customer premise equipment, it's not applicable. I have the plan account. This is what triggers which annual charge factor to use. The cost family that you see up here, distribution, tells me I need to go into the distribution table or the feeder table to get the network topology, or there's a middle mile table as well. So that's really telling me the topology table to look in. This units is used in the multiplier equation. The G or B is your greenfield or brownfield. And you can see the settings are G for greenfield, B for brownfield, and A for all. So if we're putting customer premise equipment in, we just said it goes in all, no matter what type of assumption you make. You've got your minimum capacity, so the demand has to exceed the minimum and has to be less than the max. So when we're looking at DSLAM sizes, we know we got 3 different sizes. This is how we control which size is used. And then unit capacity is the divisor to determine how many units I need. You got your material amount, non-material amount. You've got your node demand, which is the demand that drives it. The multiplier adjusts that multiplier. And then this final one is the output field that defines where it goes into the solution set on mapping. And there's the multiplier table. Users typically don't get to see that because, one, I didn't want to have to explain it to users. It's actually using a lot of SQL structure in it that I'm looking for node working lines. So if my multiplier is none, I'm going to multiply by 1. If I've got the case 16 and case 32 is when I'm looking for the splitters, which splitter to use. So it just allows me to turn on or off something. So these are really adjustments to that demand multiplier. And I can go through this at another point in time if people are interested. So in the end, I just wanted to show this again. So we've gone through this whole process of how we get then to that solution set.
So that was an awful lot late in the day, I have to say. Are there and we're right up against time, but I do want to take a few minutes to take questions just in case you forget everything you just heard before the morning. So does anybody have any questions before we head out for the evening? Stunned silence.
I want to get out of the room. Don't ask a question.
Well, okay then. So I'd like to thank all of our presenters today for what I think has been very informative, challenging but informative day, quite helpful. Tomorrow morning we are in a different part of the building. We are in the 4 South conference room. So when you come in, there will be people, as I understand it, to help get you up to the 4 South conference room, which is behind some of the electronic doors here that you may be familiar with. So when you come in, please let the security know where you are headed, and be on the lookout for people who can help shuttle you upstairs. And I just want to thank everybody who helped present today, and look forward to tomorrow morning.